to start the workshop today. Welcome to the fourth Embodied AI workshop at CVPR 2023. My name is Claudia Perez-Darpino. I'm a research scientist at NVIDIA, and today I'll be introducing the workshop on behalf of a large number, is not moving forward. A large number of organizers. A lot of us are here today. Some of us are online, but it has really been a large collaborative effort now across years, actually. We have about 21 organizers spanning like maybe 10 organizations or more. So we are very excited to really come together as one in order to explore this emerging field of embodied AI and see what we can all do together to move it forward. So the field of embodied AI really focuses on how intelligence emergence can emerge from the agent's interactions with the environment. And the reason this is important is that the interaction with the environment really will cause that the agent can influence in its own future. And this idea comes really as the convergence of multiple fields, what has been happening in computer vision, natural language processing, and so on. As these fields have been making progress, we have started to understand that it is possible to study the confluence of those in a way that really is happening in an agent that takes actions in the real environment and influences its own perception of the environment, so that we actually have kind of data and experience that involve both a complete loop between the action and the perception of the agent, as opposed to only have passive observations of the environments from which we learn from. And if you look at the history of computer vision, it started by using what we call passive data sets, right? Like you would have either pictures or photos or videos. And even if videos are moving, that's not really what we're calling non-passive. Even if videos have motion, these videos have been taken in advance by an agent that was observing the environment, but this agent didn't take actions on purpose to collect the data while it was in this environment. So this is in contrast with other fields in which we really need the agent to learn how to take actions to be successful and accomplish goals in this environment. And this is what the field of embodied AI and similarly robotics have been studied. And this is really an emerging field that has been growing in both the maturity of the tools, the engineering tools, for example, simulators, data sets, and infrastructure. And it has also been growing in terms of research contributions. So this is the fourth year of the workshop that we are starting today. And the first 3 years, I think we were looking at what we did in the first 3 years as a retrospective. We were able to put an archive paper that covers the progress over those 3 years. And really, I think as a starting point, it was really about putting together this infrastructure and these tools by making progress in these simulators and data sets. And a lot of our challenges and a lot of the work that has been happening in this community was about making progress on those in that infrastructure. But as we come to the fourth year, we started to see that there are some emerging trends of research within that community that is leveraging these tools. So we decided to move a little bit forward from specifically this kind of engineering contributions that give the basis for our research to now propose that we're going to try to focus on main topics of research that are leveraging these tools. And for the proposal for this year was to focus on foundation models, generalist agents, and sim-to-real transfer. And these are 3 topics that we are really seeing emerging. And the research contributions with these tools that we developed during the first 3 years are really happening in these fields. So we're going to have speakers that are going to cover topics in these 3 main areas, and the challenges are also grouped trying to accomplish goals that are specific to these topics. So I'll cover a little bit of questions in these 3 fundamental topics. So first, to introduce the concept of foundation models, these are really models that are trained on large-scale data. But the fundamental concept of this is that you will train using a task, But then this large pre-trained model can be adapted to perform different downstream tasks. And this is basically what have been happening in computer vision and natural language processing. We see that a large model is being trained in a single task, even a simple, very simple task, such as predicting the next word, for example. But then this really large model can be applied to different downstream tasks. So the question is, what does this mean for embodied AI and robotics? Can we integrate these different models that have been trained in these other fields? How can they be modules, or how can we replicate an approach in which we train on a large data set and then are able to adapt to a downstream task that actually requires interaction with the environment? What are these data sets? What are the architectures of foundation models that can be applied to embodied AI tasks? What are suitable architectures? How do we even get these data sets? It seems like this kind of data would require a lot of more types of data, types of multimodality that might not be needed on the first tasks that have been studied. So really, there is a big question of what does it mean to have foundation models for embodied AI and robotics. And some of our speakers will be covering this. The second topic that we picked for this year among the organizers is generalist agents. And here we're talking about single learning methods that take data from multiple tasks and then are able to do zero-shot generalization to novel tasks. And really the need for this kind of generalist agents comes also from the lack of data that is suitable for these tasks, right? Collecting data for embodied AI is significantly more challenging than collecting data for a single static computer vision task. So this is expensive and complex to collect. And for that reason, we would like to leverage as much as possible. And that probably means having agents that can take different sources of data from different types of tasks and embodiments in order to downstream adapt to new and novel tasks. And finally, we are going to focus on sim to real. And really, sim to real is one of the fields that has been showing a lot of progress recently in being able to train embodied agents in simulation, highly parallel and fast simulation that can be realistic, even photorealistic, and then being able to do zero-shot transfer from policies learned in simulation to the real world. And in all these slides, I've been showing some highlights of examples of not my own research, but research in the field that has have prominent results in these topics. So with that, we have, I would like to summarize that we have 10 challenges. There is a large number of organizers here that have been, putting up the infrastructure for their challenges, running the challenges, running the leaderboards. So today we're going to hear from 10 challenges in navigation and interaction and rearrangement. These are all very interesting results. We are going to have a number of winners. Some of these challenges have 1 or 2 winners. They are going to be announced today. So we are going to have in the morning a first panel of the challenges in navigation with the simulators outlined here. And then in the afternoon, we're going to have the interaction and rearrangement challenges. We wanted to highlight one of these challenges, the one that got the most submissions. They got about 20 competitors, which it's a pretty good number. I feel like the challenges have been increasing in the reachability and usability of the code bases. So hopefully for years to come, we have more and more participants, and the numbers get better and better. We're gonna have awards for the winners of these challenges, which are sponsored by these organizations. We're gonna select a best paper award from the submissions that we got for contributed papers. We have about 22 contributed papers that got accepted, and they will be in the poster session during lunchtime, and that's going to be on the other building. which, it works because lunch is in the other building too. So well, let's see what happens. Okay, and finally, this is a schedule. It's pretty packed and intense. So we're going to have 6 speakers. 3 of them will be in the morning, 3 of them will be in the afternoon. All this information is in the website. We have tried to make the website the most comprehensive possible. We're going to have talks on robot learning for understanding video, embodied reasoning through planning with language and vision foundation models, building the embodied autonomous agents with multimodal interaction, large language models for solving long horizon robotic manipulation problems, toward foundational robot manipulation skills, and from goals to grasp, learning about action from people in video. And at the end of the day, from 4:30 to 5:30, we're going to have a panel in which all speakers will participate. So, well, with that, I hope we all have an excellent day. I cannot describe how excited I am. This really takes maybe a year or more of organization. So yeah, have a great day. Learned a lot. Participate and let's see what we learned today. And I think our first thing is going to be the navigation panel or the navigation challenges. So who is the first one? Javita. Okay. Oh, actually, I'm still sharing. Okay, so yes.
All right. Hello, everybody. My name is Jacob, and it is my pleasure to present here today the 3rd iteration of our Room Across Room Habitat Challenge. This is co-organized with Alex, Alexander, Stefan, and Peter. So in this challenge, we place an agent in a previously unseen environment and give this agent a natural language instruction, such as take a left and go down the hallway, turn into the bedroom on the left, and stop at the foot of the bed. This instruction corresponds to a path through the environment that we want the agent to navigate using an action space of discrete actions of move forward, turn left, or turn right. The agent perceives its environment through egocentric vision consisting of RGB and depth observations. One of the interesting aspects of VLN is that this natural language instruction isn't just describing a particular place or item to go to. In describing this entire path, certain linguistic phenomena emerge that the agent has to deal with, such as various forms of referencing, allocentric and egocentric, as well as object references for grounding. Doing this over a sequence of actions, the agent's evaluation of its understanding of language is directly tied to the actions that it takes in the environment. So this is a very challenging task. We instantiate our challenge in the Matterport 3D scenes of 90 indoor environments. Some of the challenges that come with these environments include obstacle avoidance, partial observability, and long horizon planning. We interact with these environments using the habitat simulation platform. For the episodic data set that we use here, we're using the Room Across Room, or R-Cross-R data set that was released in 2020. Some of the highlights of this data set include 16,500 navigation paths, 126,000 instructions spread across 3 different languages. And part of this data set include time-aligned pose traces for fine-grained training, as well as complex navigation paths. So instead of all paths starting and ending and being a shortest path between those points, some of these paths include more complex behavior, such as traversing across rooms that aren't necessarily these shortest paths. So in this challenge, we are performing continuous space navigation. This data set was originally proposed for navigation on top of graphs where an agent moves from one node to another. But in this challenge, agents are taking these discrete actions instead. The embodiment of this challenge is based off of the Locobot platform with these parameters here. I'll just highlight these here, but we don't need to go through the specifics of it. For evaluating agents in R-cross-R habitat, the primary metric we consider is normalized dynamic time warping, or NDTW. This is a measure of path alignment between a reference path that an oracle takes and the path that an agent actually takes. This is a measure between 0 and 1 that an agent's trying to maximize. We also report upon secondary metrics, including navigation error for where the agent stops, as well as a success for reaching that final terminal location. So now moving on to our first place results in this year's challenge. I would like to congratulate the Grid team on their top performance. The Grid team is coming from the Institute of Computing Technology in the Chinese Academy of Sciences. Let's now go over these results. So results for 2023, we see the Grid team taking first place here with a normalized dynamic time warping score of 54.3. And if we move on to all of the results on our leaderboard, consisting of all results from the past 3 years, we see these results highlighted. Highlighted in green are the results from each year of our challenge. At the bottom, we can see results for the baseline model, as well as the top 2021 performance. And at the very top of the leaderboard, we see the model from 2022. Just under it, we see the Grid team from this year. Let's zoom in on these top 2 results a little bit. So comparing these with normalized dynamic time warping, the comparison is very similar, where Grid is just slightly beneath the reborn method. But the Grid team sets a new state-of-the-art on navigation error and improves results on success rate and SPL over the reborn method. Here's a quick look at the progress on this benchmark over time. We see that the baseline and 2021 methods are on the left, and our most recent methods from this year and last year are on the right. And we are seeing a nice improvement on both normalized dynamic time warping and this decrease in navigation error. So I'm excited to see what comes next, moving on into the future, where we still have plenty of headroom, both on the gap between continuous environments and discrete navigation graph environments, and the gap to human performance. The leaderboard remains open, though the challenge is closed, and the starter code is still available. So you are encouraged to submit your models to this benchmark. Now we will move on to the winning team's spotlight presentation of their method.
I'm Zihan Wang, currently a master's student at the Institute of Computing Technology of the Chinese Academy of Science. Here I'm very glad to present our method grid memory map for vision and language navigation. In our method, we build the top-down egocentric and dynamically growing grid memory map to structure the visited environment. From a global perspective, historical observations are projected into a unified grid map in a top-down view, which can better represent the spatial relations of the environment. From a local perspective, we further propose an instruction relevance aggregation method to capture fine-grained visual clues in each grid region. In previous works, in order to achieve backtracking and make global planning, a few approaches structure the topological map. However, these methods are difficult to represent the spatial relations among objects and scenes in historical observations, thus a lot of detailed information is lost. And some methods use object-centric scene graph to represent the object relationships, which are not enough to represent all visual information, such as house structure and background. The top-down semantic map represents spatial relations more precisely, but the semantic space are extremely limited due to the predefined semantic labels. In contrast to previous approaches, we propose the grid memory map, a new visual representation structure for modeling global historical observations during navigation. Specifically, the grid map divides the visited environment into many equally large grid regions, and each grid region contains many fine-grained visual features. We dynamically construct a grid memory bank to update the grid map during navigation. At each step of navigation, the grid features from the pre-trained CLIP model are saved into the memory bank, and all of them are categorized into the grid map regions based on their coordinates calculated via the depth information. To obtain a holistic representation of each region, we design an instruction relevance aggregation method to capture the visual clues most relevant to navigation instructions. With the help of aggregated features in the grid map, the agent is able to accurately conduct the next action planning. Panoramic view features, map cell features, and trajectory features are fed into a two-stage cross-modal encoder for both local action prediction and global action planning. We pre-train our model with RxR and Markey MP5 dataset on the Matterport 3D simulator. The HER loss requires the agent to predict the next action only based on the map features and navigation trajectory, without panoramic observations, which supervise the map module. The SAP loss-gated fuse local action scores and global action scores to supervise the action prediction. We fine-tune our model with RxRC dataset on the habitat simulator, and with sliding allowed to avoid getting stuck. Next is our demo showcase. As you can see, our grid memory map expands with the expansion of the visited environment, which enables better long-term planning with global spatial perception. By using a pre-trained waypoint predictor, we predict a set of candidate waypoints based on depth observations. Our model, which enhances the entire environment representations, will select the appropriate one from the candidate waypoints to move. Our model outperforms other methods that use the same waypoint predictor. Further, we use a tryout controller to detect collisions and help the agent escape from getting stuck. Thanks for their great works. Combining the above methods, our model achieved top performance in NE, SR, and SPL measures with a near SOTA normalized dynamic time wrapping score. Thanks for watching.
Thank you, Jacob. Next up is Multion.
Hi, everyone. My name is Sonia. I am a PhD student at SFU with Angel Chang. This is held in conjunction with Tommaso Unnat, Angel Chang, and Manola Sava. So the multi-object navigation task, this is where the agent needs to navigate to a series of target objects in a particular order. The 3D objects are inserted into random surfaces in the environment. This is basically a generalization of the single object navigation task. Here, 3-on means navigating to 3 objects in a sequence. The agent can take one of 4 actions. It can move forward, turn left, turn right, or generate the found action within 1 meter of the goal object. And the task setting allows a maximum step of 2,500 steps. The agent observes the environment through RGB and depth sensors, and it has access to the category of the current goal object. It is also given its current position and orientation relative to its starting point in the episode. Initially, the dataset contained only cylinder objects with same size and shapes, but with different colors. And these were placed on the floors, and these were easier to detect. In Multion 2.0, we introduced an additional set of more natural-looking objects, but there were only 8 categories of objects. This year, we have completely moved away from the cylinder objects to a much larger set of natural-looking objects, and this has like various shapes, sizes, and colors. So we have over 50 category of objects from ShapeNet, and it ranges from a very small fork to a large piano. However, sorry, most of the objects are very small, such as fork or spoon or a knife a bottle opener, and so on. And as such, these are very hard to detect. And unlike the previous versions, Multion 3.0 contains multiple instances of the same object category and thus provides intra-class diversity. This time we have placed the target objects on other surfaces in the scenes, for example, on bed, on couch, and so on. This is also unlike the previous versions where we place the objects on the floor. We also inserted distractor objects so that the agent needs the capability to discriminate between the target and the non-target objects. And we reserve a set of 5 unseen objects for our test split. All these features make Multion 3.0 much more challenging than its previous versions and hence much more interesting. So in addition to the standard evaluation metrics for visual navigation tasks such as success and SPL, we also use progress and progress weighted by path length. Next, I'll talk about the baseline that we used for our challenge and some of its limitations. So this approach is based on RRR. It's a modular in nature, and it consists of different modules. The object detection module identifies objects using RGB images. We use a pre-trained DETIC model here, along with the object categories as custom vocabulary in a zero-shot manner. These object categories are then projected onto a top-down semantic map of the environment, and this essentially serves as a memory for easy retrieval later. If the agent has not yet observed the current goal, the exploration module actually allows the agent to efficiently search the environment and discover more objects. The planning module basically selects whether to navigate to an observed goal or the sampled exploration goal. And finally, we have a pre-trained point nav agent, which can be leveraged as a navigation module. And this basically transports the agent from its current location to the goal location. Here are the results of the baseline. We can see that the performance is pretty consistent across the splits. However, there is a lot of room for improvement. The modular nature of RRR actually allows us to compare different approaches for different modules. So here we compare DETIC with other zero-shot object detectors, but we found that DETIC is performing the best so by far. However, the gap in the learned detectors with the one which uses the ground truth semantics actually indicate that we can do significantly better on the object detection. We also compared different exploration strategies, which we found to be useful in other navigation tasks, but by far uniform top-down sampling, which was introduced in RRR, performs the best in our case. This is mainly because we have a maximum step limit, and frontier and stubborn, being more systematic in nature, can only cover a certain portion of the environment, whereas the uniform top-down sampling covers much wider area. Next, we visualize some of the failure cases of our model. So here we observe that the DETIC actually fails to detect very small objects. For example, it fails to detect the fork on the couch. However, we also noticed that if we were to give higher resolution RGB images to DETIC, it tends to perform much better. In fact, we noticed a 2 times performance gain in both success and progress when we used 640 by 480 images. Another thing that we observed is that DETIC, the agent needs to be very close to the small object for DETIC to correctly identify it. This is because our exploration module often fails to cover all the crevices and corners within the maximum time limit that we set for it. We found some of the episodes where it misses some corners of the environment where the goal object was located. This brings us to the end of the presentation. Unfortunately, this year we did not receive any submission, but the good news is we'll keep our challenge open and we encourage the community to try out our data set, and you can reach out to us in case you have questions. In summary, Multi-on 3.0 is much more challenging than previous version. There is a lot of room for improvement over the baseline. And we hope that our findings help us help other methods which are to follow. And finally, I would like to thank the organizers of the workshop, Eval AI and Habitat for supporting us. Thank you.
Thank you, Sonia. Next up is Sound Spaces. Sagnik is presenting virtually. So if you can, oh, you're in person. Okay, never mind. Cool.
Hi everyone, I'm Sagnik, and in this talk, I'll summarize the Sound Spaces challenge that I co-organized this year with Changan Chen, Unnat Jain, Rohan Gao, and Kristen Graham. So moving around in the real world is naturally a multisensory experience, and an intelligent agent should be able to see, hear, and move. And this has motivated us to organize the third Sound Spaces challenge on audiovisual embodied AI. More specifically, this year, we are targeting audiovisual navigation in 3D simulated environments. This challenge is based on the well-known SoundSpaces platform. SoundSpaces is a habitat-based simulator, and it enables realistic audiovisual simulation for replica and Matterport 3D datasets. In this challenge, we only use the Matterport 3D dataset due to its larger scale, and we discretized all environments into grids. And so the way we generate the sound is by using room impulse responses, which basically kind of captures how sound travels from one point to another in the environment and is a function of the room geometry and materials and so on. In the audio goal navigation task, there is a sounding object randomly placed in an unmapped environment, and the agent receives a 1-second audio clip emitted from the source at every step of its action of the episode. The agent is tasked to navigate to the sounding object in the environment with one of these 4 actions: move forward, turn left, turn right, and stop. And the success is defined as when the agent issues a stop action at the source location. In this challenge, we considered the unheard sound setting, where the model is trained on multiple sounds and tested on unheard sounds. There are these many disjoint sounds in the train, validation, and test splits respectively. Note that the environments are also split into disjoint sets, so that it requires the model to generalize to both unseen environments and unheard sounds. Participating teams are judged on the basis of their test split performance. After calling the stop action, the agent is evaluated using the SPL metric, which is a very well-known metric for navigation tasks. This year, there were like 15 teams from various universities who showed interest in this challenge. One team was able to make a successful submission on the test set. So we speculate that the size of the data set, which is approximately 1 terabyte, might have like kind of made it unfeasible for a few teams to participate. Team AK Lab Tokyo Tech from the Tokyo University of Technology won the challenge. So we congratulate them for winning the challenge, and they outperformed the baseline by a large margin. Next, I'll play the video of the winning teams method. Oh, like before that, in terms of future directions, we plan to make it easier for participants to participate in the challenge by enabling the simulator to render on the fly. So basically, we want to move on to the second version of the Sound Spaces simulator, which allows this kind of rendering. And also, we want to test the top teams methods in the starting in the next edition on a real robot, probably like a stretch robot, to make the task more challenging and realistic.
Hello, my name is Haru Kondo. I am a member of the Kanesec Laboratory at the Tokyo Institute of Technology in Japan. I would like to present the method we used in the Sound Spaces challenge and its results. We proposed and experimented with a method called Sound Direction Map. First, an overview of the Sound Direction Map (SDM) is provided. The SDM is a representation of how far and in which direction the sound source is located from the agent. The SDM is represented by black noise surrounding the agent. In the SDM, the closer the distance from the agent to the sound source, the higher the value of the noise in the direction of that sound source. In this way, the SDM allows localization by direction and distance. This represents the relationship between the values of the noise in the SDM and the distance from the agent to the sound source. We have considered and experimented with two equations to convert from distance to the values of the noise in the SDM. One is to convert to the inverse, and the other is to convert using a linear function. In both cases, clipping is performed to obtain a value between 0 and 1. The closer the distance is, the higher the value becomes 1, and the farther the distance is, the lower the value becomes 0. The geodesic distance is used for the distance. Preliminary experiments have confirmed that using geodesic distance is more accurate than using Euclidean distance. We propose a method that uses a neural network to dynamically predict the SDM while the agent repeats its actions. AT means the current audio observation, AT-1 means the previous action, and D-T means the prediction of the SDM. So the SDM encoder is structured to predict the current SDM by inputting the current audio observation, the previous action, and the previous SDM. We also tried two ways of the training the SDM encoder. One is to input the SDM that the agent predicted last time as the previous SDM. The other is to input the previous true SDM as the previous SDM. However, in both cases, the SDM that the agent predicted last time was inputted as the previous SDM at the time of evaluation and testing. In addition, dropout was used during training. This means that the value of each node in the SDM that is input as the previous SDM is set to 0 with a certain probability. This certain probability is called dropout rate. The purpose of this is to prevent too much reliance on the previous SDM when predicting the current SDM. This is because the predicted previous SDM can fail to be close to the true previous SDM properly. Here is an overall view of the network of the model called EveryNav. The structure is based on the JRU and outputs the value function and the policy by observing visual and auditory information. Here, the SDM was applied to the EveryNav network. The whole network is shown here. The whole network is trained in an end-to-end manner. In addition to the gradients flowing from the policy networks, the gradients from the mean squared error between the predicted SDM and the true SDM were used to update the weights of the SDM encoder. We used DDPPO to train this for 1 day with 4 GPUs. Here are the test results by the model with the highest success when adjusting some hyperparameters. Here, the SDM that the agent predicted last time is input to the SDM encoder as the previous SDM, and the dropout rate is 0.2. The equation to convert from distance to the values of the nodes in the SDM is 1 in distance, and the number of nodes in the SDM is 4. The results show that every node with SDM exceeded every node without SDM for success and DTZ, but every node with SDM fell below every node without SDM for SPR and soft SPR. Here are the test results by the model with the highest SPR when adjusting some hyperparameters. Here is the SDM that the agent predicted last time is input to the SDM encoder as the previous SDM, and the dropout rate is 0.0. The equation to convert from distance to the values of the nodes in the SDM is 1.1 minus distance in 10, and the number of nodes in the SDM is 4. The results show that every node with SDM exceeded every node without SDM in all metrics. For this competition, we submitted this model. Here are the results of training, evaluation, and testing using the replica dataset instead of Matterport 3D. Here are the test results by the model with the highest performance when adjusting some hyperparameters. Here, the previous true SDM is input to the SDM encoder as the previous SDM, and the dropout rate is 0.2. The equation to convert from distance to the values of the nodes in the SDM is 1 in distance, and the number of nodes in the SDM is 8. The results show that every node with SDM exceeded every node without SDM in all metrics. Furthermore, we see that the improvement rate is higher with Replica than with Matterport 3D. We believe this is because our proposed method is not suited for complex environments with wide and many worlds. That's all. Thank you for listening.
Thank you.
Thank you, Sagnik. Next, we have the RS or RVSU challenge.
Oh, that's the end of this presentation.
Okay.
Oh, good. All right. Hi, everyone. I'm David Hall. I am representing the Robotic Vision Scene Understanding Challenge. This was created originally by QUT and is now supported by the CSIRO. So, the Robotic Vision Scene Understanding Challenges consists of two different navigation and understanding tasks. One is a semantic SLAM task, and the other is a scene change detection task. Both of these tasks involve having an autonomous agent explore an environment. The difference being that for scene change detection, you traverse the same environment twice. But between the two traversals, there'll be some changes. Some objects get added in, some objects get removed, and you might also have to deal with daytime to nighttime visual conditions. Goal of the task is for the competitors to create 3D object cuboid maps, and then they are evaluated based on an object map quality score. For the scene change detection challenge, they only need to map out what things have changed between their traversals. Now we have three different task variations or difficulty levels, or I should probably say this time we have two task variations, because these were all designed to try and help the transition the computer vision community over to a more robotics-based problem. But in the spirit of this year's Embodied AI workshop, we have decided to discard the passive version of the challenge, only dealing with active navigation. So the two variations that we are focused on is active ground truth and active dead reckoning. For active ground truth, they have control of an autonomous agent with very simple commands, move to an angle, move forwards, move backwards, but they get their ground truth pose for free. With active dead reckoning, they get noisy pose data, which they then need to adjust for as they are mapping out their environment, something more akin to what you'd see in the real world. This is all enabled by the benchbot framework, which is how users interact with our challenge. And we use the benchbot environments for active robotics, or BEAR. This is all built within Isaac Sim. Originally, it was built in Unreal and has since been ported over to the Omniverse simulator. And benchbot sits on top of that to allow the users to interact with the system. So this year, we got 78 individuals registering interest, which is up from the 23 registering interest last year. We had 5 teams actively participate, with teams ranging from 1 to 12-person teams. And the top 2 teams received GPU prizes sponsored by NVIDIA. And the first place team will also be getting a prize from the Embodied AI workshop. So thank you, Embodied AI workshop. This year, we got improved results across all 4 of the tasks that were evaluated. And this was the first time we actually got submissions for active dead reckoning. This is probably helped by the fact that we fixed some of the bugs that were in active dead reckoning from a previous year. General approach trends, everyone focused very much on the map generation rather than the active components of exploration. They use pre-trained object detection models, both 3D and 2D, oftentimes using both of them. And there was a lot of frontier-based exploration policy. So almost every approach used the same policy for trying to explore their environment. In second place, we had Tata Consultancy Services Cyan Paul. He was the best across the active tasks with ground truth pose information, but did not submit anything to dead reckoning. And as dead reckoning is more highly weighted in our evaluation process, he came second rather than coming in first. But his OMQ scores, our object map qualities, were impressive, 0.424 with a maximum score of 1 and 0.242, which may not seem like a great deal, but it is up from last year where things were closer to 0.2 and 0.1 respectively. Their approach involved both a 2D to 3D detection pipeline and then a final 3D detection for large objects such as tables and chairs, which got used after the entire point cloud for the environment had been created. They were using a Detectron for 2D detection and DBScan and LLCCP to cluster the point clouds to create their final 3D detections for smaller objects. And for the large objects, they were using soft group detection for 3D, and everything, the entire map got refined based upon intersection volume ratio rather than IOU. So very well done to Cyan Paul. In first place, we had the team MSc Lab from the Korean Advanced Institute of Science and Technology. They came first across the active dead reckoning task, and they were second in the other, the active ground truth versions of the task. And again, getting very competitive results with Cyan Paul's results came in first. Their approach was to use a pre-trained 3D object detector and a pre-trained 2D object detector, which utilized class-based 3D anchor boxes. Their 2D object detector was QueryInst, which is the same as what they used last year. They had attempted to update their 2D object detector, but found no great improvement in their results. What they did focus on to improve their results was their localization, particularly for the dead reckoning task, where they used a SLAM system, focusing on ICP-based SLAM. They tried to use images initially for their SLAM system, but found that the differences when you went from daytime to nighttime conditions just did not allow for as good a mapping process. And they also used some visual place recognition when doing scene change detection to help generally localize themselves before going to their point cloud map. So very well done to Team MSc Lab. I think that's all the time that I've got. So big thanks to everyone who participated. Big thanks to the supporting organizations, the development team. So myself, Ben, and Nico, who were supporting it this year, and the Embodied AI workshop for giving us this platform to share this work with everyone. Very much thanks. Information.
Thank you, David. And lastly, we have habitat. Okay, just okay. Oh, sorry. Yeah. Okay, yeah. Hi everyone, I'm Santosh and I'm excited to announce the results of the Habitat Navigation Challenge. This work was done in collaboration with Georgia Tech, Meta AI, Simon Fraser University, UT Austin, Cornell, and Oregon State University. Here's a quick preview of our challenge. We introduced two different tasks this time around. The first was the image goal navigation challenge, where you're given an image target in a new environment that you must navigate to. And the object goal navigation challenge, where you're given a goal category and you must navigate to an instance of this goal category. Both challenges were held in the newly introduced HM3D semantics dataset, which contains dense semantic annotations for 210 large-scale 3D scenes. Let's first look at the object nav task. In this task, you have an agent that is placed in a normal environment, and it's asked to find a goal object such as chair. It is given the observations of RGB depth, as well as a GPS and plus compass sensor for localization. The agent must go and navigate to one of the various object instances in the environment and stop within 1 meter to be successful. More specifically, the object nav success is defined as follows. Given a goal instance, in this example, a lamp, we sample a set of viewpoints that are around 1 meter of that particular object's bounding box. And each success location must be navigable and the object must be viewable from that location in an oracle sense. That is, if you were to look for the object standing in that viewpoint, in that location, you should be able to see the object. The agent is then deemed successful if it reaches within 0.1 meters of any of these green points and then stops. We also use the success weighted by path length metric, which downweights each success based on how long the agent took to reach the goal. If it strays too far away from the shortest path, then it is penalized for it. This time, we also introduce the image nav task. Unlike the traditional image nav task, which samples a random image in the 3D scene from the agent's own viewpoint, we introduce the instance image nav task, where we sample images of objects, and these images are sampled from the viewpoint of a human taking the picture of the object, making this a bit more realistic. Concretely, here is the task. You have an agent, again in a novel environment. It is now given a goal image of an object, in this case a chair, to navigate to. It must navigate to this object using the RGB plus depth sensors and the GPS plus compass sensor for localization. It must then stop within a 1 meter radius of the goal object from where it is visible in order to be successful. We also introduce a few new changes to the task. The first one is we changed the embodiment from last year's embodiment, where we used a locobot that has, excuse me. Okay, yeah. So it has a radius of 0.818 meters and a height of 0.88 meters.
It has 6 actions for move forward, turn left, turn right, look up, look down, and stop. And the camera that we modeled was in Azure Connect with a horizontal field of view of 79 degrees. But this time around, we changed the embodiment to the Hello Robot stretch embodiment. The motivation is that its height matches what a human, the height of a human, which is around 1.4 meters. And we introduced 3 different kind of actions this time. Instead of the discrete control from last year's embodiment, we have velocity control, where an agent has to emit continuous actions for the robot to navigate. This is much closer to the real world setting as opposed to the simulated setting. But we also provide 2 different wrappers around a waypoint control, which can be converted to a velocity control, and a discrete waypoint control, which can again be converted to the velocity control. So participants are free to use any of these 3 kinds of actions. But ultimately, the robot itself will receive direct velocity commands, which it uses to navigate. The camera that we used was modeled based on the RealSense camera from the stretched robot, and its horizontal field of view is only 42 degrees as opposed to 79 degrees from last year's embodiment, making this a much more challenging task. This year's challenge was held in the HM3D semantics dataset. This is the largest ever dataset of semantically annotated 3D indoor spaces. Concretely, the object nav task in the HM3D sim dataset is organized in 145 train, 36 val, and 35 test scenes. Overall, there are 6 goal categories of bed, chair, plant, sofa, toilet, and TV monitor. Here is the distribution of the number of object instances per category that may be used as goals in the training dataset. You can see that there is a good distribution of objects over the different datasets, but we do have a lot of chairs. Here's a similar distribution for the instance nav, the instance image nav task. Again, we use the same scenes, we use the same 6 goal object categories, but here the agent must navigate to an instance of the object as opposed to any instance of the object. The number of goal instances here are again well distributed over the objects, but similar to the previous case, we again have too many chairs. Here are the statistics of the challenge participation this year. We had 17 teams participating with 118 submissions to all the phases. Overall, we had 4 teams submit to the final challenge phase of the 2 tasks. Let us announce the winner of the image nav task. It is the team is the LQ team, which obtained a success of 6%. This team has made great progress over the baselines, but clearly you can see there's a lot more to go, and we hope teams continue to improve and participate in this task. The winner of the Object Nav Challenge is the Skill Fusion team, and they obtained a good success rate of 53%, making significant progress over the baseline. But again, this task is not solved, and there's plenty more to do. But what is next? So in the next challenge, we are hoping to introduce open vocabulary mobile manipulation from Home Robot. This challenge will be organized in NeurIPS 2023. The key highlights of this challenge are object manipulation as opposed to just navigation, open vocabulary of objects as opposed to just 6 categories of objects, and we have a real-world testing components where the top entries will be tested on a robot to judge the final winner. We encourage you all to participate if you're interested. Please reach out to any of us if you need more information. And thank you to all the organizers who helped, make this possible. There's a lot of work to do. And we also thank Evale for conducting our evaluations, and we thank our sponsors for helping fund this whole challenge. So thank you so much. And looking forward to next year's challenge. Thank you.
Thank you, Habitat. Okay, thanks to all the speakers and challenge organizers. especially for being on such great time despite all the changeovers and 5 different presentations. Now is the time for the panel, which will go to 10:30. So I'd like to invite back to the stage all of the challenge organizers for the navigation challenges. So anybody who's in the audience, feel free to come up to ask a question. If you are in the online audience, then I would encourage you to go to the Embodied AI homepage and submit questions via the Slack channel that we have there. Awesome. So maybe I'll kick it off with something maybe slightly more provoking, perhaps intentionally. So I get the sense talking to some people and looking at submissions that the excitement for navigation, or at least the is a bit less than it has been in prior years. And a lot of the tech, we're getting like 50% success. Maybe we're not at 100, but it's sort of feeling like it's starting to plateau. And so the slightly hot question would be, is navigation dead? Should we all be moving over to manipulation? What do you think is next?
So I wouldn't call navigation dead in that there's obviously still room for improvement. The fact that we are only at the 40–50% for what are, for some environments, fairly small standardized clean environments probably says a lot. But at the same time, I do think that for embodied agents and as a field, it's probably more interesting to start looking a bit more at how we actively interact with the environment rather than just how do we explore the environment, as that's it's been pretty well covered ground now. So it might be time to start moving a bit more into how we interact with the world. But what do others think?
Yeah, so I wouldn't say that navigation is dead, definitely not. But I do think, the benchmarks are getting saturated to a certain degree, and that means that we need to increase the difficulty of the tasks. And so in navigation, this means we could do 2 things. One is to move towards more longer term navigation in more dynamic environments with objects and people moving around. We still don't have very good simulators for that. So that is going to be a challenge. The other way to improve is to obviously introduce object manipulation, which a lot of challenges are doing. We are navigating to eventually do something, and so we should start doing that now.
I'm going to add on that. It's certainly not dead. We can see in our multi-object navigation challenge, because we have increased the complexity of the task, and we are slowly moving towards a more longer horizon task. So I believe there's a lot of room for improvement there.
So yeah, I guess along those lines, so if it's not dead, what are, you mentioned long horizon tasks. It seems like a lot of the failures that at least I've been seeing in navigation has been about recognition. And so it kind of motivates moving to sort of maybe open type navigation type settings. But yeah, what would you all see as sort of the major challenges for navigation and getting us, why aren't we at 100%?
Yeah, for multi-object navigation, we are trying to move towards a more open set of objects so that the agent can navigate to any object that it has not seen in the past in training. And we actually advocate using a modular approach like in our baseline so that we can leverage all the different kinds of approaches for other tasks here. So yeah, longer horizon, open objects. Yeah.
Yeah, I would add on that long tail of object reference is one of the challenges that is faced implicitly in vision and language navigation, where natural language instructions are free form and can describe paths through the environment in any manner. And we see that on that benchmark, there is still a significant amount of headroom, and we have yet to see successful sim to real transfers in this domain. So I think in the VLN space, there is still much to be done.
At least for the audiovisual navigation challenge, I think there's a very big sim to real gap for audio especially. So I think the main thing to check there is whatever policies these participants are proposing, whether they'll work at all in the real world. Because I think for at least for vision, it's kind of, there is some guarantee to a certain extent that you can transfer, but for audio, there's no guarantee and nobody has really done it. So I think that's the next big step that we should go for, at least for AVNav.
I'll just add that for robotic vision scene understanding, we found that the scene change detection challenge really screwed up people when it came to how good their maps were and how to align their maps. And part of that comes down to the issue of daytime versus nighttime. So we don't really have, perhaps the robustness in our perception systems that we would like, or at least we don't see them being applied to these embodied challenges. Even if they are out there, they're not being applied to a physical robotic system.
Just one last thing I wanted to add. There is also a real to sim gap at this point where perception models that are designed for the real world don't operate well in the simulators. And I think that is masking some of the progress we've made. I think if you use a segmentation model in the real world, it's more likely going to work. But in the simulators, there might be reconstruction artifacts which prevents the object from being detected and it fails. So yeah, I think there's still that gap to consider.
It's an interesting point that I think usually we think of simulators as being super clean and nice, and it actually might be the case that the models we've trained are doing worse in simulation than within the real world. So we'll take a question from the audience.
Should we ask a question on the, is it working?
I think it should be working, yeah.
Okay. So should we ask a question on the same topic, or can we change?
You can change if you'd like.
Oh, okay. Yeah. So a question for sound spaces people. So I arrived in the middle of presentation, so I might miss some part of it. But you mentioned like transferring 1 terabyte of data as a barrier for participation. Is it the data used for simulation, or do you mean like offline data for?
Yeah, it's actually for rendering the room impulse responses, which kind of help you render the spatial audio. So the room impulses, they're like stored on the disk. And for like replica, it's 1 terabyte. For Matterport 3D, it's like 4 or 5 terabytes, which is kind of a barrier to a lot of people.
Yeah. I think we should reduce these types of barriers, so like more people participate, because like 1 terabyte transferring 1 terabyte of data like might not be possible for a large number of people.
There is a solution for that, like the next version of the simulator, but it's a bit slower than loading like RIRs that are stored on disk. So we are planning to include that in the next version of the challenge.
Okay, thanks.
Hi, I have 2 questions. And first one is about RVSU challenge. And it can be the question from the ignorance, but when I think about this problem, this problem can be easily dissolved into localization and object detection problem. And actually, the first winner solved this problem in this way. But what would be the advanced difficulties or additional difficulties when we think about the RVSU challenge more than combining the localization problem and the object detection problem?
So you're asking how could we make the challenge more difficult, or what's the next?
What's the difficulty of the RVSU challenge? It is more than combining the object detection and localization problem.
Yeah, we found that part of it is exploration policy, because RVSU challenge itself enables the robot to go to all the places, but you have to be very precise in getting through some of the doors, for instance. So it's not an environment that has been made explicitly for the robot. So trying to navigate and trying to get to all the places to see all the objects is in itself a bit of a challenge. Another thing that we have seen in past challenges is just the nighttime environments that people they're not very well lit. People have issues trying to find those objects, and particularly when you're doing scene change detection, if you miss an object and you say, oh wait, that thing's gone, it's just that it's dark and you can't see it. Some people have done some things with their image manipulation to be able to get over that, but it's still a big challenge. And like half of the environments are the same environments but at nighttime, so
okay,
makes it tricky.
That's a very interesting challenge. And also I have a question about the habitat challenge, and I observed that there are huge discrepancy between the object net performance and the image net performance. But I think that image net performance is just changing the object category into image. But why would you think that there are huge discrepancy between the performances?
So I think there are two main challenges here. One is, yes, you're converting to an image, and the image, like the model has to recognize the object correctly in the image and navigate to it. That is a challenge by itself. But the other thing is, you're navigating to one instance of the object as opposed to any instance of the object. So you might be given an image of a chair here and you have to navigate to it. But on the other hand, in the object nav challenge, you can go to any chair and you're successful. So these
Okay,
add
that's
difficulty.
the point. Okay, thank you.
Yeah, I think maybe something that's kind of unintuitive for many people that sort of is going off that question is why is navigation not so like super easy? Why can't I just take exploration model, slap on top of an object detector and get high performance? Any thoughts there?
I would say you can get high performance. Yeah. It's just that in the simulator, I would say that the detectors don't work that well. So it does mask the performance a little bit. But if you go to the real world, that is a very strong baseline. Yeah.
There's also questions of efficiency. If you have some sort of exploration policy, something that simply maximizes coverage so that you can find everything in the scene might not be the most efficient way if you are trying to find a toilet, for instance, where priors can give you information about where that toilet might be located. Infusing exploration policies with such priors is still an interesting and open direction to move in.
And all the tasks have some kind of maximum step limit. So the exploration policy needs to be very efficient.
Great. Next one from the audience.
Thanks for your good presentation. I have a small but open question. Yeah. Recently, large language model like OPT, GPT, and Llama become more and more popular, and it seems some works like PME begin to introduce the ME into this task. So what's an advantage of introduce the large language model into embodied AI, especially interested in vision text navigation task? Thank you.
Yeah, I think that's a great point, that introducing large language models can give you a significant amount of knowledge without having to gain that knowledge through interactive experience. So in the vision and language navigation space, you need to be able to ground language in the environment that you see. So that would be a vision and language grounding problem. Trying to learn that while learning how to act in an environment is an incredibly challenging task. And if you can, use internet data to essentially bootstrap or leverage that knowledge, that seems to be a useful direction to move in.
Thank you for sharing your challenges. And I have a general question that I'm interested in sim-to-real transfer, and most of your works use GPS plus compact sensor, and some of your works are tested in the real world. But we know that if you use mobile robots in the real world, the localization errors are accumulated. So how do you deal with this problem? Personally, when I try to demonstrate my image navigation policy trained in the simulator in the real world in my house, the localization errors were a big problem that they get stuck on the wall. How do you solve this?
So the area of how to self-localize in that is its own field, which is separate to just the world of these embodied AI challenges. When working with sim to real, I would always recommend trying to make sure that you add in that noise to your simulator, so you are closer to what you're trying, particularly if you're trying to do an RL policy that's trying to learn how do I adapt to things. If your underlying system is assuming something that is ground truth, then that assumption will go away as soon as you go to your real robot, and your navigation system, I would understand, would fail. So in terms of trying to help with that sim to real transfer, I would suggest adding in as much noise that also accumulates with your navigation. But I would also make note that that will be different to the exact errors that you will get in the real world. So there will be that gap, and you need to see if you can learn a policy that's able to accommodate for that with its observations.
Yeah, thanks. I also tried adding the noise when training, but I thought that the challenges still use pose sensors and pose information, but shouldn't we make the research direction head to designing some policies that do not use host information. For example, we can construct a map using in the image embedding space instead of on the geometric space.
Yeah, I think that's definitely an interesting direction, and it's quite open at this point. I mean, there are some good visual odometry systems that have come up for navigation, but yeah, they are tested in the short-term navigation setting with only 500 steps, for example. But on the other hand, I think I recently tested policies on a robot, and I think SLAM systems are great right now, and I didn't face too many localization issues. Maybe there are 1 or 2 steps where things are off, but then it recovers from that. So yeah, I think if you do use SLAM on the real robot, and you can somewhat safely assume ground truth pose in the simulator. Yeah, like of course there are caveats to it, but in most cases it works well.
Okay, thank you.
Hey folks, so you folks are the closest to code and day-to-day experimentation. What are the pain points that you face in your day-to-day experimentation? Like why isn't this room full? Why aren't there 20 teams in each of your challenges? Like what problems do you face every day? I mean, there's the usual compute, but other than that.
So with regards to using and implementing, utilizing these tool sets, with RSU, we did a lot of focusing on trying to make the process of installation getting running as easy as possible. Some of the pain points do just come down to hardware, GPU requirements for particularly our largest environment, choose things up a bit and runs into issues. But I think for a lot of the teams that contacted us saying we're interested in participating, asking for help and all that sort of stuff, a lot of the pain point was just time and going, do we have the time to work on this challenge outside of what their main research focus was, or going, oh, this is related, but it's not closely enough related to my research to be exactly what I need. And they just ended up not having the time for it. But yeah, technical wise, there are always issues of like compute, how long it takes you to run your simulation, and of course the bugs that come in through the issues all the time. So yeah, I'm gonna go.
For the image nav task put on by Habitat, one of the major considerations there is if you want to develop a learning-based policy, the turnaround time on experimentation is extremely long because of the sample inefficiency of baseline methods. And if teams out there want to start by training our baseline method, good luck. You need to train for billions of steps of experience in order for you to be able to fit the training set. Being able to decrease that turnaround time and reach generalization faster so that you can see generalization to new scenes and new objects is something that is important for us to develop to lower that barrier.
So I'll again, drawing on that point, I will again advocate for modular approach so that we can leverage other methods which were trained for other tasks and maybe fine tune on our side. But related to the topic on day-to-day coding, I would say we need to gain more insight into what is exactly happening, why things are going wrong. So I would ask everyone to like dig deeper and maybe analyze what is going wrong. And this is to say on top of like we need faster simulator and things like that.
This is drawing from my own experience as a previous participant. I do think it's great that we can evaluate agents on Docker. I think that's a game changer, but it's also quite painful to do that. Like I had to spend several weeks. This was back in 2020. I'm sure it's changed now, but I had to spend several weeks debugging CUDA errors just to run the baseline agent. So yeah, I think that's definitely a pain point.
Yeah, for us it was more like installation of like Habitat. I think like the docs are still not like up to date, I guess, and like we got several emails, so we had like 15 people reaching out and then like just one person submitted in the end. And other than that, like the storage is also an issue, which, like I said, we want to move on to the second version of sound spaces. And I think like somebody already mentioned that like this whole paradigm of RL training as like the way to like train these agents. This is also, I think like kind of a bottleneck to a certain extent, because like when you give somebody a baseline, they try to build on top of that. So instead, probably like we could provide like multiple baselines, and some of them could be non-RL, and maybe that will encourage people to build on top of those and get better results.
Thank you.
Hey, folks. So looking over some of the submissions and other techniques in this space, what I see is embodied AI as a consumer of perception, right? It's a one-way street where we're using perception systems that exist to just tack on a bunch of things to do embodied AI. I don't think that's the vision most of us started here with, right? The idea that embodied interaction will give us something in vision that we didn't have already is maybe one of the pipe dreams. And I wonder if you think the challenges are set up in ways to encourage this to be more two-way streets between perception and embodied navigation or embodied mapping, or if there's something that the community is just missing there that we just haven't supported yet. How do we go from consumers of perception to producers of perception systems?
Yeah, this is a thing that got discussed a lot during the creation of RVSU. The problem came for us anyway in trying to figure out how to give the incentives for being able to do things in a clever, active way. So with the passive mode, the idea was, yeah, you could just be a passive consumer, but you're going to take a route that's going to take you all over the place, and it's not going to get you where you need to go efficiently. And then with the active versions, you'd have more control of that. But as you saw, what most people did was go, okay, here's a basic policy, let's use that and then be passive consumers. So I think there's partly an issue in the incentives going into place. So how we evaluate the systems. I haven't got great ideas for that at present as to the best way, because you want to be able to incentivize a thing without discouraging people from taking inventive ideas around a thing. I was talking to a colleague about this, and they were saying, yeah, you could add in this extra evaluation metric or this extra constraint, but you've limited me what I can do. So it's a tough tightrope, but I think in trying to figure out better evaluation techniques, I think the ones that incentivize, the clever use of active movement with the perception, I think that's probably a way to go.
Thank you. Just to chime in before others reply, I think active perception is one side of this coin.
Mhm.
The other is, when do our vision models get better because we've interacted, right? When do we contribute to perception by actually doing these embodied tasks? Because surely there should be something there.
Yeah.
Yeah, on that question, it's great because when I'm testing things on a robot, I see some obvious flaws of segmentation models, for example, that are trained on these fixed viewpoints, and you take 4 different viewpoints of the object and only in one of them the object is detected. And I think simulators are a great way to solve this. But I don't know, I think there is this visual domain gap that continues to exist, which maybe it's a turnoff for the core vision community. I don't see a lot of them working in simulators, even though it's a great platform for active learning and learning better perception systems. So yeah, like if we can attract more of the vision community to these simulators and maybe improve the rendering quality to some degree. I don't know if that's a reconstruction problem right now, because we have really good reconstruction system. It might be more about, I don't know, using some nerf-like system to augment the current reconstructions to make them look more realistic. But yeah, there's plenty to do.
There's a visual diversity problem in some of these settings as well, right? It's hard to train massive perception systems on 30 environments or 100 environments.
Yeah, I mean, we do have 1,000 environments right now in HM3D. Of course, that's, but yeah, like the advantage also is you can get like diverse viewpoints of the same thing, which does not exist in the standard vision literature. So
thank you.
Okay, thanks for the excellent presentation, and especially for the realistic simulator and exciting task settings. I just have a small question for the audio-based navigation task. Yeah, I just want to know, besides the semantic recognition and the point target direction, what else can we gain from the provided audio? I mean, what how can we better take advantage of directly from the provided audio? What else can we do? Can we gain from it? How can we take advantage of it?
Yeah, that's a good question. So like, because the audio that we have is like spatial in nature, right? So we can learn a lot about the geometry and the materials of the environment as well. So for example, like currently most of the mapping systems are like visual in nature, but if you add audio to that, you could make the model like more efficient, like map more quickly. And other than that, like you can also kind of try to figure out like, so like if you want to like listen to a particular sound of interest in the environment, while there is like a lot of other kinds of sounds that are playing, like background noise and so on. So you by like navigating towards a certain sound, you can try and like extract that particular sound better. So it like you can kind of build both like a geometric material map and also like an acoustic map of the environment. Yeah.
Is that the advantage from the audio or just advantage from the point goal? Similar to the point goal navigation.
No, so like at least for the geometric map, like the spatial audio, it carries a lot of information about the geometry because your sound will like bounce off walls and stuff. So like tall objects, large objects. So it'll give you a very good sense of geometry, even if you haven't reached that location and you can't see that location. So that can really make the model and the mapping more efficient.
Sure, thanks.
Yeah.
Okay, we have time for one very short question. So
yeah, okay. Thank you so much.
Yeah.
Quite good workshop. Yeah, I have one question. Yes, nowadays, big models is quite successful in this domain. So my question is that for ChatGPT or SAM segment everything. So do you have any comment about how to use these big models in this domain? Yeah, for the robots.
So in multi-object navigation task, the baseline that we used is modular in nature. So there's the object detector that we used a pre-trained model called Robotic. It was trained on a huge image and text space. So we are already doing that in a modular way. So I think that's the way to go.
Sorry, could I have another question? Because these big models are quite big. For example, sometimes there might be several hundred of gigabytes. So how to adapt them to the robots?
So you can take the pre-trained model and use as is. You can use the off-the-shelf model as is in your data set, or you can like fine-tune it. But yeah, so the model has already been trained on a large data set, right? You don't need to train it again on the large data set. You can fine-tune certain features on your data set.
Okay, thank you.
Thank you so much to the panel. Let's thank the speakers. Okay, next up, we have our first invited speaker, Saurabh Gupta. They're an assistant professor in the ECE department at UIUC and received their PhD from Berkeley in 2018 and spent a year as a research scientist at FAIR. His research interests span computer vision, robotics, and interacting with the physical world around them. He has won multiple prestigious awards, as well as winning many challenges at leading computer vision conferences. Thank you.
All right. Thank you. Thank you for that kind introduction, and thanks a lot to everyone for coming. Okay, so today I'd like to talk about robot learning by understanding egocentric videos. And this will hopefully touch upon some of the questions that came up during the previous panel discussion on scaling up things and so forth. So let's get started. Okay, so if we look at learning in computer vision and NLP, we are very used to learning on large-scale data sets, right? So I guess this is an older picture. We no longer train on ImageNet, but on things like Lion. which are like billions of images, right? If you look at NLP, again, the same story. We are training models not on small data, not on manually collected data, but on very large scale data sets that exist out in the wild, right? In contrast, if you look at policy learning in robotics, or embodied AI, however you want to call it, we are in some sense limited to small scale learning, right? So learning that happens in the lab or in simulators, and I'll talk about simulators in a bit too. But this is not the flavor of learning that I am used to when I'm a computer vision practitioner or a natural language practitioner. And the question I want us all to think about is how can we scale up robot learning, right? And that's kind of what I want all of us to think about. Now, to scale up learning in robotics, there are many answers that have been tried out. You can do self-supervision that relaxes the need for getting supervision. So you can scale things up if you can just collect the data. You can do parallel data collection through arm farms. You can do robots in homes. You can simplify data collection setup so that more people can go out and collect data. You can also do sim to real, and that has also proven quite successful. Now, I will not talk about any of these. What I'm going to talk about today is how can we scale up robot learning through observation of other agents solving tasks, right? So that's what I'm going to focus on today. Why do I want to do that? We do it as adults. I'm trying to learn a new task. I might, rather than entirely figuring out how I can do it by trial and error, I might actually watch a YouTube video of someone else doing it and learn something from there and try to do it myself. Importantly and crucially, it is actually a very crucial part of child development. You can look at this wonderful paper from Andrew Mintzoff and Alison Gopnik on the role that imitation learning plays on early on in childhood, to the extent it's evident in a few hours or a few days old children, right? So it's actually a very crucial part of human learning as well. Okay, so in particular, when I say videos, in this talk, I'm going to focus mostly on egocentric videos, though I'm not in principle bound by egocentric videos. Any kind of videos is fine. And for navigation-like tasks, it could be videos of this form, where people are walking around in indoor environments and so forth. And there is apparently a reason why people do this, because people want to put up their apartment online so that they can rent it out and such. So these kind of videos exist naturally. But for manipulation tasks, it could be like, egocentric videos of people wearing wearable sensors, collecting data, going about their daily lives, right? So these are the kind of videos that I'm interested in. Now, let's take a step back and let's first try to understand why would use of such videos be useful for learning, and what is there in this, right? So if you look at policy learning from interaction, and a lot of this has been said in the previous discussion, there are many challenges, be it simulation, be it real world. It is challenging to specify reward functions, right? So that's a design problem that one has to solve, and that's not so easy, particularly in the real world. There is a second problem, which is there's impractically large sample complexity, right? You need to train, as was mentioned, to train some of these baseline agents, you have to train for a very, very large amount of time. Crucially, learning signal is all derived from interaction and your own interaction. You have to make you have to make each mistake yourself before you can learn from it, right? That suggests a limitation. And lastly, there is poor generalization because of the scale of data that we're able to exploit for learning. In real world environments, in real world capture, the problem is, how many robots can you run in parallel? In simulation, the question ends up being how many environments do you have that you can train on, what is the distribution of these environments coming from, and so forth. Furthermore, if you train purely in simulation, you also have to worry about sim to real transfer and so forth, where you might also lose a little bit of performance. And some people mentioned this, that assumptions you're making in simulation might not hold true in the real world, and that causes problems. And I think this is in many ways in which egocentric videos can actually aid. There is large diversity. You have, it's much easier to scale up video collection than creation of simulators and such. You are not required to solve the problem ab initio. You have, the solution is in front of you. You need to figure out how to copy it in some ways, right? So it helps a lot with the exploration problem. And even if you're interested in tasks which are not directly being shown in the video that you want to, shown in the video, it still depicts what the world is like and how it works. And that might give you some common sense understanding about about things that you can use for making inferences and such. Now, this is all good. This is promising, reasons why one would like to do this, but it comes with its own challenges, right? So some challenges being videos don't come with action labels. The goals and the intents of people and what they're doing are not known ahead of time. Depicted trajectories may actually be suboptimal. That poses issues with learning. There is crucially embodiment gap. What humans can do in their environments may be different from what the capabilities of current robots are in terms of what sensing they have, what actuations they have, and so forth. And finally, they only showcase positive data, which, if you know reinforcement learning, causes lots of issues, right? So we have been thinking about this problem for quite some time, and here is how I'm thinking about this right now, which is that rather than trying to, and we're taking inspiration from natural language processing, where you can actually transfer, if you're trying to translate source text into target text, you can actually either do direct translation, which is you want to go directly from source text to target text, but that requires a lot of data and so forth. But you can actually consider not doing transfer at the final text level, but you can consider parsing the text into a syntactic structure, doing the transfer over there, and then rendering it back in the target language. And transformers do it in this direct translation way because there's lots and lots of paired data, but you can imagine some sort of hierarchical reasoning happening inside a transformer as well. Now, we are saying that we can actually do the same kind of reasoning when we are trying to transfer from observations of humans to producing robot actions, right? Rather than directly translating human actions to robot actions, we can consider the entire control hierarchy where we think about the decision-making process. Yes, there were muscle tensions at the end of the day, but there were some macro actions, there were some skills, there were some sub-goals, there were some goals, and then there's finally the world that this person is living in. And all of that had a role to play in producing the final actions the person produced. And we can actually think of transferring at different levels of abstraction in this hierarchy, and that could be useful, right? And depending on the amount of gap that you have in embodiment, in the goals that you want, or what you can actually observe in videos, there could be information transfer that can happen at different layers of abstraction. And in particular, we have looked at lots of these in the past. So you can actually learn subroutines and affordances, which is, you have, right, and you can learn dense about functions, task definitions, common sense about objects and scenes, and so forth. Okay, so this is the big picture. What I'm going to show you today is some examples of how we can use videos for learning. And I'll pick a couple of things. I'll talk about how we can actually use videos to learn about how we can interact with objects. And if time permits, I'll talk about how we can actually use videos to learn common sense about scenes and get at some of the navigation questions that have been of interest in the last panel discussion. Okay, good. So let's take it from here. So the first piece I'd like to talk about was a paper at CVPR last year, where we were interested in this problem of interactive object understanding. And we were deriving signal for this through observation of humans in egocentric videos. So what is this interactive object understanding problem? Let's say, you have objects around yourself. What you're interested in is answering questions of the form that in a scene, what are sites that you can interact with? In this case, the cupboard handle is something that you can interact with. How do you interact with those sites, right? Using some sort of a particular kind of a hand clasp. And what happens when you do, right? The cupboard undergoes a state change, right? So these are some basic things that we will need to understand about objects before we can start interacting with them. And you can imagine that these are all useful if you're trying to learn a policy for interacting with them. It serves as a prior for where to interact. It could be used to learn reward functions and such, right? So I'll show you two examples of, I'll try to tease out these kind of understandings from egocentric videos. Specifically, I'm going to learn state-sensitive features, which is, capturing this notion that objects undergo state transitions. So if you can learn features which can distinguish objects before an action and after an action, I can start, using it as a dense reward function. And I'll try to actually show you experiments with that later on. And for the first two questions, I'll talk about object affordance prediction, which is, can we predict where all can you interact in the scene and with what kind of a hand clasp? Okay. And the key observation in this work is that that we will learn through observation of human hands interacting with the world, right? So human hands in egocentric videos are informative. So consider this video sequence that you already saw. If you in the wild egocentric videos focus on natural ways in which humans interact with objects. So it's not, it's not lab settings and such. There are nice things that happen, right? Like not everything in the video is worth paying attention to. You can actually focus your attention to what hands are doing, because they are essentially the agents that are inducing change in the world, right? So attending to hands localizes and stabilizes objects of interest. Hands show where all you can actually interact, which is what we were interested in. And analyzing the hand can reveal information about the object, their state, and how to interact with them. Right. So how do we do this? So we essentially prepare egocentric videos for learning. We have this video. We use state-of-the-art hand and object of interaction detectors to prepare tracks of, okay, here are the objects of interaction. Here are the hands that are being used to actually interact with these objects. You can infer their contact state. You can actually also characterize the motion of the hand around the object. In this case, it's just 2D motion of the bounding box. And you can actually also infer the grasp. What kind of a grasp is the hand exhibiting? And in this case, you could do these things by annotation. We are actually running state-of-the-art models for each of these things in order to produce this data for learning. So in that sense, the results I'm going to present are shelf supervised. We are using off-the-shelf models for deriving supervision and such, right? Okay, so let's see how we can use this kind of data for learning state-sensitive features. And the basic idea over here is, because we know we have a collection of objects that that are being interacted with, very likely they're undergoing some sort of a state change. And we can use this to learn about features which are sensitive to states. And the way we do this is by leveraging temporal consistency. You have object tracks which have lots of state changes. You can actually do some sort of temporal sim-clear. That's what we do. You say that frames which are close by in time are very likely to be in same state, and I'm going to encourage those embeddings to be close to one another, and far away from embeddings for the same object, but much further out in time. And presumably this will have undergone some sort of object state change. So this is kind of the first supervision cue you can extract from over here. You can extract another supervision cue, which is, how does the hand interact with this object, right? And we can actually say that you can learn a similar embedding for the hand, and you can say that the object should be similar to the hand at the current time, and it should be far away from other hands. And the intuition over here is that this hand model will learn some sort of a space for hands. And what we are saying is that objects are likely to be in a similar state if the hand that is interacting with them is in a similar state. So it can pull on things of that form. So this is kind of the overall self-supervised learning formulation. And we collected some data sets to actually verify this, that we have a data set where we have labeled objects according to some state labels. That, okay, this is the state of an object. And in this case, it was like, whether an onion is peeled or cut or chopped, you can try to distinguish between those. And what we saw was this way of extracting supervision actually improves performance over other ways of extracting supervision from such kind of data, or not using this kind of data for using like ImageNet pre-trained models, right? And this is, you see improvements over these things, but more interestingly, you see larger improvements when you look at novel objects, which is what is interesting, going forward, right? So you get a much larger improvement in that kind of setting. Okay, so that was a quick treatment of how you can learn state-sensitive features. Next, what I'm going to talk about is how can you learn affordances? And we are doing this via context prediction. In some sense, the answer is already there. You're seeing someone, you touch different parts of the scene, you know what kind of a hand pose they're using. You just need to figure out a way of kind of teasing this out and training a model. And, there's a little bit of a detail, which is that the answer is kind of in the data. So you hide the answer and try to predict it from the remaining data. And that's what we do, right? So as I said, we have this kind of data where we have objects of interaction. We know where the hand is. What we are going to do is we are going to sample a patch around this particular hand. I'm going to mask it out because I don't want to reveal the answer. And I'm going to pass it into a model which can predict the region of interaction, that, okay, where was the hand inside this patch, and what was the hand grasp, right? So this is, classic, there's like this kind of idea has been around for self-supervision for a while, and we're just applying it over here. And crucially, the supervision in this case can be derived from the fact that you know where the hand was, and you can you know what the hand grasp it was exhibiting. So this kind of a model, by looking at the surrounding context, can reason about, okay, where are regions of interaction, right? Okay, so you can do this. Again, we collected some data set to actually verify this, where the first Mohit, who was leading this work, sat down and watched lots of this egocentric video and labeled what are objects that can be interacted with, and we evaluated our models on this, and across these different images, you can actually start picking up on affordances, right? Like that you open the door by pulling on a knob, so that knob is a region of interaction. You see edges of plates, you see edges of these drawer handles being highlighted, and so forth. Okay, you can actually also and there's some quantitative measures. I won't quite go into the details over here. Yeah, but the second task you can actually also do here is you can actually start inferring what is the grasp that you can use to interact with an object. And again, the same methodology applies over here. And we have some evaluations where we see that doing this actually improves performance over not and such, right? Okay, so so this is kind of some flavor of how we can start using video data for learning about objects and about how the world works for presumably some sort of manipulation tasks, right? Okay. Now I'd like to build upon this in a way, and we'll see, right? So what hopefully I've convinced you is that hands were useful. You can actually use them to supervise different kind of models, but in some sense they are also a nuisance, right? So I discussed learning state sensitive features. And now you can ask me that, okay, you have learned state sensitive features, but show me that they're useful for a robotic task. Can you actually use it to learn a reward function, for example, to do a task and train against that, right? And this immediately presents a problem, which is that there is domain gap in some ways between these egocentric videos that you're using to train and the kind of images you will have access to when you're testing these models, right? So on the top, you are seeing this image, from these from this Epic Kitchen dataset, and on the bottom you have like a robotic gripper or like a proxy for a robotic gripper, and there is domain gap of some form, right? So yes, hands provides signal where to touch and how to get there and so forth, but there's also a nuisance, which is you have to deal with this visual domain gap. The second is, I already showed you about affordances, how we can extract affordances from here. But again, there we had like to deal with this nuisance that these hands were there, we blacked them, we deleted those patches, and then we were trying to make predictions for pixels that we're not seeing, and that's kind of not a nice thing. Wouldn't it be nice if we could factor out these representations into an agent representation and an environment representation? And that's exactly what I'm going to tell you next, where you can actually remove the hands. And for learning state sensitive features, you can remove the hands and replace it with some sort of an agent agnostic representation of the agent, which now can be the same across whether that's a human interacting with the environment or a robotic end effector, right? So you replace it with the green dots that you can see. We can actually do the same thing for this affordance prediction, where we can actually paint out the image, and now you can solve this prediction task. Okay, what was the hand like given this complete image, right? Okay, and so this is some work that we did in this new paper that's on that you can look at on arXiv, where we are explicitly trying to factor egocentric videos into agent and environment representations. And if you're interested in learning more, I'll give you a teaser over here. But you can find Aditya at the poster session for this workshop, and you can ask him all the hard questions. Okay, so what is our agent environment factor representation? We have video frames from an egocentric video. Our representation consists of, it's a factorization in the pixel space, because now we can actually do that quite well with the latest developments in generative models. So this factorization is in the pixel space. So we have I agent, this is the agent image, and this is the environment image where you have what is the environment like. And the way we build this representation is you take in the image, you segment out the agent, right? And we are using again state-of-the-art models in analyzing hands. So you can segment out the hand. And then you can train a video and painting diffusion model, which I'm going to tell you more about, which takes in the current image, the agent, what you want to mask out, but also previous context frames, because that may have shown you what the scene was without the agent, and you can steal information from there. And it produces this environment representation, right? So that's kind of what we are doing over here. And if once you have this representation, this factorization, you can actually do lots of different things, right? So you can actually learn reward functions, and I'll show you how you can do it. So you can learn, the nuisance was that the hands are inducing a domain gap, so you can map it using a function G into a domain invariant form. And now you can jointly, you can learn something on top, and that will work out. You can actually also do affordances, which is exactly what I showed in the previous paper, where you can take in the environment representation and try to predict the agent representation, or whatever aspect of it is what is of interest to you. Or you can actually also do visual perception on this. You can now, if you're interested in object detection in egocentric data, you will see that it doesn't always work. Now you have one additional image which provides a better view of the objects in there, and you can also run your detector on that and combine the output in some way and such. Right? Okay. So at the heart of this is this video and painting diffusion model, which leverages priors on how objects are through a diffusion model that has been trained on a very large amount of data. And second, it leverages past information that is available in the video in order to steal from it, right? So we are building on top of latent diffusion models. You have this input image that comes in. This is what it looks like. You tokenize it and whatnot, and then you have some sort of unit which processes all of this with attention layers. What we are doing is we have extended this model to absorb additional frames as input, and everything is copied except information is intermixed at this attention layer. So you can actually copy, so you're not introducing any new parameters, and you can still use all the old parameters and still start leveraging information from other frames. And this has been done in other kind of work which extends latent diffusion models, but that's what we are doing here for this specific task. You combine everything and you predict the noise, and you do whatever, 200 rounds of denoising and whatnot, right? So this is what the results look like, and I was quite impressed with these results when I saw them. So this is, the original image along with some previous frames that are available for context, which I'm not showing. This is what you do single image latent diffusion. So you just run latent diffusion models as is, actually fine-tuned on this specific data, but it's a single frame model. That doesn't do as well. You can actually use the state-of-the-art video and painting model from previous CVPR. That also doesn't work as well. Here is our method, which is actually able to outperform both of these things. In particular, it can actually effectively leverage past frames to reveal these oranges that were behind the hand. And it can actually leverage, while also leveraging priors trained on large-scale data sets, to complete this handle and so forth. Right? Here are some visualizations. So this is, Lukma, no hands. Things are happening in the scene without the agent. So this is frame by frame results. There's no temporal smoothing aside from the fact that there's a temporal window that you look at to make predictions, but there's no explicit temporal smoothing. So this is there's one example. Here is another example. The drawer opens by itself. There's this floating cutlery that you can put in and so forth. Here's some other examples of objects are moving around and such, right? And you can actually use the same model in painting out robotic ending effectors, right? So here is this model, which is this proxy robotic end effector, and you can use it to open the fridge, and it can paint this out too. Now, in terms of why we were doing this, we can actually use this factored representation to learn reward functions. And what you find is that these reward functions correlate better with ground truth progress on the robotic side, and that is good. So that's a win. You can actually do affordance prediction, the works that I showed you, and it actually leads to improvements in performance over there as well. You can actually also do object detection, where it improves the average recall of a detector quite substantially, right? Okay. This actually leads to faster real-world robot learning. So we have actually used the learn reward function, the reward function that we learned from Epic Kitchen videos, to actually open this drawer on a robotic platform, and where we are using this better reward functions, which are based on this factorization. And this actually learns faster and is better than past work, which has also tried to use in painting to learn agent environment, to learn agent agnostic representations and so forth, right? Okay, so that's kind of this. If you're interested in opening drawers and so forth, as an aside, we have some work on opening more complicated objects as well. And this may be the next thing that we should do if you're thinking about navigation, which is mobile manipulation like things. And if you're interested in learning more about this, you can come and talk to me at the poster session. Right? Okay, so I think what I showed you in this talk was essentially, this general idea of transferring from how we can learn from videos and for some sort of robotic manipulation and so forth. So I talked about how to interact with objects. You can largely use the same ideas for developing common sense about scenes. And this is some much older work, which was at NeurIPS 2020, where we were essentially doing the same thing. We were taking videos and we were learning spatial common sense, which is, in these videos, you can actually see what objects are next to one another, and you can develop spatial, these kind of spatial reasoning that, okay, if I'm looking for this object, I know this object is next to this other object. And if I'm seeing this other object, maybe I should go to this object and then go to the object that I'm trying to find. And this kind of information is very readily available in videos, and we had a framework for leveraging that. I guess I am running out of time, so I won't be able to talk more about that. But if you're interested in that, come and talk to me at the poster session. I'm happy to go into some of these details. Okay, I think I'll perhaps end over at this point, and I'm happy to take any questions and so forth. Yeah, thank you for your attention.
Thank you so much for the fantastic talk. If anybody has any questions, please come to the microphone.
Thanks, Sarah. Very, very interesting talk. Just a question. So how far, I mean, general question, how far can we go with videos? Like, can we go all the way and solve all interaction problems with if we scale up the number of videos, or do you think we still need some form of interaction for learning?
So I think my answer is yeah, I don't think we can go all the way. That is why there are these dotted lines. I think the solid arcs are where I think we can go from videos, but then we might need this we need to do something about these dotted lines. And that's actually what we are doing. So in this example that I showed, we learned dense reward functions, but they by themselves are not very useful, right? I mean, they just by themselves are not very useful. You need to embody, you need to render out actions from that somehow. And, you have to render out robot generation behavior. And we are using something classical over there, but, you could also introduce learning in that and so forth. So I don't think we can go all the way. I think we'll need to start interacting with things and such to get that dotted line to work.
So is it just a small addition on top of videos, or is it?
That's an excellent question. I think it comes down to how difficult is the low-level control problem. If you have dexterous hands, I think, dexterous robotic hands, they're different from human hands, right? So even though you can learn a lot, but you still need to learn how exactly these fingers are. And there a lot more has to be done on this platform. For navigation-like tasks, I think you can abstract out the actions, and then there's maybe relatively little that you may need to do for doing the transfer. So I think depends. That's why there are dotted lines of different lengths. Because
Great, thanks.
Okay, excellent question.
So we have time for a quick question. So yeah.
Hi, sir. Thanks for the talk. Do you think there is a value in also estimating the 3D aspects of the geometry here from the images?
Yeah, so that's an excellent question. And I think for manipulation tasks, I think what I showed you was only a purely 2D treatment. You can imagine that we can, rather than grasp labels, which are only really applicable when you're actually grasping something, you can imagine hand pose, 3 hand pose would be a more natural space to make predictions in. And there's some other work which is doing that, and we should do that. Yeah, no doubt.
Thank you so much. I think in interest of time, we'll end it there, but we do have the Slack channel, and if any of the speakers are willing, please go to the Slack channel and answer questions there. Next, I think Claudia will introduce our next speaker. Yeah.
Faye, can you hear us?
Yeah, we can hear you.
Great, we hear you too. Okay, awesome. So our next speaker is going to be Faye Shah. He's a research scientist at Google Research, where he works in the robotics team. He received his PhD degree in the Department of Electrical Engineering at Stanford University. And he was co-advised by Silvio Savarese at the Stanford Vision Lab and Leo Givas. His mission is to build intelligent embodied agents that can interact with complex and unstructured real-world environments with applications to home robotics. He will be joining online, and his talk is titled Embodied Reasoning Through Planning with Language and Vision Foundation Models. Faye, take it away.
Cool. Sounds great. Can you see my screen okay?
Yes. We see you as well.
Cool. That's perfect. Hi, thanks. Thanks for the invitation. And today I'll be talking about embodied reasoning through planning with vision and language foundation models. I'm a research scientist at Google DeepMind, the newly founded department at Google. And I have been involved with the embodied AI workshop for a long time. Like this is the fourth one. And previously I was organizing, either co-organizing a workshop or organizing challenges in the embodied AI workshop. So I'm very happy to come back and as an invited speaker to talk with you guys on the foundation models. So over the past couple of years, so there has been a paradigm shift from the internet AI to embodied AI. So by internet AI, I mean people have been collecting a lot of data sets in a computer vision field and have been like working on the tasks such as classification, segmentation, detection, captioning, generation, etc. And maybe a couple of years ago, there has been a shift towards embodied AI, where people are focusing on making the agents act in their environment and solve tasks such as like visual navigation, manipulation, rearrangement, question answering, mobile manipulation, and instruction following. And in that phase, the simulators have kind of replaced the role of data sets, and agents have been learning in those simulation environments. So far, we have been thinking about these as two paradigms, like the internet AI and embodied AI as two paradigms. But actually now I've been thinking about by having these foundation models, they have been pre-trained on the internet AI paradigm, and they can also be used to bootstrap the embodied AI. And that's why I have been like looking into using foundation models for robot decision making. Just give a concrete example. So in 2021, my colleague and I have this work called Rearrangement, which basically put an agent in an environment and do all sorts of mobile manipulation tasks. In this particular task, it needs to go through, close the door into a room. So its action space is navigation points and points to push in this environment. So it explores in this environment, and over 50,000 episodes and 1.25 million interactions, it figure out the solution, which is to pull open the door and go through this door to go into this room, which is intuitive. So it's already considered quite sample efficient, but we still need 50,000 episodes to find this motion. And a lot of time, the agent is just exploring in the empty space, which is not efficient. In last year, the language model or foundation models have gained a lot of traction. And we essentially can do this thing just by ask ChatGPT or GPT-3, how do you go into a room through a closed door? One, open the door, two, walk through the door. Super simple. This is like sampled at temperature 0. We can leverage the semantic knowledge to help you gain sample efficiency and learn things much faster. So over at Google DeepMind, we have been looking into using foundation models for decision-making in robotics. Just to quickly go over a couple of works that we have been doing. One of them is SeiCan, grounding language in robotic affordances, where the user can type in a command, given an instruction to the robot. In this case, I spill my Coke on the table. How would you throw it away and bring me something to clean? The robot needs to come up with a plan, which is to find the Coke, throw it into the trash, and bring a sponge to clean the table. The robot does that by predicting two things. One is there is a language model basically predicting the sub-steps of what are the steps required to finish the long horizon task. And there is an affordance model, which regularize the language model essentially. So we have a language score and an affordance score, and we multiply these two and take the highest one of the combined score. So the affordance basically tells the language model, hey, it's not possible to do it here, so you need to find some other plan. So you cannot pick up an apple if there is no apple in front of you. You need to find an apple first. So so in this case, it's mostly using affordance to guide language models to do long horizon instruction following. We have also been looking into low-level actions, basically not directly transferring knowledge from foundation models, but we follow the recipe of foundation models. So what is the recipe of foundation models? It's about scaling rules. We have a large-scale data and scalable architecture that can have better performance the more data and the more compute you throw at it. So we follow this recipe and build robotics transformers. We collected 130,000 episodes of expert demonstration over 18 months on 13 robots. And we train a transformer with pre-trained visual representation and just directly output actions. This is what we call robotic transformer. It has some interesting characteristics. So it's able to do 700 tasks with 97% success rate. It can also generalize to new environments and can do things with very high robustness. And it can also handle articulated objects and also deformable objects, such as pulling a napkin or grab a bag of chips from the drawer. So this has been Robotics Transformer 1, or RT1, where we experiment with high capacity architecture and scale up the data collection. We have also been looking into diffusion models. So far I've been talking about language models and following the recipe, but we have also been looking into using diffusion models to augment our existing data. So the robot is trying to pick up a can of Coke in an office kitchen, but that doesn't have to be an office kitchen. It could be a home kitchen, it could be a supermarket, it could be a living room or some like workspace. And we augment the different scenarios. So the learned policy is not overfitting to a particular environment. It can do things with high robustness and generalize with different backgrounds. We can also augment the data so that it's reimagine different scenarios. For example, it's putting the thing into the drawer, but we can reimagine the drawer into a sink, and then it knows how to put things into a sink. So this has been rosy. So as you can see, we have been exploring using foundation models for robotics. And in this talk, I want to ask and give some thoughts on two questions. First is, can we transfer visual reasoning or high-level planning from pre-trained foundation models to robotics? And the second question is, can we transfer low-level control from pre-trained foundation models to robotics, which arguably is a lot harder. And I will explain why. So for high-level planning, it's closer to the LLM training corpora or tasks. So we have been reading the WikiHow articles to learn how to do things, and language models have read about that too. So given the closeness of the task space and training corpora, zero-shot planning is possible, which is shown by Wenlong's work in 2022. However, we show that grounding is needed. The affordance is very important, like Professor Saurabh Gupta also mentioned. Grounding is needed to improve the performance. In the SEICAN work, we have shown that using the language model itself, just do the zero-shot planning, essentially half the performance compared with when you are paired it with an affordance model. However, in all of the work that we have done before, we have been treating this language model and affordance model as two models. Can we do it in just one model? And do we see interesting transfer behavior when we build just this one model? So today I will be talking about the POM-E, embodied multimodal language model. In terms of low-level control, it's a lot harder. And so far, we need a lot of expert demonstrations to achieve low-level control. And even when we try to transfer things from foundation models, we mostly transfer the vision part from foundation models, such as we use open vocabulary detector, we use open vocabulary segmentation tools, and also clip representations for this transferring the vision part from foundation models. However, we recently proposed we can learn low-level skills by leveraging language models. The only thing we need to do is to define a better interface. And we hypothesize that reward might be a good interface to transfer low-level motions from language models to robotics. First things first, let's talk about the PaLM-E, Embodied Multimodal Language Model. This is a collaboration with folks at Google Research. The main gist of this work is that we combined the largest vision transformer, which is VIT, 22 billion parameter model, and the biggest language model, which is PaLM 540B. We fine-tuned it on some robotics tasks, and now it becomes a capable robot brain, essentially, and you can use it to do robot planning, you can use it to do scene understanding, question answering. It's also a very capable general vision language model, period. There are some interesting findings that we found along the way, so I would like to share with you guys. Some highlights of the PaLM-E. So how do we do it? We largely build on a language model backbone, which is PaLM, and we basically do this multimodal tokens inside of the PaLM-E. So the multimodal tokens can come from images, or it can come from robot sensory data, or it can come from states, robot states. And we basically train an adapter to adapt those robot states or images to the token embedding of PaLM. So it's basically an affine transform from the multimodal tokens to the language tokens. And then we interleave. We support arbitrary interleaving. Basically, we interleave the multimodal tokens with the language. Essentially, we just treat the robotics problem as a visual question answering problem. And it's basically a multimodal sentence as input and a multimodal sentence as output, and the sentence as output. So the sentence in this case is text. It's usually a plan or some like answers to certain questions. So what we find interesting is that we see positive transfer. So we use this one model to train on different robotics tasks, including 2 embodiments. One is this mobile manipulator that can do mobile manipulation tasks, involving like navigation and manipulation. And there is a second embodiment, which is an open source environment called the language table. And the robot is able to rearrange objects on the language table. And all of this is coming from the same model. Also, it has seen some very interesting zero-shot generalization capabilities. One of the very interesting capability we found is it's able to do zero-shot chain of thought reasoning. You can basically give it an image and ask it to analyze the image step by step, and it will output the steps. So just a brief history of multimodal language models. So there has been Frozen, and there has been Flamingo, which is using cross attention. There is this Pali from Google that is using the VIT and also an encoder-decoder language model. Recently, there is also PaLiX from the same team. And some of the concurrent work, including Blip2, Cosmos 1, and GPT-4. What motivated us to do this multimodal language model is, of course, robotics. So historically, we have been working on language models plus robot data for high-level planning, including SEICAN, Socratic models, and inner monologue. So SEICAN does this affordance grounding. Socratic models combines multiple models, including a vision language model, and use language as an interface between all of the models. And inner monologue start to ground the planning in environmental feedback. And in PaLM-E, we try to combine everything. We try to combine everything in one model and treat everything as a vision language modeling problem. For low level, we have been looking at interactive language, language table environment, and also the RT1. So I would ask people to refer to our paper for more details, but our main model is a PaLM-E 562 billion model. It's a generalist vision language model. It's trained on robot data, internet scale VQA and captioning, and we start to see transfer from the internet scale data to robotics tasks. Not in the main results, but we also explore in PaLM-E some neural scene representation, neural 3D scene representation, and object-centric representation, like the OSRT, which helps with the task and motion planning in robotics tasks. So sometimes the occlusion is a problem, and by using this neural representation and slot attention, we are having better performance. We also did a couple of experiments involving different domain or category of robotics tasks. We found our model is state-of-the-art in vision language tasks. One of the vision language tasks is called OKVQA, which requires reasoning with outside knowledge. And perhaps not surprising, with a super large language model, 540 billion parameter, it stored all the outside knowledge. So it does quite well in the OKVQA task and achieved the state-of-the-art of 66.1. And last but not least, we only fine-tuned the PaLM-E on multimodal input data for not too long, so it still remember a lot of the language tasks, and it's also a capable language model, and scaling it larger makes a catastrophic forgetting problem less severe. So just to showcase a couple highlights of what we were able to do with the PaLM-E model. So first of all, it can do zero-shot multimodal chain of thought. So maybe I will highlight two examples. On the top right, it's a confusing street sign. Perhaps not too confusing, but it requires a bit of reasoning. So we can ask the language model, given the image, can I go down the street on a bicycle? Yes or no? Let's think step by step. And the answer is do not enter. Second, accept the bicycles. Three, do not entry except the bicycle. For yes. So you should be able to go down this with a bicycle. So interestingly, it's basically understanding both the text, the sign, the signage, and everything, and then use that for a reason. So I think this is one good motivation for using multimodal language model. And maybe let's take a look at the bottom left. We are doing few shot prompting for it to do a joke generation based on the image. So in this image, we ask it to generate a joke, and it first generated a description. A donkey is carrying a dog, cat, and a rooster, and generate a joke. What do you call a donkey with a rooster on its back? A rooster booster. So it's quite interesting and quite creative. Like when I see this, I'm pleasantly surprised. And finally, it can also do math reasoning. So in this case, we give it a menu and ask, I'm just getting 2 custom pizza for me and my friend. How much should I pay in total? And figure out there is this pizza and there's a $9.99 on the right. So it gives you the answer of $19.98. I guess I will skip this part. So although we only trained with a single image in the question, it can also do multi-image reasoning. And we're seeing positive transfer from PaLM-E. So basically, when we train with only one embodiment, we are not seeing great performance. But when we combine all 3 robot embodiments and when we're mixing with internet scale data, we're seeing big performance boost on all 3 embodiments. So which is like showing we're transferring knowledge from the internet scale data and the internet scale pre-training to robotics tasks, which is super encouraging. And here I would like to showcase quickly 2 robotics tasks. One of the tasks is to bring me the rice chips from the drawer, and the robot open the drawer, take the rice chips out of the drawer. So interestingly, here we are not using a separate affordance model. The robot understands affordance just within the large language model. So when I put the bag of chips back in the drawer, the robot is able to pick it up again. So it basically knows in this particular state what it needs to do. So the retry is almost emergent, right? The retry is not emergent, but it's just baked in the model itself. The same model, as you can see just now, can also work on a different embodiment. In this case, it's a language table environment. and it's able to rearrange the blocks. Sorry. Yeah, it's able to rearrange the blocks to put sort out the blocks into different corners and respond to adversarial perturbations. And finally, the catastrophic forgetting issue, which is usually seen when you do fine-tuning from a language model into a specific domain, it's much more severe when you have like only 8 billion parameters. With a super large scale model, 540 billion parameter models, you see negligible performance drop in this natural language understanding tasks. For more on PALME, I would encourage the audience to look at the website. There are some interactive demo on the website. I would like to go into the second part of this talk, which is low-level control. So historically, we require a lot of demonstration, but in this case, we hypothesize reward might be a good interface for robotic skill synthesis. So this is a new work that is hot off the press, language to reward for robotic skill synthesis, which we recently put on archive just on Friday. So we have been looking at using language model to generate a plan or generate low-level actions or generate code to do low-level actions. But we still struggle to synthesize new motions. For example, if we just want a robot dog to stand up on 2 feet, and we want a language model to give you the steps to do that, it's not possible. When we probe the language model, we actually find it has quite a bit of knowledge of how this motion might look like. So it will tell you the dog should stand on 2 hind feet, the 2 hands are, 2 front leg are in the air, mimicking human, but it's not actionable on the robot. However, if we directly synthesize code to do this type of motion, it's also not possible because there is no like training corpora on how to map the human instruction to motor joint angles to do a certain task. So what is the best interface between language and low-level actions? We hypothesize reward might be a good interface because what do we think about skills? So previously we think skills is a mapping, is a PI, is a policy that map from state to actions or map from observation to actions. However, the skill could also be a reward or constraint. Let's say pick something up. The skill is essentially defined by a constraint or reward. It means something is in your hand and something is off a supporting surface. So it's very easy to represent that using a reward function. So essentially, we use the reward function as the interface. We have a reward translator that transfer like human instruction into a reward code. And then we use a motion controller, which is MJPC in this case, to solve the reward function in real time using black box optimization or using gradient descent or ILQG gradient-based method. We benchmark this. Well, it's very important that we use MJPC because then we can synthesize the motion in real time and human can give additional feedback to correct the actions. We demonstrated this algorithm on 2 embodiments. One is a robot dog, and the other is a mobile manipulator. And for the robot dog experiment, we are able to make it stand up on 2 feet like a human using the just a language. And we can also give additional feedback or give additional requests, like make the robot do a moonwalk while standing up like this. And as you can see, it doesn't generate really good motions because it set some parameter wrong. And then you can give it more detailed feedback. And moonwalk means you should walk backwards with a foot swinging like going forward, correct the answer and make it walk at a speed of 0.5 meters per second. And this time it generates the right motion. And in the manipulation task, we could also make the generate reward functions to make the robot pull open a drawer, put things in the drawer, and then close the drawer. This can also be done by using a high-level planner, such as in Seikan. And in terms of the results, we are able to compare with code as policies or ablation of our method, and we find our method performs much better than using code as policies, just using the low-level interface. And finally, we are able to transfer the policy to real and do basically do state estimation in the real world and generate a plan in simulation and then roll out the motion in the real world. And in this case, it's able to push the things push two things closer together or pick up an object. As a summary, we propose to transfer like internet scale knowledge from pre-trained foundation models into robot planning and robot control. In high-level planning, we propose PALMI, where we do language and affordance and many more in just one model. And we are also seeing positive transfer from vision language tasks to robot planning tasks. In low-level control, we define an interface which is using a reward, and we are able to synthesize dexterous motions and synthesize new motions to do these different robotics tasks. And I would like to thank my collaborators and colleagues at Google DeepMind. If you have questions, feel free to shoot me an email, or I'll be answering questions on Slack. Thank you.
Thank you so much, Fei, for your talk. We have about 4 minutes per question. Anybody in the room, feel free to come to the mic, and I have some questions from the online attendees. Go ahead.
Hi, Fei. Thank you for the great talk. I had a question about PAMI. So right now, the grounding to some degree is happening by providing images of an object or like a token of what you're talking about. I'm wondering if how far can we go with this? Because ideally, we'd like to give a textual description of, for example, an object that we want, and then ground it in vision as opposed to giving an image of that object. How far do you think we are along this line?
Yeah, I think that's a super great question. So far we use essentially 256 image tokens, and then we have a text, right? Like, for example, if a can is in front of you, you can do it. If it's too far away from you, you cannot do it. So it's doing this type of binary classification based on a multimodal sentence. I think there are some certain limitations of this method. So of course, you are at the mercy of the pre-trained VIT representation. Mm-hmm. For example, if all the spatial information is lost, then it cannot do a very good job of grounding. So far, we have found that the large enough, like VIT model is pretty good in terms of preserving this spatial information. But if we want to go further, I would hypothesize that some 3D representation might also be needed to help further grounding. Like if you can recover the 3D information of the object and supporting surface and articulation information, it should perform like much better than just with the image itself.
But then, like, if you don't want to use images, or if you don't want to use images at all and you want to just use language, but then you still want to be able to ground it for the robot in some sense, like, are we making progress along that line without giving images as an input to the language model?
I see. Yeah, that's a great question. We haven't looked too much into that. Yeah, so far we have been looking into putting like state information, vision information into language model, but just by grounding the language model itself, we haven't been looking into that. I know what you're talking about. You essentially want to help from the robot data, you want to help the language model itself. So far we haven't seen like signs of life for that.
Okay, thank you.
Hi, thank you for your awesome presentation. And I want to ask how you use the reward. Like the idea to map language to reward is awesome. And I want to ask whether you learned the reward or use some specific code to generate the reward.
Yeah, that's a great question. So we define a few building blocks of the reward. So some commonly used reward would be, for example, L2 distance of two objects, or objects to a target location. So we define such interfaces for the reward function. And then we ask a language model to leverage those reward function APIs to generate a reward. So similarly, for different embodiment, we might need different
different APIs. So for the robot dog, we then need different APIs. And for the manipulator, we need different APIs. But it seems the language model is able to understand the reward APIs and generate suitable reward functions. Like pick up an apple, it will just generate the palm need to be closer to the apple and the apple need to be off the ground. So it knows to generate such reward functions to achieve the task.
Oh, thank you. Then how do you think about extending this work to learning the reward using reinforcement learning from human feedback, aka preference-based reinforcement learning?
Yeah, that's a great question. So far, I think we can collect the generated reward function and collect human feedback and then treat this as a few-shot learning problem. Or kind of a retrieval, you can use retrieval augmentation when next time you want to generate a reward function. You can retrieve from like previously generated reward function and the human feedback. Eventually, you might also want to fine-tune your language model so that it can generate better like reward functions according to human feedback. So far, we haven't been collecting data on like generated reward and human feedback, but just as how people fine-tune dialogue models, such as ChatGPT, you can also fine-tune your reward generation models.
Yeah, I agree. And I think that personally, I think that supervised learning for the reward function is great, but I think if you use ChatGPT based on supervised learning methods, that would be also great. Okay, thanks.
I'm so sorry. We have more questions for you, Faye, but we are running out of time for the next speaker. So I'm going to ask you to thank Faye one more time and feel free to ask in a Slack more things.
All right. Our next speaker today is Rustam Selakuzunov. Yeah, he is a UPMC professor of computer science in the Department of Machine Learning at CMU. He received his PhD in computer science from the University of Toronto. After spending 2 postdoctoral years at MIT, he joined the University of Toronto and later moved to CMU. Russ's primary interests lie in deep learning, machine learning, and large-scale optimization. He's an action editor of the Journal of Machine Learning Research, served as a director of AI research at Apple, served on the senior program committee of several top-tier learning conferences, including NeurIPS and ICML, was a program co-chair for ICML 2019, and will serve as general chair for ICML from 2024. He is an Alfred P. Sloan Research Fellow, Microsoft Research Faculty Fellow, a recipient of the Early Researcher Award, Google Faculty Award, and NVIDIA's Pioneers of AI Award, and now he is here for you today. Russ, take it away. Whoop, I can't hear you.
There it is. Okay, I apologize. Sorry, was
no worries.
Fine. You can hear me, right? Everything is good.
Yep.
I wish I could be there in person. I apologize for not being there in person, and I'm in Europe right now. So if my connection goes a little funny, I apologize. I'll try to reconnect. So today I would like to talk about some of the work that we've been doing in the lab, and I'd like to talk about 2 kind of research thrusts. One is on object goal navigation using self-supervised embodied active learning and instruction following. And there's a series of papers, but the primary people who've done the work is Devendra Chaplot and Tiffany Min on a lot of these topics. And the second part of the talk, I'll talk about how we can ground language models, particularly large language models, to images for multimodal generation, make a connection to embodied AI space. And this work is done by Jin-Yu Koch, PhD student at CMU. So let me start by sort of saying that, how do we treat internet versus embodied data, right? And Faye kind of, just listening to Faye's talk, I've mentioned that. A lot of times when we look at the static internet data, it kind of looks like this. And if we look at embodied data, where the agent moves around the environment, it looks very different, right? So for example, here we're using state-of-the-art object detection system, and we're trying to find a chair. And this is a false positive. This is we're using Mascar CNN. Here we're trying to find a toilet and we are failing here to find it. And primarily because you see this object is half occluded. And so we cannot find it. And in general, if we look at sort of embodied data, there is the notion of consistency through time. Right, you see objects typically don't appear or disappear, in particular static objects from the environment. So how can we make use of this information? And there's this notion of, we can improve our perception system and in general, what we see by moving around in the environment, right? Not just recognizing objects from static images. And then there's notion of action, perception action loop. Right, there's been a few exploration in the last few years, but I think there's going to be more and more happening given, where we are right now with foundation models. But the idea that we're pursuing here is that, say, during perception step, we're going to be doing self-supervised active exploration. So think about the agent moving around the environment and learning about the environment. And in the second phase, we're going to be using self-supervised visual learning. So the question is, how can we use self-supervised exploration in such a way that we can improve our perception system, right? But so this notion of if you move around, you can improve your recognition or your perception system. So the way that we do it is we do it in two steps. In the first phase, we're basically learning to explore the environment by learning active exploration policy. So the idea here is that we start with some pre-trained model, some pre-trained segmentation model, and now we see better and better foundation models like the ones that Meta recently released. And that basically, we're building a 3D semantic map. The map of the environment, where things are, where the different objects are, and we're building it through what we call exploration policy, right? And that's the exploration policy is what we're going to be learning. And given that, in the second phase, we're going to be improving perception. We're going to be fine-tuning the segmentation models using 3D label propagation. So by understanding the 3D map of the world, we can actually propagate the labels and be able to build a better perception model. And the interesting thing about these settings is that in both of these cases, we do not require any additional label data. And the notion is, again, we can just use self-supervision to move around the environment, learn about the environment, and using 3D label propagation, learn a better perception model. So let me show you how this is done. So in the first part, we're building a 3D semantic map. So given an RGB image and given the depth, we're using an initial Mascar CNN model. In this case, you can use any other model here to get the initial set of semantic predictions. So we have a point cloud and we have semantic scores, right? Associating objects, semantic objects to the point cloud. Then using spatial transformation, we're going from egocentric representation to geocentric representation. Right, that gives us a geocentric representation of the voxels. And then given, the map that we've built from the previous step, we do a map aggregation to update our semantic map. Now, I'm kind of, there's few details in the system. You're welcome to read the paper, but essentially this allows us to build, a reasonably accurate 3D semantic map. So visually how that looks like, this is as the agent moves around in the environment. We're building the semantic map here. We have, in this case, we have 6 objects, and we're estimating, 3D here. So we have length, width, height, as well as K that corresponds to K different objects, right? The semantic objects. Now, the question you might ask is, how do we train an agent to move around the environment such that we can build as accurate map as possible? And we use a very simple idea, which essentially relies on reinforcement learning, but with a very specific reward. So what we do is we essentially count the number of voxels where we make confident predictions, right? So these are all the voxels where we make confident predictions about classes, and that now becomes our reward. That goes into reinforcement learning agent, and we're essentially training an exploration policy. right? And this is something that we call gainful curiosity. So where we're trying to gain definitive knowledge about the environment. Right. So the idea is, how can we move around the environment such that we can, find objects that we're mostly confident about what these objects are. And that allows us to build an agent that has these nice exploration capabilities where we move around and not just sort of stuck in one place. So that allows us to build, this exploration policy allows us to build a 3D semantic map. And so now, how does the learning proceeds here? We typically have a sensor pose reading. We have an observation. It goes to the 3D mapping. We have a global policy, where the global policy is also telling us where we should go next. Then we have a deterministic local policy. You can think of it as just trying to execute what the next step should be, and then we execute a low-level action. And in this case, we have a fairly simple procedure. We only have 3 actions. We either move forward, we turn left or right, and we sample goal every 25 local steps. So we execute local steps, sample the goal. And the global policy here is learned to explore the environment, again, using gainful curiosity. Now, in the second part of the phase, once we build a 3D semantic map, we're going to be using 3D label propagation to essentially update our perception model, right? And the label propagation, the idea behind label propagation is also fairly straightforward. We assume that all the objects that we're detecting in our SIEM are static objects. And let's say, the agent is located at a particular position, and this is where the agent is looking at. Now we can use, essentially get instance label for each pixel by using ray tracing based on the agent's pose, right? So given our semantic map, we can actually project these 3D space back into our image space, right? And so this now creates what we call self-supervised labels. Right. And then if we look, for example, at our perception model, in this case, Mars-Car CNN prediction, we're essentially seeing that these represent false negatives. Right. So in this case, we know that this is a chair, we know that this is a table, but we're basically missing them here. All right. And the reason why we sort of have this notion is that we've seen these objects, we've seen this chair from a different viewpoint. And now, given that this chair is in our semantic map, by using these projections, we can essentially create new pseudo labels, right? And so now, as the agent moves around, again, this is an example of, finding a false negative where the Mars-Car CNN says it's a chair, but it's actually not a chair, right? And so we can take that information and, as a false positive, and again, update our perception model. So again, this notion that building the semantic map and maintaining consistency of objects, we're able to create the pseudo labels. And then we can take these pseudo labels and update our perception system, right? And again, this notion of the fact that you're moving around in the environment allows us to, create these labels on the fly. In this case, we've looked at the 2 conditions. We looked at the generalization. So, we're training the system and specialization where, we get one test episode. So you can think of it as a setting where I throw the agent in the environment. The agent just walks around in the environment, explores the environment, updates its own perception model, and then we test how well this agent does. Right. So again, in all of these settings, we do not provide any additional labels, right? And that's why the notion of self-supervision here becomes important. So we've looked at a Gibson data set, 25 training scenes, 5 test scenes. We so far looked at only 6 object categories. We have a training set, we have evaluation set, and we report, the standard scores. What's interesting about these systems is that if you look at, Mars-Car CNN model, we get these scores. And if we've tried, looking at a lot of different algorithms, including self-training, including optical flow, there's a frontier-based exploration, there's active neural SLAM systems, semantic curiosity systems. You can also interestingly see that a lot of these models don't really improve over the baseline pre-trained model, right? So you can think of it as, obviously there are better models today compared to Moscow CNN, but you can sort of see a lot of these models don't really move the needle. Whereas using these ideas of self-supervised active learning, we can actually do much better. Of course, still there's a lot of room for improvement, but we can do much better here. Another thing that we started thinking about is this notion of self-supervision with location consistency. Much like what we're doing with propagating the labels, we can build a system. This was done jointly with Apple Research, where we look at a particular location and the agent moves around and looks at that specific location from different views. And then we're using contrastive learning to essentially say all of these representations should be similar to each other, right? And what's interesting about, again, this notion of self-supervision, the different way of doing self-supervision, is that, using unlabeled data and using this notion of self-consistency, sort of location consistency, we can basically reach the same performance as if, we had supervised data for 25 labeled houses, right? So about 100 unlabeled houses where we do this consistency sort of estimation allows us to basically reach the same performance as a supervision with 25 labels. So again, this sort of points to the notion that the idea of self-supervision in embodied AI systems where you solve sort of different tasks, either 3D label propagation or location consistency, is an interesting one because it allows us to actually build systems that work on par with more or less supervised systems. And this is just the setting where this robot was built by folks at Apple, and you can sort of see it's moving around, and here you're trying to find a bed, and it builds the semantic map and eventually, finds the object of interest. This also sort of gave us the idea of instruction following, right? That's another very interesting area of research, and there's a lot of work done in that space. We've looked at this environment called DialFred, where the agent has given an instruction. You have to go through a sequence of sub-goals. You have to figure out what these sub-goals are, and then figure out how to solve the task. And in this case, you can sort of see here we're given an instruction. We go through language parsing, and the language parsing gives us a set of subtasks that we need to execute. Whereas from the RGB, we build a semantic map, much like what we've seen in the first part of the talk, where it's in this case, it's a 2D semantic map. That information goes into semantic search policy that finds, the next sub goal to execute, and it goes to deterministic policy that actually executes low-level actions. One interesting thing about these sort of ideas here is that, language becomes important, semantic map becomes important, and this notion of semantic search where we're looking for the right object or executing the right sub-goal becomes important. So this idea of multimodal learning becomes more and more dominant. And I think we'll see more and more work kind of done in that space. Right, and this is what, for example, a system like this would look like. You can see that you're building the semantic map, you execute a bunch of these sub-goals. What's interesting here is that you have to execute a couple of nonsensical instructions here, like opening the fridge, putting the lettuce, in the fridge, then picking it up from the fridge and stuff like that. And the reason why is because instruction says you have to place a cold lettuce, right, in a waste basket. So it has to be cold. So you kind of have to put it in the fridge and then take it from the fridge and then throw it away. But nonetheless, these are interesting, sort of interesting simulator to look at. One interesting aspect of this simulator is that finding small objects becomes really hard. So this perception problem still remains one of the challenging problems, especially in these environments. Now, let me sort of, and we get results, obviously, but one interesting thing about, building these agents is how can we interact and take multimodal input into account, and as well as reason and understand natural language. So let me quickly jump into the second part of the talk, is how can we ground these large language models for multimodal generation. Now we've seen that LLMs have been very impressive in the last, the last 6 months. We've seen explosion of these models. And typically these models are text to text and they're resource intensive. There's been a lot of work in trying to sort of adapt these models for multimodal tasks, like for example, prefix tuning, where we give it an image and then try to describe what's going on, or we fine tuning new cross-attentional layers, to be able to deal with images, for example. But a lot of these systems are operating in, give an image and text, you sort of generate text. And we started asking the question of, can we ground text-only large language models so that we can take as well as produce visual data, right? So for example, here's the system where, you have a dialogue, but in addition to having a dialogue, we can also retrieve images, right? So here it says, here are some of the birds that eat seed and so forth, right? So these is what the model actually retrieves. And so, how can we take these large language pre-trained text-only LLMs and essentially build the multi-models from them that can take images into account so that we can maintain in context learning and can generate coherent dialogues. We've been thinking about building these models that are frozen, that are model agnostic. And we also were trying to figure out how can we build these multimodal models that are simple and resource efficient. And in particular, we can adapt large language models to deal with this multimodal data using a single GPU and training for 24 hours. So let me quickly show you how we're doing it. We're basically getting very strong image text retrieval models, and these models typically, use some form of, encoder-based language models. And the question is, how do we adapt to autoregressive models? The way that we do it is we learn a special retrieval token, right, for retrieving images. And the model is going to be trained to learn when to generate the retrieval token. And by essentially having a dedicated token, we can improve the retrieval by about 30% over not having a specific token, right? And maybe just quickly show you what the model does. It's a very simple model. We call it fromage. It's a frozen language model. So let's say here we're adapting it from the captions data. We're using conceptual captions data set. So given an input caption, we pass it through the large language model. And our goal is to generate the text plus the retrieval token, right? Because we talk about, we talk about specific captions. And given the input, we use the visual encoder, and we're essentially using noise contrastive estimation loss to make sure that whatever the retrieval embedding is fairly close to the visual encoder. So these layers are being trained, these layers are being frozen, right? And again, that allows us to build models that are fairly easy to tune, because we're essentially just learning two linear projections, essentially learning to align what the text is saying to the visual representation. And just to quickly show you that, these kinds of models, they work reasonably well without fine-tuning large language models. Here we've looked at the contextual image retrieval. So given a series of text and images, these are from visual storytelling, can we retrieve the image, right? And these models, our models would go from MASH, frozen language models, they do quite well. We also looked at the visual dialogue where given in the prompt, you have a bunch of questions and you want to complete the answer, or given the questions and answers, at the end of the day, you want to retrieve a correct image that that's relevant to a series of dialogues about it. And again, these models do fairly well across different tasks. And, we've tried to look at the, VIL bird, we looked at Klim, Flamingo, and so forth, right? What's interesting about these models, and it's relevant for embodied AI, is that we found that multimodal context is actually fairly important. So the longer the context that your model can take into account, the better your, let's say in this case, the retrieval of the correct image is compared to, not having much of a context. And again, looking at, for example, a model like Clip versus looking at our model, and you can sort of see that, a longer dialogue typically gives you improved performance. That's one of the messages that I want to communicate here. The self-supervised aspect, as well as a larger context, is important. And again, just to give you some examples here, it's kind of fun to play with these models. You can say, what kind of animal I'm thinking? It's brown and furry. It's a squirrel. No, the animal I'm thinking lives in the river. A beaver. That's right. They have a tail. Show me illustration of a beaver. It shows you a beaver. And then you say, yes, what about a pencil drawing of one? And so here we're failing it, right? We're retrieving an image of a beaver with a pencil, but not the pencil drawing of a beaver. How about a photo? And then we retrieve the photo, right? So you can sort of go in and play with these models. And, as a next step, we've been building models that can extend these models, not just to retrieve the images, but also to generate. So, there's the retrieval aspect of it. There's a generative aspect of it using stable diffusion. And now you can have systems where you can ask, how can I make this more nutritious? The system would say, add, this and this, and it would actually generate the image. So this is the image that was generated by stable diffusion, right? And so you can interleave these systems with either images that are retrieved or images that you can generate. And I think these kinds of systems are going to be fairly important for embodied space, especially when we're going to be interacting, either through instructions or through communication with embodied agents. And you can try this model. It's online. It's free. In fact, a lot of systems that I've talked about today, a lot of it is open source, so you can play with these models. And on that note, I'll stop because I'm running out of time. So thank you. I hope I haven't lost the connection yet.
No, you're still here. We're here.
Okay, excellent. That's great.
Excellent. All right. Anyone in person, if you have questions, please come to the microphone. And if you want to ask your questions online, please just make sure to use the Slack channel. All right. As a starting point, a question from online. We now have large data sets of 3D assets with paired text, Objaverse example. How do you see these being used to enable viewpoint consistent detectors and segmentation models? Are there any caveats about using these objects in a similar pipeline to the one shown?
Yeah, that's a very good question. I think this is something that we've started to explore, but we haven't made much progress yet. I think the idea of having 3D assets, one of the challenges is, when you are in embodied space and you're actually operating in the physical world, because we're also building robots that operate in the physical world, sort of matching those 3D assets to the real world becomes a little bit of a challenging piece for us. What we do find is that, perhaps surprisingly, is that the latest models that Meta released, I think, blanking on the name of like Segment Anything or Dino V2, they actually work surprisingly well in terms of being able to segment the objects. And, with the viewpoint, once you move around this object and with the depth, you can actually get fairly accurate 3D representation of these objects. So I think that somehow we should be able to use those 3D assets. But, what I'm seeing right now is that these foundation models are getting to the point where we can actually get fairly accurate representation, 3D representation, just by, using the current pre-trained foundation models.
Awesome. Thank you. Yes, go ahead.
Hello, Prof. Thanks for the nice talk. And I have a question because now you're trying to use some phrase language model and phrase vision model to build like a fake foundation model for multi-model. But I think that's just temporal solutions that we can solve now, just training efficient. But what's his long-term vision for the solution, like really tackle the problem? Yes, that's the problem.
So, yeah, it's a very tough question because in academia, we cannot train these large models and fine-tune them from scratch. So that's why we've been thinking really hard about how can we use existing models and how can we adapt existing models to deal with multimodal input. We're also seeing that, potentially, I think that, if you have enough compute and enough data, I do believe fine-tuning these models will probably work better, right? So in a sense that alignment, we've seen this example of clip is a very good example of aligning text and images, even though the data sets are very noisy. So one of the big challenges that I see right now is the data. The data for multimodal dialogue is very difficult to get. Right. And so that's why we're also looking at the frozen models where we don't have a lot of data. We've looked at visual storytelling, we're looking at the captioning, but it's still not enough to have a dialogue, and evaluation also becomes challenging. In terms of, the capabilities of what architectures to use, I think we know what architectures to use. I think the architectures that we've been using right now are probably going to get us there. But it's the question of the data and it's the question of evaluation, right? That's something that's at least we've been struggling with.
Okay, thanks, Prof. Thanks.
All right, well, there's no more questions online and we have exactly hit time, but I want everyone here to thank Russ for a wonderful talk.
Thank you.
Now, after this, we've got the lunch and the poster sessions available. They will be held in Exhibition Hall A at posters 123 through to 148. If you're wanting to, we can all move as a cohort. We're meeting around sort of central area and then heading off together. So just look for me. I'll be the person leading people to the posters. Cheers.
Oh, yes, for free. Yeah.
Hello, everyone.
Hello.
Hello.
Which is the other one?
Do you want me to share the slides already? Are you still testing sound?
Okay, now are you the host? Okay, can you give it back to the?
Oh, it's very low volume somehow. I don't know if this is.
It'll, is that good?
Yes, that's
Okay,
way
okay.
better. Yes.
Perfect. We just have to be near the mic.
Hi, Dieter.
Oh, great. Great. Yes. Okay, you be able to give me the Luca Wise one. I'm sure there is, but it's with the whole like sound system here. So I guess I could just raise my volume. Yeah. Oh, yes.
Could you speak a little bit just to see what the volume is?
Yes. Hello, everyone.
Yeah. That's great.
Hi, Claudia. Hi, Dieter. Hi, everyone in the audience who I see. Let me know if I should continue.
It works well.
Okay.
So we're waiting for people to come back from the poster session. Maybe we wait a couple more
Yeah.
minutes and then go.
Sure.
Okay. Okay, I think we're ready to get back to the afternoon session. We will have 3 speakers, the interaction challenges on the panel, and a speakers panel at the end of the day. So we are up for a great afternoon. So our next speaker is going to be Jeanette Borg, and she's an assistant professor of computer science at Stanford University. She was a group leader at the Autonomous Motion Department at the MPI for Intelligent Systems until 2017. And before joining AMD in January 2012, Jeanette was a PhD student at the Division of Robotics, Perception and Learning at KTH at Stockholm. She proposed novel methods towards multimodal scene understanding for robotics grasping. She also studied at Chalmers, I'm sorry. A lot of names I don't know how to pronounce.
Swedish names, yeah.
Right. At the Technical University of Dresden. Dresden is a great city, where she received her master's in art and technology and her diploma in computer science. And today, Jeanette will be speaking about large language models for solving long horizon manipulation problems. Take it away, Jeanette. Thank you so much for joining us.
Thank you so much, Claudia, for the nice introduction. And thank you so much for inviting me to the CVPR workshop on embodied AI. So yeah, I'm going to talk about this topic. And let's first talk about what long horizon problems actually are. So these are, for example, problems that you could imagine a robot doing in this particular kitchen, like giving a high level goal that could be cooking a meal or cleaning up this place or unloading the dishwasher or unpacking groceries and storing them away. All of these types of tasks in this kitchen here, for example, involves or requires the robot to figure out a sequence of actions to achieve this high-level goal. And what is definitely not practical for doing this is to plan every joint motor command to accomplish this long horizon task. It's just not computationally feasible to operate or define algorithms on this level. So it's really helpful to abstract away low-level details of the environment, such as the exact poses or mesh geometries of the objects, and operate at the level of symbols instead. Like, for example, whether this pot is on the stove or this microwave is closed or not. And using symbols to plan over long horizons is called task planning. And it has its roots in early AI when researchers studied how to give robots the ability to reason through symbols and logical reasoning. Task planning alone, though, is not really enough for robots to perform tasks in the real world. So consider this example here where the robot needs to transfer this mug from the dishwasher to the cabinet. And task planning might come up with a simple two-step solution to this problem, where the first robot picks up the mug and second places the mug in the cabinet. But if the robot blindly executes this very simple two-step plan, it might actually not succeed, because in this case, since the robot grabs the mug from the bottom, it's as it is the easiest way to pick it up from the dishwasher rack, it can't actually place it later upright in the cabinet, because the gripper would basically collide with the shelf. And this is an example for a problem where the geometric aspects cannot be, that we actually purposefully abstracted away for the task planner to do its thing. Ultimately, we can't ignore these details, and we actually want to execute this task plan in the real world. And so this really motivates the need for something like motion planning or planning, where we can plan a motion trajectory that will successfully execute the sequence of actions proposed by the task planner. So in some cases, though, like in this one, the motion planner might not be able to find a feasible collision-free trajectory here for the given sequence of actions. And so instead, what the robot may need to do is to, after picking up the mug, it may need to actually place it on the counter first so that it can pick it up from a different configuration and then place it upright in the cabinet. And so this task plan involves 4 action and is a different task plan from the original 2-step one. But it's one that is actually feasible for the robot to do on a geometric level. And so motion planning can really affect the task plan. So we need to somehow include feedback from this motion planner back into the task planner so that we can come up with a better task plan as well, or so that it's informed and that the task plan is geometrically correct or symbolically correct and geometrically feasible. And so this integrated loop of task planning and motion planning is what is actually called task and motion planning, or TAMP for short in the literature. And there's a lot of works in this area. And so here are 2 videos of state-of-the-art algorithms, which can perform long horizon tasks, such as grabbing an object outside of the robot's workspace, using a hook to bring it closer, that's on the left, or performing food preparation tasks in the kitchen. And so these TAMP planners can actually find very impressive solutions to long horizon planning problems. But the catch is that they're extremely computationally expensive. And so the TAMP solutions in these particular videos, they took several minutes to solve or to find. And as a result, these previous TAMP works are often limited to simulated environments or highly controlled environments where there are no moving objects or external disturbances. And we, in my lab, we ask ourselves, like, how can we bring this actually great way to break down the problem into the real world? And it's of course, it's really important to do that because we can't just expect the real world to pause itself for several minutes while the robot tries to find a plan. And so here is an overview of what I think the necessary components are to actually bring these kinds of task and motion planning types of methods to the real world. And this diagram really, it's like a very high level diagram, but it shows the crucial system components of a robotic stack for performing these long horizon tasks. And a lot of previous work in this TAMP area focuses on the integration between task planning and motion planning, which what you see here in green, and ignores everything else. And this is why TAMP is typically, in the traditional way, it's typically limited to simple and static environment. And really, if you want to bring this nice problem framing that TAMP actually brings into the real world, it requires integrating these methods with the rest of a robotic stack. And for the rest of this presentation, I'm going to mention a few works that we've done in this space, and in some of them, specifically the one where we used large language models, I will go a little bit into more detail. So the first thing we did in my lab is actually use a very reactive reformulation of the problem based on trajectory optimization to actually deal with objects that are moving while the plan has already been computed and the robot has to actually adjust to this. So let's take this problem here. I'm just going to talk very briefly about this. The goal is to place the small box onto the large box, but the problem is the small box is outside of the workspace. And so the robot actually has to pick up the hook to bring the small box closer, then place the hook somewhere, pick up the small box and place it on this large box. And so the way we frame this problem is to combine symbolic and geometric reasoning using something called object-centric Cartesian frames. And what happens now is that by doing this reformulation, this robot is actually able to execute its plan despite Toki, the first author of this paper, actually disturbing the robot, pushing it around, moving the object around while the robot is trying to execute this plan. But because it has this particular framing that is object-centric or relative to objects, it can actually adjust to these disturbances. And as it also turns out, this task and motion planning framework that we are using, it can find multiple solutions if there are multiple feasible ones. And we can also, because of a particular framing, actually solve them really quickly. So finding these 2 solutions here to the Tower of Hanoi problem took like less than a second in both cases, which is nice. Okay, so I don't want to talk too much about this method because it's a traditional method, but I just want to show you how we can how we can make these TAMP planners actually feasible in the real world and make them reactive. And so one thing that we haven't done in this previous work that I just showed you is to actually also change the task plan. We only change the way the robot actually executes on a lower level its motion, but we also want to be able to react to any symbolic changes in the environment that actually may influence the task plan. So for this, we basically looked in this particular paper at a way to ground predicates, that is what a task planner reasons over, through actions, and actually learn this grounding from human video. So we used the 20 billion something data set in this case. And so now I show you how once the robot actually learned how to ground predicates, given videos of people actually doing the same actions, we can now use these predicates in a closed loop task planner. So here, the robot, what it wants to do is to actually put all the fruit, or reach the goal where none of the fruit is on the surface anymore, and everything that can be closed is actually closed. So this is the goal, expressed here in the logical formula on the top. The initial task plan is here listed under action skeleton on the right, starts with open the drawer, pick up the banana, put the banana in the drawer, and so on. And then here on the bottom right, you see the classification of these different predicates that the task planner actually needs to come up with different task plans. So basically what is happening here is that we're in real time basically try to classify these predicates and then replan based on changes of these predicates while the robot is actually operating. So you see again, Toki, who's the first author of this paper, again, is like disturbing the robot, changing the environment and therefore the predicates, and it has to react real time. So you see also the action skeleton changing all the time. Okay, so now what we have is basically this framework for doing task and motion planning on a robot in the real world that is very reactive, right? So it can really deal with disturbances, both by adapting on the symbolic level, but also on the geometric level, okay? But what is maybe a little bit dissatisfying or unsatisfying with this is that we still rely on a lot of handcrafted domain knowledge, right? So for example, for this task planner, we just use strips planning, which is a very traditional method, right? And basically needs this kind of domain definition that you see here in PDDL. And for the other work that does this object-centric task and motion planning, we actually use a trajectory optimization approach. And what is very hard to actually set this up is defining the constraints for all of the different primitives, like picking, placing, pulling, things like that. It's actually very tedious to set these up. It's beautiful math, but it's hard to scale up to maybe, let's say, 70 different primitives. And so what we did next after finishing this work, we were thinking like, okay, we really want to scale up the kinds of primitive skills the robot actually has. How can we do that? Preferably by learning, and preferably by learning in the most efficient way. So looking at videos again from humans. But really, I don't want to focus today too much on this part. But in my lab, we developed something called concept to robot that basically looks like this or solves this problem, where it takes as input a natural language instruction, like put something behind something or put something into something. It gets an initial scene image, inputs that to this, what we call manipulation concepts here, and then outputs the appropriate motion trajectory according to what we instructed the robot to do. So you can also think of this manipulation concept bubble there in the middle as a multitask policy. And again, like if you're interested in this work, feel free to look it up. But what we come up with is basically one policy for 78 different skills or tasks, like the ones you see here. And all of these have been possible by actually learning them from human video demonstrations as well. And the nice thing is that the language input here, which by the way, back in the days in 2020, we encoded this with a BERT encoder, really like index into this multitask policy and tell the robot what to do in this particular scene. So we have like, again, as I said, like 78 different ones. And we can even, at that time, right now, it would probably work even better. We could even generalize to novel instructions as well. Okay, so I didn't want to spend too much time on these works. So, you know, we use concept to robot, but you could use any kind of method that is out there to learn a library of policies, right? To replace basically these hand-coded controllers that we had before with many more, right? That are now hopefully easy to scale up by learning from videos. But you see there's now a gap here between this motion planner and the learned policies, right? So it still remains to be seen, like how can we now with this library of learned skills or learned policies for these different tasks, how can we actually sequence them together? And so this is not just as simple as executing learned policies in a sequence. So let's come back to this example where the robot needs to pick up a mug from the dishwasher and place it upright in the cabinet. So we can learn a policy that picks up objects with 100% success rate. And then we can learn another policy that will place objects into cabinets with 100% success rate. But executing them one after another would not necessarily mean that the robot would actually succeed, because there are geometric dependencies between these actions that the learned policies for picking up the mug doesn't take into account. And so we need to figure out how to pick up the mug in the way that allows placing it in the cabinet later. So before with our handcrafted policies, we used motion planning to reason about these geometric dependencies, but it's not quite obvious how we can do motion planning with learned black box policies, basically. And so one way is to do RL with this. So lots of people have done this, but they typically actually 3 out of these 4 works that I show here, actually they claim to do RL for long horizon problems, but they don't really generalize over many different long horizon tasks. So 3 of these papers, except from the one from Danny Dries, is actually handling exactly one long horizon task, and they can only generalize to different instances of the same long horizon task. And so that's really unsatisfying, because we want to generalize to many different long horizon tasks, right? With many different chaining the skills basically together in many different ways. And the last paper from Danny Dries, it can generalize to other long horizon tasks, but to achieve this generalization, they require training on data collected from expert handcrafted policies. But our original motivation for using learned policies was to exactly avoid that in the first place. Okay, so let's see what we've done. How do we now do planning with learned policies, right? So let's say for now we keep this task planner in there because we like that we can use logic to reason about action, pre and post conditions and so on. And so we want to take advantage of this task planner's generalization ability. Okay, so the task planner tells us to perform what in what order, and all that's missing is now how to do it exactly with these learned policies. And so we propose a sampling-based trajectory optimization with policy value function of these policies to realize TAMP with learned policies. Okay, so what do we have given? We have a library of independently learned primitives. So a policy for picking, pulling, and so on. And we get from the task planner a sequential manipulation task. And so in this example, the sequential manipulation task involves picking up the hook from the table and using it to pull the yogurt that is initially beyond the robot's reach closer. And the challenge is that greedily executing primitives in the sequence may fail due to these geometric action dependencies. So for example, if the robot picks up the hook in a way that prevents it from actually reaching the yogurt, right? So the robot might pick up the hook in the center, which is the most stable grasp, but then it doesn't have enough reach to pull something closer. So succeeding at this long horizon task really requires reasoning over long-term dependencies between actions in a given task plan. And our core idea is to cast this planning problem with learned primitives as a maximization problem over the probability of long horizon task success. And we show that this is equivalent to the product of Q function for each primitive policy in the task plan. So intuitively, what this means is that basically, if earlier actions in the sequence are executed in a way that neglect downstream action dependencies, we might expect one of the downstream Q values to be low, and hence the overall planning objective J here will be low. And so the way we solve this problem is with sampling-based planning to find a trajectory where the Q values of all the primitive policies in the long horizon task are high. So planning with learned policies requires three key components. We have the primitive policies, their Q functions, and dynamics models that predict future states at which the Q functions will be evaluated. And we also, so we employ SAC to learn the primitive policies and Q functions jointly on independent environments with domain randomization. And the dynamics models are trained with the transition experience in the replay buffer collected over the course of training each primitive policy. And then we also use uncertainty quantification, which I don't go into detail right now. So in comparison to prior work, which includes model-based RL and traditional TAMP methods, our work can generalize to arbitrary long horizon tasks. It produces plans quickly through the use of learned models and also promises better scaling to larger libraries of primitives. So we compared our method to baselines across 3 domains, each with 3 different tasks that constitute a unique set of action dependencies deterring long horizon success. And so here, this domain you already know, right? Grasping the hook and to get something closer. And so our method is actually able to plan the pick hook action by grasping the hook at the end of its handle so it can perform the subsequent pull actions. And you see the greedy execution, on the other hand, picks up the hook in a way that makes pulling infeasible. Here's another domain, the constrained packing domain. Our method plans placement locations on the rack for all the objects to maximize the place policy's probabilities of succeeding, but greedy execution results in a configuration of objects that the imperfect place policy doesn't know how to handle, and so it fails. And here in this rearrangement push domain, the robot needs to pick up the yogurt to place it back on the table in a way that enables pushing it under the rack. But greedy execution ends up placing the yogurt in a location that causes the push policy to fail again. So you see it actually collided with the robot. Okay, so just to summarize, the problem we address is to handle sequential manipulation tasks that contain geometric action dependencies. And prior work trains a set of primitives synchronously for specific tasks which limit scalability and generalization. And our core idea is to train primitives independently and then plan to maximize long horizon success. And the result is a planning framework that can solve arbitrary long horizon tasks. Okay. So now you can probably also see what's happening here. So I'm replacing all of these boxes in this particular framework with a learning-based approach, right? And so there's one box left here that is the task planner. And previously, we basically use strips planning, which requires you to set up these domains, right, manually, which can be quite tedious. And of course, we've all seen those cool works, right, that came out that actually use these large language models to do these types of task planning, like or solve these tasks. And of course, it seems much easier to provide natural language prompts than these PDDL domains, right, where you have to adhere to very specific, syntax and so on. So what we did here is to actually rip out this task planner and replace it with a large language model. But then, of course, the challenge here is, as you probably all know, an LMM can output arbitrary garbage, and you don't want to have a robot to actually execute that, right? So the key challenge that we addressed here, or the key question that we asked here is, how can we given a language instruction, how can we actually generate and verify the plans for tasks with complex geometric dependencies, right? So we like the flexibility of large language model, but we hate their ability to, not know whether they output something right or not. Okay, so so how do we do that? So basically what we have again is a library of skills learned maybe with concept to robot or your favorite method. Then we have a language model, and the robot is now given a brief description of the scene through some perception model. You pick the one you like, And then it's supposed to follow an instruction. So for example, how would you fetch me any box from the table? And the robot's objective is to plan a sequence of action that satisfies the instruction if executed from the current state. And solving the task requires semantic and geometric reasoning. Now, prior work in language-based planning for robotic proposes to solve such tasks with the language-based agents, which at every time step ranks skills by their usefulness and feasibility and executes the highest scoring skill. In this case, the robot picks up the hook, but the grasp on the hook does not enable pulling the red box. The robot's only choice is to place the hook back on the table, returning the environment to its original state. And so this is like a cycle that goes on indefinitely if you do it in this greedy way. And this failure demonstrates that myopically selecting and executing skills cannot reliably solve long horizon tasks that contain these geometric dependencies. So we really must consider this feasibility of the planned skill sequences before they are executed. And in addition, a language-based planner needs a way to verify a computed plan that satisfies the natural language instructions if it's executed from the initial state. Okay, so the goal of this work is to construct this feasible manipulation plan and verify that it satisfies an instruction prior to executing any actions in the environment. And in step one in our work, the LMM infers a goal proposition that must hold in the scene for an instruction to be satisfied. And in step two, an integrated search algorithm is used to construct feasible manipulation plans by interweaving LMM task planning with geometric feasibility planning that I've just shown you in the work before at each search iteration. So the plan is only executed if the inferred goal proposition hold in the plan's final state, as predicted by a learned dynamics model. And so we actually use two different planning strategies. One is a shooting-based planner, where we query the LMN only once for a full sequence, and that's very efficient. You get very diverse solutions, but you may generate a lot of plans that are not feasible. And the other solution is a search-based planning method where you query the LMM numerous times through search. So it's basically a beam search. That's great because the plans are going to be likely feasible because you check every time you add another step. But the cons are that it's computationally costly and there's minimal plan diversity. So we made a hybrid method of this where we basically integrate the strengths of both of these planning methods, and we optimistically invoke shooting and fall back to greedy search if shooting fails. And so that's how we inherit both of these. And we evaluated this method on 6 different tasks that have varying degrees of difficulties, which you can read about in the paper. Yeah, so here's the comparison again against the reactive baselines from prior work that are basically greedy. And you see also the shooting baseline. The reactive baseline basically produces action with low value scores for the place on rec skills. So it just keeps placing objects back into the world, while our framework can basically pack them on this relatively tight space, and the shooting baseline can do that as well. We also have, here's another example. How would you get 2 primary colored boxes onto the reg? And again, it's the same problem with inner monologue, which is this greedy baseline. Again, it grasps the hook in the most stable way, but then fails to actually use it appropriately. Yeah, so this is called text to motion. You can find it on arXiv. It can solve geometrically complex manipulation tasks expressed by natural language. While prior work only does this myopically, we generate actually feasible plan and verify that they satisfy these goal propositions inferred from language instructions, and therefore we can solve these long horizon tasks specified in natural language with lifted goals and partial affordance perception, which are very hard cases. Yeah, so I think I'm actually out of time, probably. Yeah, so you can basically here see the overview of all the works I've been talking about. I also had some other work, but maybe because I'm out of time, I will probably skip this and just show you a cool video of another long horizon work that we've done recently that doesn't have these geometric dependencies, but certainly has to work a long time to actually clean up our lab. So here you see TidyBot that is basically using an LMM to parse user preferences about where objects in this user's space basically go. So it can toss, pick and place, or put things into drawers to finally then having every object at the place wherever the user wants it. So if you're interested in this fun work and how we used a large language model in a slightly different way than what I talked to you before, you should check out this work that is called TidyBot, where we use summarization of large language models to achieve generalization in robotics. And we only achieved this generalization from very few user-provided examples. And yeah, so just to conclude, I think large language models offer new and more open-ended ways to plan robot actions, especially for long horizon tasks. That's very exciting. And the key insights about the works I showed you were that LMM plans can be wrong, as you know, but they are verifiable if you have a library of learned skills. And summarization is an effective way to achieve generalization in robotics. So thank you very much for your attention.
Thank you so much, Jeanette, for a great talk. Maybe we have time for like a couple short questions. If anybody in the audience have one, please come to the mic. If not, in the meantime, I'll take my chance to learn something that I was curious about. You didn't mention this, I think, a lot, but I noticed that some of the results or some of your training videos looked like they were done in simulation, and some of the results were in real, which is great. But I was wondering in your work, how you are dividing these two worlds and how you reconcile them, and if you really think we should be investing in simulation or more on real. What are your thoughts on that?
Yeah, that's a very good question. I think we need every person on deck, meaning like we need to be able to learn from simulation, from real world data, and from videos as well. And in fact, in this works that I've shown you, most of the learning was actually done either from videos or in simulation. Or in the case of TidyBot, we actually had primitives where there was no learning involved at all. But I think simulation is pretty necessary, but I think it's not possible to replace learning from real world demonstrations, but it can certainly get you at least pre-training. You also, if you're smart about maybe choosing certain action spaces or how you represent the input space, maybe you don't use pixels, but you actually have an object-centric representation. I think then, especially policies that you learn in simulation, they actually transfer much easier to the real world. So that's a lesson we have from STAP, the work that I proposed in the middle, but also for text to motion, where we've basically done that. We learned all the policies in simulation and then did like zero-shot transfer to the real world. Yeah, so I think there's not one.
Any special
bullet,
tricks for that sim to real transfer?
So depth always helps, right? Like depth as a perception modality, I think, is always easier to transfer from. Again, like since I'm talking to the CVPR audience, I can tell you we're trying to use the state-of-the-art 6 degree of freedom pose estimators for objects that are supposedly out there and are great. I can tell you they are not great. So there's still a lot of work to be done, maybe on new data sets, right? They are not working out of the box. So that's really unsolved problems that we are continuously running into in robotics, where it's really miserable. So yeah, please, people, work on that. I tell you, it's not solved.
Please, you have homework.
Yeah.
Do you have online? We're on time. Okay, we're running out of time, but I'm gonna ask you to thank Jeanette one more time. And thank you so much for attending from over there. And we're gonna move on to the next speaker. Thank you.
Thank you.
You just present directly on Zoom. You share.
Oh, I'm not even on the projector. It doesn't.
You will
delay.
when you share your screen on Zoom, it will show up on the projector.
The videos are not good because they go through Wi-Fi and everything.
It has been working.
Okay, yeah. Okay, let me try that. Yep.
Ah,
Interesting.
we will make you host. Yes. Okay. 1 second.
Now. Yeah. Okay, great. I think Alexander was going to.
Yeah, I'm going to introduce you.
Okay, let me get running.
Hey, my name is Alexander. I'm one of organizers. I'm from Meta Research, and I'm here. Have pleasure to introduce Dieter Fox, who has his PhD degree from University of Bonn, Germany, and he is a professor in Allen School of Computer Science and Engineering at University of Washington, where he leads the Robotics and State Estimation Lab. He's also senior director at robotics research NVIDIA. And his research is in robotics and artificial intelligence, while focus on learning and estimation applied to problems such as robotics manipulation, planning, language grounding, and activity recognition. Please welcome Dieter Fox on the stage.
Thank you. Hi, everybody. Thanks a lot for coming. I will talk about our work. The first word says it already, toward foundational manipulation skills, where the idea is that in robotics, we actually there's also, for example, another workshop going on pre-trained visual models for robotics. And I believe for robotics, what we really need still is manipulation skills, which are things that a robot can just execute in the real world, and hopefully in a broad range of settings, and also different locations, different labs, and things like that. First, to put this in context, there's, of course, a huge amount of work going on in training and benchmarking in these 3D environments. Of course, that's what embodied AI is mostly about. There's many of these simulators kind of abstract away some of the, let's say, the core robotics aspects, meaning that, for example, they are not physically extremely realistic. They focus a bit more on photorealism or on having longer term tasks, more complex tasks. But often, again, the physics are abstracted away in the sense of that the robot just needs to identify whatever object it wants to pick up, and then suddenly it appears magically in the hand. There's some work, like especially the many skill work, and some work also the NVIDIA, where actually the physics simulation is pretty accurate. But even those works are kind of focusing more on benchmarking rather than actually saying that if your agent does well in this environment, it's also going to do well in the real world. So the sim to real aspect is not a focus of these kinds of work. There's two views on how we can kind of generate the data that makes robots hopefully at some point succeed in the real world. And the upper one is work that we were involved in several lines of that, where the idea is like a dedicated sim to real effort, which means how can we train robots in simulations such that the policies or the visual perception, things like that, transfer to the real world. I'll give you some examples of that in this talk as well. And then there's another view where people argue that we can't train it in simulation. We have to generate the data in the real world. Some examples here, also, especially, for example, the Google team has done some very major efforts on many hours of teleoperation of robots in the ARM farm and then training from that data. The advantage of this approach is, of course, that you don't have that sim to real aspect, but it just comes at a huge cost. And scaling that and generating really a breadth of data is going to be, I think, very, very difficult in the real world for these robots. And then more recently, of course, there's a lot of effort going on what we might call multitask transformers. I'm sure you all heard of the Gatto model. We were involved. I'll give you one example later, like this clipboard perceiver actor, where the idea is we train a single transformer such that it can execute or generate policies for multiple tasks. These are often specified through language commands.
or sometimes also through some other kind of prompting, like giving it a video sequence of what the robot should do. Another example is, of course, the Google model RT1 that they trained again on huge amounts of teleoperated data. And most recently, of course, we see a lot of work on leveraging large language models for that. One thing that should be noted here is that all of this work still depends on the robot actually being able to execute those things, right? The language model can only kind of generate the sequence of steps a robot should perform, and then it's still up to the robot to perform these steps, which is not a trivial detail if you're coming from a robotics perspective. But I think it's fair to say that the progress that's been made in these generative models, be it the vision model, language models, has been truly astonishing, right? I think nobody in this room can claim like 3 years ago they saw that coming or something like that, right? Or even 1 year ago, right? So I think it's really, really amazing what we see there. And I believe it will have very significant impact on even real robot task and execution and the visual understanding that they can provide to these robots. But at the same time, I think it's fair to say that these language models, for example, themselves are not gonna be able to solve the low level, let's say, manipulation skills that we still need for these robots. And if you follow let's say, the core robotics community, then it's really true that we still do not have any kind of broadly applicable skills for manipulation that can be used, for example, across labs. It's like every robot lab, when they start their manipulation projects, they put different things together and somehow get the robot to pick up stuff, but there's nothing out there that you can just, let's say, download and it works for you or something like that, right? And that's clearly something that's missing in order to elevate the research community so that we can do work at a higher level. And why this is so hard is, on the one hand side, Moravec's paradox, which says like the things that we always thought that are easy in the robotics context actually turn out to be hard, and the things that we thought are hard are not as hard as we thought. So for example, higher level reasoning, things like that are not quite as hard as we thought. However, these simple things that a human doesn't even think about explicitly, those are the things that are really difficult for robots, which means, for example, for me picking up this phone, I don't have to explicitly reason about how I'm going to move my fingers in order to pick it up. I just do it, right? Or opening a door or something like that. And it turns out those are the things that are actually extremely difficult. And the other key problem that we have, of course, is we don't have the kind of data that, for example, language models can be trained on. And what I mean by that data is not just large data sets, but if you think about language models from, let's say, robotics perspective, they're kind of trained via, you could call it behavior cloning, right? There's large sequences of data, and you get a portion of that sequence, and you predict the next words in that case that come up. And in robotics context, if we could generate demonstrations of behavior that we would like the robot to follow, then possibly we could train the same kind of models on this kind of sequential data, where now the robot input is a history of observations and controls, possibly a task description, and it just learns to predict what the robot should do next. Now, the key trick is we need the data in order to train that. So my key lesson or key takeaway actually from this big success that we've seen is that if we could generate data that has this nature, that it's suitable for behavior cloning and at a very large scale, then these transformer models should be able to also learn very complex manipulation skills. The key trick is now, of course, where are we going to get the data from? And I'm going to propose that, especially initially, simulation is a great tool to do so. The reason for that is the tools are getting better and better, more realistic from the physical side and also from the rendering side. And of course, it's significantly cheaper and I think also more scalable than real world data. Right. Another nice aspect, of course, of simulation data is that you can do benchmarking on it very thoroughly. Benchmarking in the real world in robotics is very, very difficult. And also in the simulator, we have access to privileged information, which means we know all the shape models, we know where the objects are and things like that. And we can use that to solve tasks that in the real world, we don't know how to solve yet. Okay, so in the rest of this talk, I'm going to first give you some examples of work that we've done on training some manipulation skills in simulation with focus on sim to real. And then I'll tell you a little bit about our ongoing work on how we try to generate a large scale data set hopefully on which we can train some broadly applicable manipulation skills. So, for example, object grasping is one aspect, of course, of this, where if you have a robot, have an object on the table or something like that, how should the robot pick it up? If you want to generate training data for that in simulation, actually with physics simulation, it's pretty easy. Let's assume you have a 3D shape model like this red object there. All you do is you just randomly generate many possible relative poses of the gripper, and then you feed that into a physics simulator, and you tell the physics simulator to close the gripper and then shake it. And then you can see if the object stays within the gripper, then that was a good grasp. And if not, then it was an unsuccessful grasp. You can do this, of course, in parallel on GPUs. And we did this here, for example, on almost 9,000 shape objects from the ShapeNet data set. So what you get out of this now is these 9,000 objects that are all annotated with relative gripper poses that have a high chance of succeeding in picking up the object. Okay, once you have that, you can now go and generate training data for a deep network that takes as input not the object model, but just a rendered point cloud, a rendered depth camera image, for example. And it's trained using these graphs that we generated in the simulator to output over the point cloud. Here you can see this on the right, the set of graphs that are possible in this scene. Okay, so it's just replicating what we've done in the simulator, but the key trick is that it's replicating it from depth camera data rather than from 3D models. Okay, and it turns out that works then more or less out of the box in the real world without fine tuning. Another aspect, of course, is you want to also be able to segment the scene. So, or scene, segment anything models, but we've done also quite some work on segmenting based on synthetic data. The nice thing about synthetic data is that you get the labels for the objects for free. And then you can train, for example, segmentation models such that pixels that are on the same object should be close in embedding space using contrastive learning. All right. And you can also do this across scenes. So if an object appears in multiple images, you can train the embedding such that it is similar in the embedding space again. We have done several papers. You can take a look at the details here. And then once you have that, you can now, for example, take a look at the scene where on the upper left, we can, for example, show the robot an image of an object. This is just RGB, not depth. And then the other two panels in here, they show two different views. One is from the robot gripper, which is on the right. And then the one in the middle is just from an overhead camera. So it can take the image that you show of the pan, for example, and then it segments the scene and segments out the pan that you actually worry about. And then based on that segmented scene, we can then also generate these graphs using the technique that I just described to you, also trained in simulation. And then the robot can, for example, pick up the object and get it out of the sink here. One interesting aspect is also you need to do motion planning for the manipulator, and that involves collision checking and all of that. We actually trained a deep network to do collision checking as well. It turns out that if you do collision check, here's just another example, for example, the fruit snacks, you just, again, you show it an image, and it doesn't have to be objects that are highly textured or so. So I think the next one you can see, for example, then, oh, we get the pen again. So it turns out if you do collision checking only on a point cloud, you might miss collisions because of occlusions. But in simulation, you can train a deep network to also do collision checking and detect collisions that are in occluded areas. And that turns out to be much more robust. And we use that also for the model predictive control that's going on the manipulator here. And it's pretty robust, as you can see here, across different scenes as well. Again, nowhere in here did we use real data for training. All the object, the segmentation, the grass generation, the collision checking, everything is trained in simulation and then transferred to the real world without any fine tuning even. And none of these objects are known. So we're not even aiming here at, let's say, doing object pose estimation, right? Like all of this is operating on the raw point cloud data so that the robot can do this for arbitrary objects. Another area that's actually relevant instead of just pick and place are these industrial kind of tasks. NIST came up with this benchmark, for example, this is the version we're looking at. There's a more recent one, but the idea is in industry, there are often these very tight margin where you have to kind of place a pack into a hole or insert connectors and things like that with a manipulator. And it turns out that people used to work on this only with a real robot, simply for the fact that there were no simulators out there that were actually accurate and precise enough for these kind of tasks to simulate them. Before our most recent work, actually, this was kind of the best work out there, where you're simulating kind of screwing this nut on bolt task. The problem is it's 350 times slower than real time, just because all the contact modeling and everything is actually very complex. And that beats the purpose of simulation, because you typically want to be faster than real time in order to train policies and things like that. So we worked with the internal NVIDIA simulation team, and we had that paper last year. We can now do 1,000 of them in real time. Okay, so you can see this here on a single GPU. We can simulate 1,000 of these tasks. And once you can do that so quickly, you can now use it also for training policies in simulation. Okay, again, beforehand, that was not possible because there was no simulation out there on which you could train your policy. Okay, and once you train the policy in simulation, we now have a paper coming up at RSS where we show that actually we can transfer these policies to the real world. Okay, so we can train these context-rich tasks in simulation and transfer them to the real world without any additional fine-tuning. Okay, and there's also, this is not, I would say, a finished piece of work. We're still improving that. And we're also looking at adding touch sensing into the simulator, so you can do touch-based control for that. One last example I want to give you is this kind of for a more dynamic task and context-rich task is dexterous manipulation for this in-hand cube rotation. OpenAI were the first ones who did this, and they needed actually a very major compute environment and also setup for their hand. We're now able to train this significantly faster on a GPU, and it transfers actually very well to the real world. So on the right-hand side, you can see the robot executing a policy that is purely trained in simulation. Okay, and the key tricks are, what you have to do is, of course, the right kind of randomization on the visual data, randomization on the physics parameters. But if you get the right randomization parameters, then it transfers actually pretty well to the real world. Okay, so these were just some examples that I hope convince you that there's a chance that we can actually train robots in simulation and then succeed in the real world, which is for us the key aspect. We want them to succeed in the real world. So now where we want to move is, rather than looking at these small individual tasks, we would like to train to generate data that captures a more variety of tasks that we would like a robot to execute. The specific here is for object rearrangement in these cabinet style environments like a kitchen or so. This is our robot. We just got it about a bit more than 2 months ago. Caveat, this is a mock-up. We put it in this position to take the picture, just because we don't have the controllers, all of them up and running. It kind of takes a while to get this, put all of this together. But what we want to do is we want to train skills so that, for example, this robot, you could just say, hey, open that drawer down there, right? And you indicate what it should open just by, for example, maybe either clicking on a single pixel somewhere on the drawer so that the network knows what is meant, right? But you could also imagine you have a bounding box or a segmentation mask or a language model on top of that. And then you should be able to just say, hey, open that door, right? And the robot should just, based on the perception data, know where the handle is and then open it with the right articulation. In addition to opening, you should be able just to tell it, hey, close that, retrieve this object, right? Get it out of the cabinet or pick it up. You should be able to say, hey, place the object down there. And then you could imagine inserting and unplugging an object, right? So this is actually a very small set of skills, but I think it would be super helpful if we had robots that could actually execute those robustly in the real world. And also in a way so that, for example, if you start your robotics lab, you kind of download those skills and hopefully they work for your robot too, right? Now, This transfer across robots is something we haven't really looked at yet, but you can imagine in simulation we might be able to do this, right? So these are the kind of skills we want to train. And the question is, where does the data come from in order to train them? So we set up first, we're generating scenes synthetically and procedurally. So the key aspect of these scenes is that they are physically realistic, which means they work with a full physics simulator. And the nice thing, of course, in simulation, if you can do one, you can do many, right? So we'll generate many of these, let's say, kitchen-style environments and randomize kind of the configuration of the assets and change the sizes of assets and things like that. We can also then, of course, put objects in there for the rearrangement tasks. And to make them look more realistic, we're looking at using, of course, diffusion models in order, like if you look at the 4 kitchen models here on the left, these are all kind of color textured using the text fusion work by Sanja Fiedler's team. The key trick is, or the interesting aspect here is that it's not sufficient to generate a pretty looking kitchen image, but what we want is we want to generate images that are consistent with our physics assets, right? So that, for example, the handle in your image should be where the handle of your physics door or drawer is. Okay, so that is why we can't just generate 2D images, but we're here actually generating textures for the assets. Okay, and on the right side, you can see some of the textured objects. And the idea is that that way we will hopefully be able to generate scenes that look very realistic in simulation. And then the next step is, the nice part is Jeanette already told you everything about task and motion planning. Task and motion planning works really well in simulation. So you can then, for example, in one of these kitchens, you can just, whatever here, it should put the 2 objects onto the countertop. And we can automatically generate tasks and solutions for them in simulation. Now, if you look at how this arm is moving, this is kind of what state of the art typically does these days. If you ever download Move It or one of these tools, that's the kind of motion they give you. The problem is that that is not well suited actually for behavior cloning, because you want the robot to move in a way that is much more consistent and also, of course, at least closer to optimal. So we developed a tool that's called QRobo that is GPU optimized motion generation. On the left, you see 2 examples for what a standard, I would say, bidirectional RT with shortcutting or so would generate. And you can see that those motions are not pretty, I would say, right? They're very convoluted. So in QRobo now, we can actually generate motions that are significantly more kind of natural and shorter than what you would see, right? The nice thing about that is it's fully GPU parallelized, so we can run it on a cluster in parallel on many tasks. Therefore, it's significantly faster, and the motion it generates are also much better. So we're going to use that in this training generation pipeline, again, where we first generate kitchens, we generate placements for objects, we're going to generate tasks. We use task and motion planning in that tool to generate actual motions for the robot that then execute these tasks. And then we can, once we did that, we can, of course, generate from these examples, we can also generate sequences of what it will look like from the robot's perspective. So this is a robot, for example, with 2 wrist cameras, right? And also a head camera. So we can then generate both color and depth information for that. And then we are kind of in business, right? Because let's assume we can generate, let's say, 1 million of these. And these are demonstrations of how a task can be solved. And now we can do behavior cloning on that in order from the data that is available to the robot and transfer that to the real world by adding also the right kind of randomizations to them, right? The one thing that's missing is, I want to give you a brief idea of what specific model we want to train. This is a multitask transformer that we developed and it had a paper on call last year. So the idea is now, again, we're going to generate all these examples and we're going to use them to train a transformer that then takes as input this image data and somehow generates, for example, the right motion for the robot to open, close doors and drawers, pick up objects, place objects, and hopefully in a variety of different environments, okay? So the idea is that we feed this in, and then one thing you could do once you generate that data is, of course, you can feed that just into a big single transformer that does the whole motion policy generation at, let's say, 10 Hertz or something like that. And we're going to try that. I believe that what might be a bit more promising in this direction is actually a two-level approach, where we're first going to feed the data into a transformer that generates kind of a target where the gripper should move in order to, for example, open a door. And then that gripper target is being fed to a lower level policy, a motion policy that then operates, for example, at 1000 Hertz or something like that. Okay, so we want to have a two-level approach where the upper level is a bit more semantic visual reasoning, and I'll tell you how we do that. And then the lower level is the motion policy that actually executes it, rather than a single transformer that does everything. Okay, and the specific network we're looking at is based on perceiver actor. Some of you might have seen that, but the idea is as follows. It takes as input a voxelization of a 3D scene, like here on the right, and it generates as an output where the robot gripper should go in this 3D scene in order to execute the task. Okay, the input, in addition to the 3D scene, is also a motion command or a task like open the middle drawer. Okay, I'll get you to take a look at the paper if you want to know more details. Let me just give you one example for how this works. So let's assume the task is put the tomatoes in the top bin. And in this case, it's all about training from just very few examples. But this is then how this works. On the right side, you see now the voxelized input to the transformer. And along with the task, put the tomatoes in the top bin, it's going to generate a 6D gripper target where the gripper should go in order to achieve that task based on the demonstration. So it's just doing behavior cloning, like transformers are good at, right? And then the robot moves there, we feed that back into the transformer, and then it generates the next gripper pose, which actually then goes above the tomatoes and grasps the stem. We feed this back into the transformer. So this is kind of the high level reasoning I just described, right? It generates now the next target for the gripper. And in between, there's always a motion policy that moves it. Okay, and here in this case, for example, then, because put the tomatoes in the top bin, it just moves it over there and then drops it up. Okay, here, let me give you some more examples. What you see is all these examples were trained from only 53 demonstrations. Okay, so the interesting aspect here is, again, it's doing it in full 3D. Prior work that we did, like clipboard or transporter networks, only was able to do like top-down 2D. This is full 3D reasoning here. So for example, put one lime in the bottom bin, you can see that the gripper actually has to rotate and things like that. So we're reasoning about the full 3D rotation. And you've seen the tomatoes in the top bin. Now the limitation of that work, first of all, it's really aimed at training from very few examples. Okay, but it can do, you can see it actually can do quite a variety of tasks already. And what we want to do now with this data that I told you that we generate for these simulated kitchen environments is we want to train it on 1 million examples rather than on 53, right? And then the idea is, as we know, transformers are really good at scaling with data. So we then hope that the network will be able to generate kind of these kind of policies or motion gripper targets, but in a realistic kitchen setting environments. Okay, and in order to scale this up, also we developed a more efficient version of the same system. So rather than reasoning about these 3D voxels, which is computationally not very efficient. So for example, training the full perceiver actor transformer took 2 weeks because of all the randomization we had to do and things like that. So with this one, instead of reasoning about a voxelization of the scene, we're generating a point cloud and then render the point cloud into multiple viewpoints. I think yesterday, some of you might have seen Philippe Isola gave a talk on a system called Mirror, which has also this idea of rendering views into a scene. And then the advantage is that, for example, the transformer doesn't have to reason about 3D voxels, but it just has to reason about individual 2D views. And it turns out that that scales significantly better. So here's just the training curve we are seeing right now on, it's called RL benchmark. where the dashed line is the training curve for perceiver actor, and the solid line is for this new RVT model, which means we achieve the same level of perceiver actor rather than in 2 weeks, we are achieving it in a bit more than a day. So it's like 36 times faster than perceiver actor. And actually the top quality is higher than what we were able to do. So we're now we're going to use this to scale to this very large scale data that we want to generate. So with that, I'm going to come to the conclusion. I think, again, we've all seen how dramatic the improvements can be if we can generate very large scale data for visual and language kind of tasks. I think it would be great if we could leverage that in robotics as well. And I think simulation is a very promising way to do that for various reasons that we can also discuss further in the Q&A. And we are currently in the process of really finishing up this whole pipeline of the data generation in order to generate this really large scale data set and train our transformer models on it. So stay tuned for when we have the results, and hopefully it's going to work in the real world. Thank you.
Thank you, Dieter. We are running out of time, so we will have one question, unfortunately. Hope you will have an option to ask it more.
Yeah, later. People can just contact me. Yeah.
Great talk. A key theme in your talk was this idea of compositionality, building up fundamental skills that can be deployed widely. How important do you think it is to have sort of simulation environments that are as sort of large scale as a house versus, just having heavily randomized kind of kitchen sink like environments, having heavily randomized kind of bathroom environments, and then just building out, like training the fundamental building blocks in those like little mini environments versus big scenes? And do we finally have enough photorealism to the point where you'd rather use that GPU budget for physics fidelity rather than rendering fidelity? How does Dieter Fox want to allocate that GPU budget?
We need it everywhere. Buy more of them. No, but great question. Oh wait, now I forgot what was the first question. Actually, the composition. Oh yeah. It depends on what you want to do. So on purpose here, I focus on these skills, right? Because I think, in light of all the stuff that's going on and all the hype about the language models for planning and reasoning and long-term planning, I think people tend to sometimes forget that, but the robot still has to do this stuff, right? So that's why I focus on these lower level skills. And I think for those skills, there's no reason to have a whole house, right? What you need is a good simulation of just the stuff that is at any point in time in front of the robot, right? So you might even not need a full kitchen, right? You might just need, okay, there's 2 cabinets in front of it, and then you just have to be able to do these things there, right? We'll have to see how well that works. But if you want to go then a step up where you do more of the language and the scene reasoning and those kind of things, then clearly you need the more complete models. But at this point, we want to focus on just the simple little things down there in the manipulation side. Where to allocate? Yeah, that's a good question. I think on the one hand side, still all the rendering and stuff like that is still going to be pretty important, right? And have the right kind of randomizations on there, possibly with motion blur and all of that. We did a lot of that when we did this in-hand manipulation stuff. But I think it's going to be where a lot of the power, a lot of the compute need will be in the demo generation. Like you have to do all the motion generation, right? And store all of that, and then do the physics simulation on top of that. And then you have to randomize over the physics as well. So I think it's just a combination of all of these things coming together that will make it really hard. And the main effort of all this work right now is actually not so much in developing a new transformer model, but building the infrastructure that lets us just generate that data at scale on big clusters and store it and access it so that you can train on it in parallel and all of that stuff. So it's actually mostly, infrastructure building. Thank you.
Okay, we are now moving to the interaction channels or challenges portion of the workshop, after which there'll be a panel, and then more great speakers, and then finally the speakers panel. Okay, great. I'm presenting the ITHOR rearrangement challenge results. Okay, so the ITHOR rearrangement challenge is held in the ITHOR environment. This is our interactive simulator of indoor living spaces that prioritizes realistic physics, complex object manipulation, lots of interesting state changes, and even allows for multi-agent interaction. Jumping straight into it, I will now describe our rearrangement challenge. So in our challenge, there are two distinct phases. The first phase is the walkthrough phase, and then the unshuffle phase. In the walkthrough phase, the agent has to navigate and explore its environment and take down and record all of the positions and states of objects. Then in the unshuffle phase, the environment is changed. So here you see a cabinet being closed and a loaf of bread being moved. Then the agent is put into that shuffled environment. The agent then has to undo all of the changes that have occurred. So it records in the walkthrough and then undoes in the unshuffle. In our challenge itself, in our data set, we have around 10,000 distinct rearrangements, 120 unique rooms, thousands of object instances that can open, and lots of objects that can be moved around. Our challenge itself has two different variants. There is the two-phase task, which is just as I described. So first the agent is put in the walkthrough, then into the unshuffle and has to do the full task. And then we have an easier one-phase task. So here the agent is put into both the walkthrough and unshuffle phases simultaneously. It gets to see both images at each step. And of course, this makes it easier as it can see precisely that an object is not in the position that it should be. So here you saw that it will put a laptop into the correct position. Great. So, all of this is online, easily accessible. There's a really easy installation to install AI2 Thor. We have lots of starter code and pre-trained baselines, and a persistent leaderboard that anyone can submit to at any time. In 2023, so we had no one that beat the previous winners for the one-phase track last year, but we did have a new two-phase winner, which was a near winner for last year. So this is the tidying up novel rooms using Visio semantic common sense priors by Gabriel Sarh and others at CMU and UIUC. And they included a video.
We introduced Tidy, novel room reorganization using visual semantic common sense priors. Tidy is an embodied agent that can tidy up a never before seen room without giving any explicit a priori information about the scene. Tidy can map out a scene, detect objects which are out of their natural locations, and reposition,
which is very low volume,
to plausible locations within the room using only visual and semantic priors learned in a set of training houses. The first thing Tidy does when it enters a room is to explore the environment to obtain an obstacle map to use for navigation and to keep track of previously detected objects. Tidy maintains a 3D and an overhead 2D map of the scene by unprojecting the depth map to an occupancy grid and aligning it to a common reference frame using the agent's ego motion at each time step. We use the state-of-the-art deformable Dieter object detector to detect objects at each frame, which are then added to the 3D semantic map by estimating their 3D centroids. Point goal navigation in the 2D map occurs by greedily picking the action set that minimizes the geodesic distance to the goal location. Once the scene has been mapped out and explored, Tidy samples locations in the map to search for the out-of-place objects, which have been moved out of their natural locations. Tidy searches until it detects an out-of-place object, or a max amount of locations have been sampled. Tidy's out-of-place detector makes use of both visual and language features. The detector works by considering a detected object in the current view, for example, the sponge which is out of place on the stool here. Contextualized visual features are obtained by taking the query embedding of the deformable Dieter decoder output of the detected object. We obtain a relational language description of the object under consideration by inferring its relations to other objects in our semantic map, and then giving these relations as input to a BERT network to obtain a language embedding. The visual and language embeddings are given to a classifier, which is trained to predict whether the object under consideration is in a plausible location or not within the context of the scene. Once an out-of-place object is detected, Tidy navigates to it and picks it up. Then Tidy uses graph inference by bridging the out-of-place object features with a memory graph and a current scene graph to infer where in the current scene the object should be repositioned. We first build the memory graph, which we call the MEMX, by taking a subset of the training rooms and adding a node for each object instance in each of the rooms. The nodes consist of both visual features from the backbone of our detector and category embeddings. We add edges in the MEMX graph based on inferred relations between the objects. The MEMX graph provides instance-level contextualization for the out-of-place objects. We then build a scene graph from the current scene using object visual features and category embeddings using detections from images obtained while exploring the scene. The out-of-place object is given a separate node with its visual and category features. We bridge the out-of-place node to all scene graph nodes using a distinct bridging edge type. We then bridge the out-of-place node to the MEMX graph based on category. And we similarly bridge the current scene graph to the MEMX graph with the bridging edge. Information is passed between nodes in a differentiable manner using relational graph convolutional layers. Finally, the out-of-place node features are sent as input to a classifier to predict which receptive class the out-of-place object should be placed on within the current scene. The network is trained end-to-end using plausible object locations from the training houses. Once a plausible location has been determined, Tidy navigates to the receptacle if it exists in its semantic map and places it on the receptacle to reposition it. If the receptacle is not in our semantic memory, we use a visual search network to output likely locations within the 2D map for the object to exist. From the output, we obtain a set of search locations and have Tidy search in those areas for the object. We test Tidy on a novel task to tidy up disorganized scenes in the AI2 Thor simulation environment, where objects have been moved out of their natural locations by applying forces to them. Tidy must reposition the messy room to a plausible state without ever having seen the room or object configuration previously. We evaluate performance on this task by having human evaluators score the placement locations. Tidy outperforms ablative versions of the model that do not use one or more of the common sense priors on the human evaluation. Lastly, we show that without modification to Tidy's system, we can perform the rearrangement benchmark, where the goal is to rearrange objects in a room to a previous state. In this task, the agent is allowed to observe the room in its original state before the room state is changed. Tidy outperforms the current state-of-the-art model by a significant margin, even with noisy sensor inputs. We present Tidy, an embodied agent that uses visual semantic common sense priors to tidy up a room without any explicit low-level instructions or information about the scene. Please see our paper and project website for more information. Thanks.
Congratulations to the Tidy team. Great submission, and yes, good job, first place. Next, we have, I believe, Alfred.
Sorry, can you hear me?
Yes.
Okay, let me just share my screen. Can you see my screen?
Looks great.
Cool. Hi everyone, my name is Mohit and I'm one of the co-organizers of the Alfred Prestige Challenge this year. So one of the common themes across this workshop is, how do we come up with generalist agents? So we humans are not a single task species. We can acquire a lot of skills and we can operate in very diverse environments. And in the past 2 years, we've seen the rise of agents like Gato and Pami that can acquire a lot of skills in diverse environments. We've also seen the rise of open-ended agents like Voyager in rich domains like Minecraft. So can we do something similar for embodied AI challenges in this workshop as well? And this is something that comes up every year. Every time we organize, we try to think about how can we sort of combine these challenges together. And one of the reasons why we have this giant table on the website is so that you can see that there are common data sets, common action spaces, common observation spaces. But it's still very hard to train a single agent for all these tasks. Maybe in the next iteration of the workshop, we'll have a single agent that can solve all of them. For this year, we just decided to combine 2 pre-existing challenges. And specifically, we looked at challenges set in the Thor environment. So Thor, as Luca just mentioned, is an interactive simulator that has a bunch of rich household environments. So you can do things like rearranging objects, change the state of objects like cooking and cleaning. So we had 2 existing data sets in this framework. So the DialFred data set that came out in 2020, it consists of declarative instructions, which involve following a long sequence of goals. And there's another recent data set called Teach, which involve dialogue-driven interactions where you have to go back and forth with a human. So let me just give you an example of each of these tasks. So in DialFred, you're given a high-level goal, like put the green bottle in the cabinet under the sink, but you don't know where the green bottle is. So you have to follow the instructions, like turn around so you're facing the toilet. And once you see the green bottle, you can pick it up and then walk over to the sink and then place it. So this is just one example in the data set, but there's a lot of examples. There's 25,000 of these language annotations in the data set, and they're all set in very diverse environments. So there's something like 120 different scenes, which involves kitchens, bedrooms, and bathrooms. And they're all evaluated in completely unseen environments, which they've never been in before. Similarly, Teach is also set in the exact same setting as before. The main difference is that, as I mentioned, they're all based on dialogue interactions. So let's say you're trying to boil a potato, but you don't know where the pot is to boil the potato. So you can go back and forth with a user until you figure out how to solve the task. And there's something like 3,000 of these human-to-human dialogues. And there's roughly 12 categories of tasks in the data set. And again, they're evaluated in completely unseen rooms. And the idea is to sort of give it novel dialogues and figure out how to solve that task in that setting. So we had these 2 pre-existing data sets, and the key challenge this year was to kind of train a single agent for both these data sets. We've actually been running the DialFred challenge at the Embodied AI workshop for the past 2 years. But this time we kind of combined it with Teach so that you can actually train a single agent for both of them. And that's exactly what the winning submission did this year. So without further ado, the winner of this challenge is Yonsei VNL, and they're gonna present their approach now. All right, take it away.
Hello, everyone. My name is Jonghyun Choi from Yonsei University. And thank you for the great introduction, Mohit, about this challenge. So we're gonna describe about our approach called ECLAIR, the Event Cognizant Language Interaction Robot for the Generalist Language Grounding Agent Challenge, which combines the DialFred and Teach. And here is my teams. All right, so the current state-of-the-art embodied agents for these challenges are usually using this egocentric RGB images and creates a depth map out of it and uses the object mask to interact with. And they create this semantic spatial map so that they can navigate the space more efficiently rather than just learning the RGB images and depths on the fly. But these new, these state-of-the-art approaches usually ignore the objects that could move. So we call it event. So this state-of-the-art only maintains the obstacle areas and object positions and their classes, but they ignore the situation changed by the agents and agents action that is done, which we call events. So because of that, the performance drops by interacting with the irrelevant object because the objects are changed in their state. So we propose to remember the moved object and their mask that are not occluded. So before we dive into the details about our approach, we have to explain a little bit about the state-of-the-art approach and how we modify it to tackle these both challenges in DialFred and Teach. First, we create a semantic spatial map following the 1 and 2, the film and the prompter. That is a state-of-the-art in leaderboard in DialFred. And we use the semantic spatial map for the better navigation by constructing a map to help the agent efficiently navigate to the desired location where the target object is located. The predict and depth and object mask on the way. And we construct the map with the navigable area and object locations, discrete navigation, and object enlargement to make the agents avoid the obstacles in the way. And more importantly, to tackle both challenges in Teach and DialFred, we customize a template for generating the sub-goal plans for the declarative statements for the DialFred and the dialogue style instruction for the Teach in a single model. So next, we're gonna explain about the event memory that we are proposing. So the event memory consists of two components. One is monitoring the object position. We call it MOP. They record the location of the relocated object by the actions that is predicted by the agent. And we track the object to move location to help the agent efficiently complete tasks as their state changes. The state here, the moved location during the interaction by improving navigation and interaction with the object in different locations. And also we have this FPM, the fallback to previous mask, to utilize the previously obtained object mask without occlusion, because when you interact with the objects are usually occluded by the other object, which is a plate or some other bigger obstacles in the middle. So here are the benefits of the proposed components. Using the MOP and FPM, we improve the performance from the state-of-the-art prompter's performance, which is 45 to 50, and FPM contributes roughly 3%, and MOP contributes roughly 2%. And combining them, we have a synergistic effect to achieve the 50% test unseen success rate in the DialFred challenge, and Teach TFD validation unseen performance to 13.23. With that, we got first place in the DialFred and both on Teach by outperforming by large margin the previous approach of Film and Jarvis. And thank you. And if you have any question, we will have the QA session after this. And thank you very much.
Great. Next is DialFred, for which we have a video.
Hello everyone, I'm Xiaofeng and I'm glad to present the DialFred challenge. DialFred is a dialogue-enabled embodied instruction following benchmark. The motivation comes from the fact that it is natural for humans to seek assistance from others when facing challenging tasks. Similarly, for embodied instruction following agents, when given some ambiguous instructions, it should also actively ask questions and use the additional information in the answers to complete the task. As an example, given the instruction to move to the kitchen table and pick up the knife, the agent ends up finding 2 knives on the table. In that case, the agent can check the appearance of the knife to better understand the user's request. DialFred is an extension of the AlFred dataset. On top of AlFred, we perform an ontology extension to increase the task variety. We split the subgoals in AlFred into several atomic actions and merge these atomic actions in a meaningful way to get new tasks. As a result, we are able to obtain 25 types of tasks. For each new task, we perform instruction augmentation to ensure the language variety and add some ambiguity in language. To help the agent resolve the ambiguity in the instruction, we define 3 types of potential questions it can ask to get additional information about the task. Given an instruction, the agent can ask about the location or appearance of object in the instruction, or its movement direction. To learn when to ask a question, or which question to ask, we collect 53K human QA data. Each data session contains a question selected by the human annotator during an embodied instruction following task and the corresponding answer. We also build an oracle that uses the ground truth information in the simulator to generate answers. As a result, the dataset in DialFred contains 34K tasks in the training split and 2K in the validation split. For each task, we include the expert demonstrations, human instruction, human answer, and oracle answers. For this year's DialFred challenge in the workshop, we released an additional test set containing 1,000 sessions. These data sessions do not have expert demonstrations. The challenge is open for submission on eval.ai from March the 10th to May the 19th. Each submission is evaluated by the average success rates in the 1,000 test set missions. As a result, we received 20 submissions from 2 teams, and Team KO achieved the highest success rates. Let's welcome the winning team to present their approach.
Hello, everyone. My name is Kome Sugiura. I'm a professor at Keio University. So our motivation is to build multimodal language generation and understanding for domestic service robot, such as Toyota HSR shown in here. So these are my robots. So that's why we participated in DialFred because the focus is instruction following with dialogue. So there are many related challenges and solutions, and I'd like to emphasize that many robotics people also interested in physically embodied AI, and such as RoboCup at Home and World Robot Summit. And since the collecting data from robot, including dialogue, is labor intensive, I think it's very promising to use simulation for collecting data. So by the way, I'd like to thank the organizers because I'm also have been organizing RoboCup at Home for 15 years, and I know it's tough for organizing challenges. Thank you very much. So these are main key points of our method. And first of all, we introduced moment-based adversarial training for DialFred. And this adds adversarial perturbation to language, image, and action. And second thing is simple. We use a parallel cross-modal feature extraction mechanisms to language embedding space and also visual embedding spaces. So here we use a clip, text version of a clip and deburter, which is a more robust than BERT. And what MET does is to add adversarial perturbation to embedding spaces. And let's say the delta represent the perturbation, and this is the update rule for the perturbation, which is similar to Villa, which was proposed in Europe's 2020. And the different thing is the update of delta is calculated like this, which is a exponential moving average of scaled gradient of loss function with respect to the delta, divided by the squared EMA of scaled squared gradient. So this table shows the quantitative results. So actually, the baseline is simple, and also our method is simple. So it's not very high, but we confirm that our method MET helps to improve the result by 3%, and also introducing parallel cross-model encoder improved the performance. The important thing is that the test set is not published, so that we had to, and also the submission time is limited to 10 submissions per month. So we had to divide the data set into a pseudo test data set and pseudo body test. Okay, and these are qualitative results. Our method successfully moved to the desk in the left example, and also in the right example, the method brings the robot to the floor lamp and power on the lamp. Okay, here is the conclusion. And also we published the code, and hopefully it will be the next baseline for the next DialFred challenge. Thank you very much.
Great. Next is Maniskill ahead of me.
Yeah. Hi, can you hear me? Okay. So I will start. Hi, everyone. My name is Jiawen Gu, and I will present our Maniskill 2 challenge here. Yeah, I'm glad to present today. And today I will first give like introduction of our Maniskill 2 challengers, which contains like 3 tracks and how we evaluate the submissions. And then I will announce the winners. And finally, I will give some summary of the solutions. So, and on the right side is our barcode, and you can check our website as well. Okay, let's first give an overview. Yeah, Maniskill 2, first it is like unified benchmark for generalizable manipulation skills. Generalizable manipulation skills, which can be composed to solve like long horizon tasks, are one of the cornerstones of embodied AI. So we try to address the critical pain points for researchers in our Maniskill 2 benchmark. So here we can see that we propose like many tasks. And first, it is easy to get started. So Maniskill 2 is pip installable. So starting from a clean Python environment, you can see a robot working in 1 minute. And second, we can like our benchmark contains like diverse tasks and objects. So Maniskill 2 embraces a heterogeneous collection of out-of-the-box task families for 20 manipulation skills. Besides, we also support like fast visual IO visual IO experiments. MenSQ2 provides blazingly fast visual IO environments using our asynchronized rendering system. We also natively support like 3D point cloud observations. We also provide large-scale demonstrations. MenSQ2 verifies that all tasks are solvable and has connected over 4 million frames of demonstration. We also have an interactive GUI, which is very helpful for researchers to inspect and interact with the environments. The users can click and to check like the coordinate frames, or they can like move the robot. Yeah, it is very helpful. Okay, in the Challenger, like we include 12 rigid body tasks, like including pick and place tasks, precise assembling tasks, and articulation-based tasks. We also have like 6 soft body tasks. So here are some examples of our rigid body tasks. Like pick single EGAD and pick single YCBs are both pick and place tasks, which require the robot to pick an object up and move it to the target position. And for the plug charger, it requires the robot to precisely manipulate the plug and insert it into the charger on the wall. We also have like 4 underactuated like manipulation tasks. So like move bucket, push chair, open cabinet door, and open cabinet drawer. Here are some examples of our soft body tasks. Like pour, like robot need to grasp the bottle and pour the water into the target beaker. Yeah, we have 3 tracks for our challengers. So the first track is imitation and reinforcement learning track. It is for the solutions that utilize the imitation learning or reinforcement learning to solve rigid body environments. And the second track is no restriction track. So people can use like classical robotic pipelines like sense, plan, act framework here, or you can write some like heuristic to solve the tasks. And similarly, we also have this no restriction for the soft body as well. Our evaluation system is based on the Kubernetes. Each submission contains a user-submitted Docker image and is evaluated by a pod. And we have 2 stages. And the first stage is like a public leaderboard. Users and the participants can compete. And at the second stage, the first stage leaderboard is like closed, and we will evaluate it on another like set of episodes. And finally, we will finalize the winners based on the stage 2. For the evaluation protocols, the evaluation metric is the average success rate across all tasks. The maximum episode length is like 200 for the rigid body tasks, while that of soft body tasks varies from like 200 and 300 or to 315. We especially focus on the generalizability. If a task has asset variations, we evaluate on 2 sets of episodes using training assets and the held out task assets separately. Okay, next I will announce the winners. So we have like 5 teams participate in our challengers, and here are the top 3 teams. In fact, they, each team like keep the positions in all the tracks, and let's give the congratulations to those winners. And we will have the award ceremony. And we will have the award ceremony later. Okay, next, let me give a summary of the solutions. So the top teams use point cloud observations and the task space controller. And demonstration augmented policy gradient is the dominant method for the rigid body tasks. And since our benchmark focus on generalizability, so we show some comparison here, like RL policies generalize quite well for pick and place tasks. So we can see the performance is almost the same for the test assets. And RL policies outperforms our sense plan act baseline, which can only achieve like about 43% success rate on pick single YCB train set. Yeah. Besides, there is like larger gap between teams on tasks that including the articulation. So we can see the top team has achieved like much better success rate on the term for set test assets. And here we show some like successful episode of the top team. Yeah, their policy is based on the reinforcement learning and the imitation learning. So we can see like they can grasp the objects quite well. And here are some example, even for the precise assembling task like plug charger or the term for set tasks. Yeah, here are the examples that they can open the cabinet door or drawer. Another examples for move bucket and push chair. Okay, so the key takeaways are that like demonstration and interactions like both play important roles as many teams use the APG method. And our policy trained with object variations can generalize to unseen objects well and outperform the classical sense plan act framework. And the policies based on the point cloud observations shows great potential. Precise assembling and the actuated manipulation tasks are still difficult to solve. And last, I would like to thank all of the organizers. Yeah, so we can have this challenge. Yeah. And besides, I would also like to acknowledge the sponsors like Qualcomm to give the prize award and the Nautilus and the National Research Platform to provide the computing resources to evaluate the submissions. And yeah, we are glad. I mean, this is the first time for our challengers to join the family of the Embodied AI workshop. And the award ceremony will happen like at our RSS workshop. So yeah, maybe if you have interest, you can join them like join us on July 10th. Thanks.
Thank you for that great presentation, and let's give one more round of applause to all of the the rearrangement and interaction challenge organizers and winners. Awesome. So due to some sort of unexpected unavailability, we're going to skip the interaction panel. So that means we will have a 40-minute break. So at 4, Kristen Grauman will be coming with her presentation. And then there'll be a speakers panel at 4:30. And so until then, get some coffee and see you then.
spaces, meaning move around in them, and then also manipulate with human-centric objects. And so we're thinking about ways in which we can, narrow that gap between the experiences that we have in our daily lives and that we want to translate into robotic agents. And in particular, looking right at video as a raw source of human observation of all kinds of real-world action. And specifically first-person video, so a wearable camera where you have that egocentric, dynamic view of a person going about daily life, let's say, that's going to reveal so many things we care about for building intelligent agents, how people move in the environment, how they direct their attention over time, interact with other people, and importantly, how they interact with objects in the scene. So all this is, of course, present in video, and our job and the examples I'll give in this talk is to think about how to, get this rich information from the video and ultimately to robotic agents. So this talk then has the following structure. We're going to look at our steps in this direction, specifically looking first at video encodings. So one example I'll show is looking at first-person video to learn video language embeddings in a new way. And then we'll look at learning, again, video embeddings, but now caring a lot about viewpoint invariance to the extreme of mapping or bridging between ego and exo viewpoints. And then the second part, we'll talk about our efforts to translate things that we are picking up from video into our agents, who right now, full disclosure, are 98% virtual agents. But we'll see how real video can inform the learning of those agents and their behavior, both from activity context about objects that get used to achieve different goals, as well as down to the low level of dexterous grasping. Okay, so when I kind of look back at the structure of what I'm about to show you, there's kind of two parts here. On the left, we're talking about new ideas for learning video representations that are equipped for action, meaning they're trying to address things that you need to worry about when you want these representations to inform robotics. And then on the right-hand side, this is our attempts to start to move from these video priors to influencing the agent's action itself. Okay, so that's where we're going with the rest of this talk. And let's start with hierarchical video language embeddings. And here I want to overview in a slide this data set Ego4D that we released over a year ago and presented at CVPR last summer. This is a multi-institution effort from a number of academic partners and FAIR who came together to create this glimpse of daily life activity around the world. So 900 plus unique individuals wore cameras for typically up to an hour at a time, and they come from many different parts of the world, 74 worldwide locations, and altogether yielded 3,670 hours of this unscripted daily life activity content. And as you can see these little glimpses going by, you see that this is both solitary activity as well as social activity. It's a lot of interesting hand object manipulation that of course rings a bell for some of the things I'm talking here for human-centric objects. It's indoor, it's outdoor. And because of the diversity of the folks wearing the camera in terms of where they live, what their occupation is, you see really different visual experiences in this unscripted form. The other thing I want to emphasize about the data set, Ego4D, is its multimodal nature. So we're looking at the RGB. There's also audio. For a portion, there's 3D scans, meaning you can situate these video streams within a 3D environment that's been scanned with Matterport 3D scanners. There's IMU, there's small amount of stereo, also some multi-camera, money people in the same scene wearing their own cameras. And finally, throughout all the data, there's a modality of text that I'm going to use in just a second here. So these this clip is one of the ones we were just looking at, now played. I think you've got the hang of this one now. What I want to use it to emphasize is how much, when we look at video, we're really understanding more than the sequence of actions that are there, all the physical things that have happened, or whether we can name them or not, but we're also understanding, you and I, the intent. This is something we have to be able to translate to a robot to have this data be of high value. By that, I mean, for example, here, the intent is to make this food and to get the filling in and then to seal it with this sauce and then, get it all packaged up. I'm inferring this looking at the video, but look at all the things I know are not the intent. If he were to drop it and then pick it back up, the robot watcher would think, okay, there's a step where you drop it and then you pick it back up. And then, the fact that the paste is on the right rather than the left, I'm assuming is not significant, and so on and so on. These are all things I can get, because of my understanding of the intent. This is where we have to go with video representations for them to fuel an eventual robot. So let me show you how we're trying to start to achieve something, getting more towards a video encoding with intent and goals as part of the representation. For this, we'll rely on that modality I just mentioned for a moment, which is text narrations that accompany all of the Ego4D video. So you're looking at examples of it here. It's a play-by-play. Those white strings at the top, C is the camera wear, and it's saying, C unpacks the saw, C stops sewing the cloth, C removes the threads, he puts the threads, he grabs the thread. And so it's every action that's observed from the camera wearer point of view. Furthermore, on top of that narration is a video level summary. So for every 8-minute chunk of video, there's also a free-form language description of what that whole sequence was about. And that's a summary. So our idea is actually to look at these two in concert. And what we've developed and we'll present at the main conference this week is a hierarchical video language embedding learning framework, where the hierarchy is on the semantics we're getting from language. And the goal here is to let the intent come out of that summary. So let me show you what I mean. So here at the bottom, these are examples of narration statements, fetch the water, cut the onions, and so on, that have accompanying video clips. And some recent work has done some inspiring design to do contrastive learning on these, to come up with a representation for video, for language, where these pairs of things would be close. And that's a great way to push those semantics into the video encoding. Here's where we come in. On top of that, we would like a hierarchical embedding that says, pays attention to that summary text, which here across the longer video says, C made salad dressing. That's the goal. That was the objective that all these little steps are leading up to. And so what we want to do is link that what at the bottom there, the step-by-step actions, to the why, or which is the goal expressed in that summary text. So we see an opportunity here. You've got these two levels of granularity. And now let's see how we can put both of those together into learning a multimodal video encoder. At the child level, we'll do what I already described. So for every pair of the video and the text and this play-by-play statements, we'll learn the visual encoder and the respective text encoder that maps the appropriate ones close or far. Okay, close if they were paired and far otherwise. But on the parent level, here's what we want to do. We'll have that summary text over here on the right-hand side, like C was in a studio, he played piano. And from that temporal aggregation of the video clips in sequence and the text statements in sequence, we say that once those guys are aggregated into their encodings over here, we want that to be close to that overall summary text encoding. So in both cases, it's the same text function, FN, and we can apply it to summary language. We can apply it to the atomic action language. And what we're doing is stitching these things together and jointly training them so that both the goals will influence that clip level encoding, which is so much more local, and vice versa. The steps encoding can influence what we understand about that global or longer sequence of events. So we call this method HiRVL, hierarchical video language. And this picture from a t-SNE plot shows you a bit of what's going to be achieved by this embedding. So on the left, this is our model, where the big circles are the parent level summaries embedded, and the small circles are the child level narrations. And you can see how it's starting to bring together the same colored blobs because of their relationship that's been tied together through this joint multi-resolution learning. Whereas without that kind of relationship modeled and in the right-hand side, as the previous work would do, then we don't get that kind of structure from the embedding. So for time, I'm not going into details of the results, but I'm sharing with you this visual impression of how flexible and versatile this model has been as we try on different data sets and different tasks, which require longer form video understanding. Places where, just knowing exactly what you see and naming it is not enough. For example, long-term anticipation, knowing the next sequence of actions that might happen. That's the bottom left in Ego 4D, and many others too, where we're seeing really strong results, outperforming the existing models, using the same language and data set, even using the summaries without this kind of multi-resolution approach. And there's a poster on Thursday to check out more details here. All right, so this next example I wanted to give you, we just said that robots need to start to understand intent to make good use of human video and not just pay attention to the wrong parts. Robots also need fine-grained video understanding. So if you look at the video understanding literature, you might see tasks that are relatively coarse, very challenging and still very important in different applications, but things like knowing, are they knitting or are they mopping the floor? Whereas often in robotics, I think there's a need for much more fine-grained down to the manipulations of individual objects and how is this pouring action being executed, for example. So here's the domain we want to look more closely. Challenges, it's fine-grained, so these differences will be subtle. And secondly, coupled with this, we have the expectation of very wide viewpoint change. Okay, so we need to understand these fine-grained actions, knowing that the viewpoint at which we observe them is going to change a lot. In particular, here's one extreme change that we care a lot about, which is from exocentric to egocentric, or vice versa. So exo to ego, so exo third person, if I observe someone demonstrating, and ego, then I see myself doing it. And I want to be able to have representations that move fluidly between them, so have some invariance from these views, so that we understand how to map these actions back and forth. And this talk is motivated from embodied AI and the robotics side, but the same goes for augmented reality, where I would like to be able to have the AR glasses of the future that could help me understand how my own actions are relating to those of an expert, say observed in a video like this one. Okay, in general, viewpoint invariance here is the thing we need. So let me show you what we're exploring for ego-exo alignment for learning these viewpoint invariant video features. And this model will be a frame level video encoder that operates by trying to discover during training the temporal alignment from ego to exo. So ego stream on the top there, exo just below it. These are people playing tennis. One is, each is in a different environment. And the question is, during training, can we learn to align these such that we discover the association between the viewpoints, as well as the association of the different phases of the action? This won't happen for free. So like if you just took the off-the-shelf good visual encoding of either of these videos, the frame encodings would look like these pink and green dots. The thing that most relates to them is the other frames in the same viewpoint. But what we're after, and I'll show you how we can get, is an embedding where the viewpoint invariance is achieved. So a pink can look similar to a green because it has the same action. And where the traversal of the phases of that action are aligned over time. And that's depicted in this plot by the color shading where it's dark into light over time. So this is what we want to get. And so we're talking about a view invariant feature learning approach, of which there's other alternatives that in the literature. The thing that's so important about this problem setting and what we're trying to tackle that's new is that this data that we learned from should be unpaired. So there's a certain expense associated with having concurrent ego and exo views, certain limitation to same environment. We would like to be able to take unpaired ego and exo video from the same action, like the ones I'm showing, and then allow this view invariant learning. So the model we developed is to train feature encoders for any viewpoint. So it's a frame level encoder, and we use a transformer architecture to do this, where the key loss or the base loss is about the dynamic time warping. So we're taking training pairs of sequences from the same action, and we want to find the alignment between them that minimizes the dynamic time warping loss following the feature encoding. So that's kind of the base of the model. And then there's two key insights that we put together here. One is to make the encoding explicitly expose hand-object interactions. So if you think about how non-trivial it is to relate the ego view to the exo, I mean, just the visibility is very different when I see you do something versus when I watch myself do it. But there is the shared, in many of these manipulation activities, there is the shared object manipulation. And so that's the thing that despite the different background and the different parts of the body that are visible, that should be consistent. So we expose that explicitly to the feature learner by encoding not just the global frame, but also the hand and object regions from an object agnostic hand object interaction detector. So that's part one of this. And then the second insight is a regularizer that is self-supervised. So if you had an ego stream on the top, exo here during training, same activity, but different person, different object, we would say that the loss to align those two should be less than the loss if I were to reverse the frames of the exo sequence. Okay, so for this, for these two sequences, let the loss of aligning these two be less than the loss of aligning these two right here, because this one's backwards in time. And so it shouldn't agree as well with the forward instance of the exo viewpoint. Okay, so two kind of technical insights we put together with this feature learning framework to get view invariant features for video frames. And now we've tested this on 4 different couplings of ego exo data. So taking, as you see listed here, from CMU, from H2O, from EPIC and HMDB, and then some tennis video captured by ourselves as well from the ego view, as well as the third person and UPenn actions. So here are 4 different ego exo data sets that are all action specific. So you'll note the top left is breaking eggs, top right is pouring, etc. Actions of the fine grained nature that we want for learning objects, robot object manipulation. And the other thing to notice about these is the bottom row brings us into pretty good in the wild territory, because these are completely different actors, subjects, different environments, but same action. And so this is something we want to study. For all the data sets I'm showing you, we treat them as unpaired. Okay, that was the thing. We don't have synchronized data. CMU actually offers it in that data set, but we won't use that as a constraint. Part of the contribution we made here too is action phase labels. So during training, no such labels, but when we want to evaluate how good is our alignment, it's very useful to have these phase labels that say, okay, well, here's where the water exited the pitcher. Here's where it started to, the hand started to be removed, et cetera, like those different phases. And so that's what we evaluated based on action phase labels for here. Don't worry about the number of values I'm showing you is 4 data sets, A, B, C, D, and our method on the bottom row of each of these, looking against important baselines from the literature. So methods that do self-supervised learning with paired ego exo data, or that do, but assume it's paired, or that do alignment-based, temporal alignment-based feature learning, but don't account for these dramatic viewpoint changes. And what we see here is good flexibility, consistently across those different 4 data sets and across those baselines I just overviewed, we have, consistently higher results. So most visually, we can look at best visual examples to look at alignment that we achieve. So here's an unaligned pair from breaking eggs. So you can see an ego view on the left of someone and then an exo view of someone else on the right. And you may have seen that, it's definitely they're both breaking eggs, but the timing is not the same. They take it at different paces. There's different lengths to the action. Here's what we get when we align using our encoding. And so you might see how just by doing what we're doing here is nearest neighbor from the learned encodings from the left, every frame on the left to its nearest neighbor in the exo view. And you might have seen how the exo view kind of paused for a moment at the beginning, so till they were in sync, and then they just kind of phase by phase were keeping in line, which is really cool, right? To think about being able to bring demonstrations from different viewpoints and different people into alignment in a way that's consistent for the progress of the activity over time. And sure enough, if we look at the embeddings that I already kind of motivated before this learning, we have clustering based on viewpoint. After this learning, we're having alignment over time for the action phases, as we saw in the video, as well as for the view invariant measure of the frames. And how do you see that? That's because the pinks and the greens are together rather than clustered on their own. Here's another similar example. Our output is on the bottom. I'll play it one more time. Input at the top left, and then our synchronized version on the bottom. It's very quick. There we go. And you can see that tennis, the motion of the racket being aligned. All right, so then finally, I want to talk about examples where we're looking at what we learn in video as something we want to influence the agent with. And we'll be doing this in simulation, first at the higher level of abstracted action spaces, such as put down, pick up, and move. And that's with activity context. And then we'll look at dexterous grasping briefly as well. All right, so I've already said robots need to understand intent. So we talked about that feature learning. I said they need to understand fine-grained actions in a view invariant way. And then the final, need I'll talk about today is learning complex sequential behaviors. So visual semantic planning as an example, if we say to the agent, wash the dishes, there's so many things that have to happen, right? You have to go to the right place, you have to get the right objects, you have to have them in the right combination. So, washing the dishes means you're at the sink, you're holding a sponge, there's a dish there, it's dirty. The faucet can get turned on, you've got a sponge, you've got a soap, etc. Like, we know that, there's a really high inefficiency of learning if we're not careful, because there's so many things that have to be just right, such that, if we're doing reinforcement learning, stumbling upon them is extremely unlikely. Any one thing that's broken there won't allow you to succeed in that action. So what the community does is, not just reinforcement learning, which, burns a lot of experience to try and find these good combinations, but also, imitation learning can help. So being able to steer a robot according to how it should move or what objects to use for a given task is helpful to improve sample efficiency. But our premise here is different. Inspired by watching people, but here watching people again through video, we want to know, can we discover what are those configurations of objects and object states together that tend to enable actions for people? And I say tend to enable because an important part of this work that I'm showing you next is it's task agnostic. So we're not learning a policy right now for one thing in particular from the video, such as you would do in imitation. Rather, we're trying to pick up good behaviors of useful things to bring together, such that progress will be made on many actions, many possible tasks. So people show us this, forks and spoons and water and sponge, et cetera, and sink all came together in this particular video. So can we pick this up from in the wild egocentric video and then translate that to agent action? And so that's what we've done, where we take the intuition that it's valuable to interact with some objects only when other relevant objects are nearby. So for example, if you're holding that frying pan and you bring it over to the book, there's not much that's going to change in life. But if you brought that frying pan to the stove, like, things can start happening. Of course, this is well known to us, but think about building up all these kind of combinations of compatibility of objects that are action enabling. This is what we can exactly get from video. So we take video, here we're taking an Epic Kitchens data set to detect active objects and interactions, build up statistics about which ones people are bringing together, no matter their task, and then find out, for any object, what its affinity is, not just for co-occurrence in the world, but for enabling human action. So pans do things with stoves and sinks, but not so much with a bottle and so on. And then we treat this as a prior. So when we have our action about in the world, or our agent about in the world, it's going to be, if it's learning a particular task, it'll be rewarded for that, but it'll also be rewarded for experimenting with combinations of objects that have high activity context from human video. And that'll just steer this agent to the things that are more likely to pay off for something happening in the world. Okay. And that's what we saw when we did this with visual semantic planning tasks with AI2 Thor, which are tasks like, here, cool something, or put something in a drawer. I'm showing 4 such tasks on the left there. And what happens is you learn faster. So we take a reinforcement learning agent that's trying to tackle any one of these tasks. And then we give it this video-based prior, and we get this purple curve, which means that for less total experience, success is climbing more rapidly compared to if we just had seen co-occurrence priors, or if we had earlier kind of exploration, like state-of-the-art exploration-based policies that favor trying new things or trying to reach new places in the scene. Okay, so then the last bit, let me just show you going down a level to grasping what we're attempting to do to translate what humans do to the agents. Here we're talking about a dexterous hand. So 24 degrees of freedom, very high, highly complex action space, but so attractive because of the similarity of the human hand, the complexity of actions that would be possible, and the suitability for human-centered objects that they need to work, we'd like them to work with. So here's what we've done. We took YouTube videos from How to 100 Million. It's a public data set. We extracted hand poses automatically in 3D using a model called Frank Mocap. And then we say, okay, this is the pose prior for good ways to hold different objects one at a time. So, you know, cups and hammers and mugs and teapots. And then we learn policies where the agent's rewarded not just for getting something off the table, so it's a grasping task, but also if it does so using a human-like hand pose. So that will also give, well, the intention is to speed up its learning, have better generalization, including with new objects. Okay, and for time, I'll go to show you examples. So finding poses of people, you know, how do they hold cups? Here's some examples that come out of the data to give us a kind of the mode of that pose. And then using that to train this virtual dexterous hand, we can compare the learned policy behavior of our model on the right to what you would get with adding imitation in the middle. Here we go. To a simpler prior just based on the center of mass on the left. And so here, this is what I think is important to note. You know, an imitation is definitely one way to go with using video to help our agents, but it can be rather task specific and brittle. You know, if we need to really mimic in a, you know, get to the inferred state and then mimic that kind of behavior, we have, you know, we have a higher ceiling of data that's required. Whereas here with this task and object agnostic type of approach, you have the possibility to approach new things still with that human-like prior, but in a less literal kind of imitation and mimicry way. Okay, here's the other example with hammer, different hand poses for hammer, and then our policy on the right, learning how to pick up hammers a bit more like a human. Okay, and this pays off in time spent and the efficiency of the learning. The blue curve is using this prior from video, getting a more successful policy with much fewer samples compared to the baseline, some of the baselines I mentioned. Okay, so I wanted to stop here then. I've shown you ways in which we can use video to inform about human goals and inform agent action, from the data to video embedding ideas to the final instances with building up activity contexts or hand pose priors from humans. Thank you for your attention. Highlighting the first authors from all this work here, and I'd be really happy to have any comments or questions.
So if anybody has any questions, please come to the mic. Otherwise, maybe I'll start with one from the online Slack channel. So your ego-exo alignment process sounds very similar to the field of visual place recognition, needing to find the same things at different times/view angles. What would you say are the key differences? And is there anything here that would could be used in a field like VPR?
Oh, okay. Yeah, so you're right. In video and visual place recognition, you also are very interested in viewpoint invariance. So they share that. I guess in place recognition, you're talking about a static place, typically maybe a building or things that you want to re-recognize in new views. And here we're talking about dynamic video and the goal to kind of stretch and compress video samples so that we can find where they align on their action phases. So I think definitely the two problems share the need for view invariance, and you know, maybe invariant feature learning that might happen for say local features for place recognition, would also be up against this paired and unpaired thing, but have the advantage of you can kind of generate samples that should correspond from same 3D object or same building, say, whereas over here, we're doing this from unpaired data, again, with where you don't have that as part of the, like, you don't have the ability to generate that in the same manner. So that's, I think, a big difference. Yeah. Yes, Rob.
Okay. Yeah, thanks a lot for the great talk. I had a question about the last piece that you presented. There is a need to retarget from human hands to robotic hands, and presumably you have kind of done that. I was wondering, and you also made a remark that maybe imitation is not necessarily the right way to do. And I'm wondering, can you say more
Sure.
on that? Or
Yeah. Sure. Yeah, I think what I was trying to express there is that in some ways, imitation is more rigid and more rigid on the data requirements than things we might try to explore that are, I think, more fragments of activity that humans do that and can be like reusable, maybe, I don't mean in multitask learning sense, but reusable as like composite, like composable, I guess. And I think like this is a possible instance of that because you're saying these are things I favor and it's a softer requirement, I guess, than saying like, I'm trying to reproduce the exact sequence that the humans used throughout the whole activity. Yeah.
So I guess my follow-up question is, did you try it in this setting and it did not work as well? And that's why.
Well, there's a baseline that's imitation. Yeah.
Oh, I see.
Yeah. So we were using that DAPG model for imitation, and that's why it's actually stronger supervision, and you could arguably, but for this was playing out better is what those results were showing, was using this kind of more localized prior about the hand posture solo. Yeah.
Okay, thanks.
Sure.
I liked your work on ego to exo alignment. I'm curious that the examples you had, like cracking eggs, that's pretty short an activity. Did you have examples of longer ones? And as you get an okay.
Not yet. No.
Not yet. Okay. I wonder for like even ego to ego, if you have longer examples of activities, if that makes it harder or easier to align things, if you have more phases to something.
Yeah.
Thoughts there?
Yeah. Well, it's definitely something we're very interested in, generalizing to longer actions and even untrimmed video, because you'll notice we do have this weak supervision at the least of, here's a instance of breaking eggs. So will it be harder or easier? I mean, I think harder once, especially if we're adding untrimmed, like if it was long, but still similarly like same action,
yeah,
maybe we expect less change, but I think the untrimmed is what's going to do it. But very interesting to, just you need a much even more robust way to calculate this alignment and discard portions and drop portions altogether, I would guess. Yeah.
Yeah. Thank you.
Thanks.
Awesome. Maybe let's all thank Kristen once more, and then we can start the speaker panel in maybe 2 minutes. If anybody needs to use the restroom, coming back. Yes.
So Luca, how are we going to arrange the got some people that we need to, and I think Faye is still remote.
Yes.
So we should make sure he's unmuted and has the ability to speak.
Yep, that's a good idea. Let's see. Sarah, if you want to. Okay, Faye, are you there?
Yeah, I'm around.
Okay, awesome. So we had some speakers that were coming from Germany, or not from Germany, from Europe, and couldn't make it, Ruslan, and I think Dieter might be running late, but I'm hoping he'll show up. Otherwise, yes, thank you all for coming to the speaker panel. Anthony will be hosting it, so take it away.
All right, thanks. So I'm going to give us a little time while Dieter's getting here. I wanted to kind of give a summary of the workshop. Thank you guys for hanging in here this whole time. Embodied AI 4 had 21 organizers, 26 challenge organizers, 17 scientific advisors, 6 speakers, and 4 sponsors. We had 10 challenges, 13 tasks, 50 submissions, and 10 winners. And each of the winners will be getting 300 from the workshop organizers. That's thanks to our sponsors, which include Hello Robot, Apple, and Logical Robotics. We had up to 60 people in the room in person and 32 online. There were at least 30 tweets to the Embodied AI hashtag when I checked earlier today, and over 26K views on the most popular tweet. But I think the content's really interesting. We've seen an amazing set of approaches. There are, to get data in the systems, we've been learning from video how to extract quality information from it, how to perform actions, learning from simulation and how to randomize it to get good sim-to-real transfer. For planning, we have chain of thought and multimodal models. We have language models interleave with constraints and learning components. And the models themselves, we have frozen models plus embedding mappings and combiners and approaches like self-supervision to help figure out the right approaches. So my first question for the panel is, it seems like almost anything can be done with a mix of some solid foundation model, some pre-trained or learned set of embeddings, nice set of data structures to store the output, algorithmics to handle some task constraints sometimes, and occasionally supervision or chain of thought. Is this an actual like architecture that's developing, or is this more just like a grab bag of techniques that we are kind of like throwing at a problem and hoping that some of them stick? Is there any unified thing that we can take away from all of these different approaches? Are we getting closer to something, or is it really, you know, we're just trying stuff and it's working?
Maybe I'll ask a slight clarification. So can you list the constituents that you are saying we are all putting together?
Well, it seems like
bit,
so.
right?
So it seems like many of these approaches, there's some kind of foundation model involving language. Often there's a set of embeddings either derived from that model or learned separately. And then that gets stored in some kind of data structure, some kind of map or network, and so on. And then occasionally we have algorithms to help us solve problems like the task and motion planning thing, which then feeds back into some kind of language model that that has some kind of chain of thought or some kind of sequence of self-supervision to help it make things consistent. And obviously I'm compressing over a lot of models, but these features showed up in a fair number of the presentations, and they showed up in a fair number of the challenge winners in various different permutations. And I'm wondering is this a grab bag of techniques, or are we starting to see some kind of coherent approach that's developing?
Yeah, I'll start with something and we'll see. So I think, I mean, I view this as a combination of high-level reasoning or like high-level things that you get from language and, you know, prior observation and such. And then there is like some low-level motor control that needs to happen in order for it to all work together. I think there's also language, and I think that's serving, in my view, the purpose of an interface and like high-level planning, right? And I see most of this work as a composition of these two things. And it's not too many things that are going on. I don't know, maybe I'm not understanding some aspect of it. But I mean, I guess there are these two components, but then to realize it, you need to absorb pixels and produce actions. And like a pre-trained visual model would be useful for those kind of things. So I think it follows a set recipe in my mind, at least. Curious what others think.
I think it's important to note too that just the breadth of tasks and problems we've been talking about here is, I think, at the extent such that we don't expect one single paradigm. However, we can narrow, right? So if we think of navigation specifically and all the progress that's been made there by this community for including like navigating an unmapped, novel environments, and then looking towards sim to real transfer, like this is, in my mind, has become so much more mature over the last 5-ish years, that there is more of a pathway. I think if you're a new student, say looking at that approach, there's stuff you're going to grab right off the shelf from the literature. There's kind of a including architecture or general paradigm for doing that. So, but that's one, in my mind, that's one trajectory, no pun intended, I guess that's one trajectory of like what we're talking about in all of embodied AI. I mean, if I take that term literally, I don't think we should see like a single paradigm emerging. We're looking at like the breadth of kind of problems, but that's what your question makes me think of.
Yeah, I guess I can also briefly chime in here. So if we look at embodied AI in its narrow definition, it's basically from sensor information. You're taking sensor information and you output actions to change the state of the world. That's kind of a narrow definition of embodied AI. In its broad sense, we can think of even more like embodied question answering and some more tasks. Scene understanding can also be thought of as embodied AI. And I think there are a couple ways to decompose this problem. Like one is you get the sensor information, you do some like state estimation, and then you act upon the states, like you can do some planning on top of it. So that's how we used to think about it. Another way to decompose it is like task planning and motion planning. So task planning is to figure out the steps to achieve a long horizon task, a long horizon goal, and motion planning is to figure out the trajectory or motor actions to fulfill those sub goals. So historically, there has been, for example, planning-based method like traditional robotics, state estimation and planning. And step by step, they are replaced or they are augmented by machine learning models that is learned in simulation, for example, or learn from like watching human videos. Now, I feel like foundation models is yet another tool that we can use in machine learning models, right? So it's pre-trained on large amount of internet scale data. It can perform decently in 0 shot. It can be prompted to have different behavior. So I view it as yet another way of using like learning-based method for these like high-level planning and low-level control. So that's what we have been playing around with.
So several of y'all just mentioned the breadth of the embodied AI problem. And we certainly have like 13 tasks and 10 challenge organizations. Is it possible to develop some kind of unified list of problems or some kind of unified challenge? I know there are tremendous practical challenges. I work with various efforts trying to compose more of these together into single systems, and some of them can't even be compiled on the same machine at the same time currently. But that doesn't mean that that's a practical thing. Is it feasible to think about trying to develop some kind of overall embodied AI suite, or are we too early for that process? And if we were to develop one, what would it look like?
I think I'll start. So I think, I mean, this is obvious. We have to kind of first, figure out what the landscape is like, and then we can perhaps start thinking about what are canonical problems. So I think the breadth is necessary, even if we come down to, okay, here are the few central problems in this area. So it's necessary effort. If I were to pick something, I would think about not just simulation, but also bringing the real world in, like doing things in the real world. And that has interesting avenues by itself. And I think in my view, that is slightly underemphasized because benchmarking is harder, but that's also a crucial piece to the puzzle. So I just want to bring that up.
Anyone else?
Maybe I can briefly chime in here. So when you mention like, can we develop some like unified notion of embodied AI, it makes me think of one project that like Stanford did a couple of years ago. Is called taxonomy, basically trying to find the taxonomy of tasks and what are the relationships between them. So all the perception tasks, they have some different taxonomy, and you will find, for example, learning semantic segmentation help with depth estimation or vice versa, or like there are a cluster of tasks that require 3D understanding. There are some tasks that requires more semantic understanding. So I think it will be kind of nice if we can do similar, basically a taxonomy of tasks in embodied AI, that you can point our fingers and say, hey, if I add more manipulation data, it also helps my navigation, right? Like maybe we can blur the boundary of different embodied AI tasks. Another thing that like makes me think is how snakes move on the trees. So if you watch how snakes move on the trees, they wrap around their body on the tree, and then it's basically manipulation and like locomotion in the same task, right? So that's really interesting. And maybe we can start to blur the boundary of different embodied AI tasks. Like the snake is manipulating the tree, but it's also moving itself. So I think it'll be beneficial if we can establish such a taxonomy of different tasks. And I think in one of the organizers, Luca would be have a lot of experience on that, because Allen Institute had an attempt of doing this. I think there is a suite that is basically trying to encompass all embodied AI tasks. So it will be easier to train agents and benchmark agents in different embodied AI environments, simulation environments, for example.
Okay. Just want to make sure everyone has a chance to weigh in. Okay, if there's no more, I want to go to a question from the online. Does embodied AI, practically speaking, seem to need reinforcement learning in order to achieve high-level tasks with embodied agents? Anyone?
Yeah, I think I think there is quite a bit of emphasis on want to do end-to-end RL for X. I think that is I feel that might not necessarily be the right solution all the time, and maybe it's and we have seen lots of work where modular approaches, particularly for navigation, have proven to be more effective. Things that separate out the high level use some other kind of data to learn the high level, and then the low level is learned using RL. Seems to be more effective, at least in the current regime of data and compute time that we can invest. So yeah, so I think I would have said yes to that question, because the low level, perhaps we need RL for that, like low level skills and the like what Dieter was presenting. The high level, I think we could do without RL. I think something more classical could work there. I mean, you don't need RL. I mean, there are many examples of that kind of work too, right? So I think that's my view. Now, the low level also you could replace with something more classical in certain limited settings, but that won't always work out. I mean, it can work for some application, may not work for some other application. So end-to-end RL, in that sense, for the low level skills, I think would be useful and necessary. Yeah.
Yeah, I agree. I agree with your assessment too. And I think it's like if we're saying, is any amount of experience needed, any in any degree. I think it's wise to expect yes. And just another dimension to add was Sarah was saying is like embodiment changes or small changes or corruptions of agent or upgrades of agent. You know, we think like the evolution that has to happen, that it seems like a natural place where also experience-based learning or reinforcement learning would play a critical role, if not a more efficient role, you know, or handle more efficiently than alternatives, we could say. Yeah, and I'm glad you said about like maybe there's some waves of obsession of end-to-end RL, and we don't have to go like that. May not be, that's not even what your question was either. I think it was, is we always going to need some reinforcement and some feedback from the environment based on our actions. And I think that one seems safe to say, yes, let's not abandon that. And it doesn't mean it's a commitment to like RL for end-to-end only.
Faye, do you want to weigh in on this one?
Yeah, so I think we have some data points. So for like low-level actions, there has been a lot of success with RL, such as in locomotion, a lot of the work has been using RL and then distill a policy out of it. And for manipulation, we have seen some success with behavior cloning, but for RL, we find it generates trajectories that are a little bit too jerky. Maybe we didn't engineer the reward well enough, but I think the field has produced some pretty good work that is using RL for like manipulation. In terms of high-level reasoning, I think there are many other alternative approaches, such as like PDDL, you know, like some symbolic solvers that can be helpful here. And also in high level, it's also quite close to like language models. So if we want to use RL, maybe we still want to use language models to guide your search instead of using RL to blindly search for a solution. So I think it will be a combination of RL and some heuristics from foundation models. That seems a promising recipe.
Okay, so take one more. So this is I see a question from the Slack, which is I was about to ask. So I'm going to skip forward to that one. On learning from video data, which I'm glad that we have like Sarab and Kristen there, is that it seems like we have some very powerful techniques for extracting information from videos, which seems like that. I agree, we're probably not going to be able to get rid of RL per se, but we've gotten a lot of information out of videos. How much more headroom do we have in extracting data from video, or in terms of the sophistication of behaviors that we believe that we can extract?
I mean, the short answer is there's lots. I feel like we barely scratched the surface, right? As far as getting, and I think you mean this specifically for translating to agents, right?
Yeah.
I think it's very, very early in my mind for what we're getting from video and what it can mean for instructing an agent. So.
Are there challenges in grounding that data in the agent's environment? Like once you actually try to translate it back to action? Because like the environments that we learn the video from are very different from the ones our robots are generally acting in.
Mm-hmm. Yeah, I mean, again, it's at all levels too, I think. I mean, so if you're talking about reducing to like hand postures, which was an example I gave, then there's their own challenges there, but you're abstracting away, ignoring the surrounding visual context. If you're talking about things that are more navigation oriented, including some of Sarab's earlier work, like really pioneering, looking at like the human point of view as you move through a space and navigation, then the scene is very central. So that's where that kind of alignment, I think, becomes more relevant. So yeah, it really depends at the level, I think, that we're trying to pull to guide the agent. Yeah, you were going to say?
Yeah, no, I agree. I think my biased answer would be there's a lot to be done. I think I'll agree completely with Kristen. Like we just scratched the surface. And yeah, there's so many exciting. And I think what you mentioned, that the things that you see in videos are not exactly the environments that you are acting in. That's a interesting challenge, right? Like, how can you transfer across these domains? There is embodiment gap. Humans have different end effectors. Robots might have different end effectors, but could you still learn in spite of that? I think that would be important and useful to look at. So I view it as an opportunity for doing something more creative.
Faye, anything to?
Not really, but I was really curious about the embodiment gap. Like I was just wondering, to fully leverage the human video data, like do we have to build a humanoid and build a dexterous manipulator, or do you think there are promising ways that we can transfer to a different embodiment, like a parallel jaw gripper? And another thing is that eventually we probably want robots to be better than human. Like if we are like just using the human data, how can we bootstrap to get potentially better, more dexterous behavior?
Cool. So unless you guys are going to weigh in on that, are you guys going to weigh in on that question? Or
Yeah, I was going to say, I think that's an excellent point. I think imitation has this limitation that you're bounded by the performance of the expert, but then this could be used in conjunction with more interactive forms of learning, and it could be used to, let's say, bias exploration or goal setting. Lots of variations, right? So, but I agree with what you're saying. Yeah.
Kristen? Okay. So we've had a number of approaches that used large language models and similar things for embodied AI and similar control tasks. I was wondering if you guys could talk about your thoughts about and we already touched on this a little bit earlier, but this is a question from the Slack. What are your thoughts on the role of LLMs and similar foundation models for embodied AI? And I think, Saurabh, you touched on this earlier. Maybe expand on it a little bit.
Yeah. So, okay, I think I like to, I guess this has been said multiple times, but so foundation models, by foundation models, we are basically referring to large scale pre-trained models, right? So they've been around for a longer time. So it's not like suddenly 2-3 years ago, there's been a revolution. I think it's a slow progress, right? So I don't view them as a very large, I mean, it's a large leap, but it's been on a continuum. Now, I think large language models, I think my view is, and I'll be very surprised, is they are useful at the very high level. I think you have to go below a certain level. I think the large language models are actually not useful at all, I would argue. I think Alyosha has this beautiful example that he gives, which is, think of learning how to climb stairs by someone describing how you climb stairs. And he has like a passage from some book that you can read and such. And, I think language is so abstract. I think like certain visual motor, sensory motor things are just not expressed in language. And so I think if we just believe in LLMs, that LLMs will solve robotics, I think that's not going to happen. So my view is it's useful as an interface. It's useful for high level planning kind of things. And that is great. But at the same time, it doesn't replace the effort that is necessary for building basic sensory motor intelligence, which, very basic organisms have. So I think that's my take. Yeah.
Maybe I can briefly weigh in on this. So I think language models provide an excellent tool. Like it definitely doesn't solve all problems for robotics, but maybe it can help us concentrate on the harder problem of robotics. Like we all know that generating fine like motion, generating action is difficult. So maybe we can all focus on that and treat the task planning or high level reasoning more like a solved problem. So it helps to kind of help us focus on energy on harder problems. The other thing is that I feel it's a little bit weird to say, but like we can lean on the progress of language models. Essentially, the progress from the NLP community trickle down to like the robotics community or embodied AI community. Just giving you an example, like when earlier last year, we published SayCan. We use a slightly weaker language model, which is FLAN, instruction fine-tuned variant of Lambda, which has 137 billion parameters. And we get about 70-ish% like success rate in SayCan tasks. Just by upgrading it to a better language model, PaLM 540 billion parameter model, we achieve like probably 10% or 16% higher success rate in task planning. So we are not changing anything about robotics. Just by replacing the language model, we are getting better performance. So I feel like we are riding the wave of like those large foundation models, and you can essentially get some progress for free. It definitely helps a lot with like high-level reasoning, and all these latest multimodal models. You can also just use them, and they also bootstrap like high-level reasoning. So you can use them as a backbone and just fine-tune the part that you want, and then seemingly a working recipe to get good performance out of those foundation models for a specific domain.
Kristen, do you want to weigh in?
I don't really have anything to add. I think that's exactly where we're at. Yeah.
So my concern with this is I get a little.
We can't hear you.
You cut out. We can't hear you, Anthony. Still, oh no. No, he's not. He just disappeared.
Can you hear me now?
Yes.
Okay. So what I was saying is I'm concerned about these pre-trained models. I don't know how much you guys heard or not. You didn't hear a darn thing. Okay. If I suddenly disappear, there's a thunderstorm and lightning has struck my internet cable. So I'm concerned with these frozen models because like 15% or 16% improvement is much better than some of the gaps between the baselines and some of the models that were.
Yeah, we still can't hear you, Anthony. Oh.
Can you hear me now?
Yes, yeah.
Okay. If I drop out again, would someone just wave their hands rapidly and okay. Are these frozen models a problem for us? 15% is more than the difference between baselines and some of the challenge winners that we saw today. And it's putting a lot of our success in the hands of other teams that we don't control. Do we need a foundation model for robotics that we're training and that we're developing? Or are we forced to be, riding this wave? Do we know enough to build that foundation model?
I think I can start. I'm not worried about this at all because I don't think LLMs will solve robotics, right? I mean, they are useful for the high level planning bit, and that's good. But robotics is not hard because of the high level planning bit, or it's equally hard, if not more, from the low level control aspect, right? Like dexterous manipulation, et cetera, right? Those aspects are actually really hard. And I would go on to say, I think we should not be distracted by all the improvements in LLMs because they're not going to solve the basic sensory motor intelligence problem for us. So yeah, I'm not worried about this at all.
Okay. And if no one else wants to weigh in, one of the a lot of the work we've seen has been focused on indoor environments and controlled settings. How well will these this work translate to outdoor scenes where the ground is not level, and you have more people interacting with the robot, or greater variety of non-manufactured objects.
Yeah, I think this is right on point. I mean, maybe the positive version of this is that this community has found ways to, leverage simulation, especially in indoor environments and without the social elements, to make really rapid and controlled progress on certain problems. But that's great. And that's a lot of work that's worth doing, continuing, but it does seem in this part of the community. And by that, I mean, we clearly don't represent this workshop doesn't represent all of robotics, for example, but, this is at the exclusion of some of the challenges you just mentioned. So I don't know, I think of it as a well worth it focused study and reproducible results and benchmarking, which is fantastic. But because of parameters that have to do with what are those things we can control and benchmark, model, and have at scale for scanned environments, for example, yeah, it does mean a certain carved out part of the space. I think that's definitely true.
Sarah Burfay?
No, I agree. I think, yes, it's not everything, but it is substantially interesting and useful. And, interesting things will come out, which would be useful for the other settings too. And I mean, yeah, nothing more to add. Yeah.
I think nothing is fundamental between indoor environment and outdoor environment, and you can get arbitrarily complex in indoor environment as well. So it's mostly just a function of your locomotion capability, if you can travel in smooth ground or rough terrain. So yeah, I think for embodied AI community, it's not super productive to make this distinction between indoor and outdoor. So whatever we're developing, I think can be used both in indoor environment and outdoor environment.
Okay. Can y'all hear me? Okay. So my next question is about safety and long-term tasks. And one of the questions in that Luca raised in the chat was, can we trust the plans generated by LLMs in the real world? How can we prevent the long tail of horrible potential outcomes? And specifically, there are some things like safety layers to prevent robots from running into the wall or running over my feet, which, that didn't always work. But with long tail tasks, there's complicated sets of outcomes that it's hard to necessarily say, okay, this thing that the situation the robot is set up is intentionally or unintentionally very, very bad. How can we detect and prevent these kinds of outcomes, especially if we are relying on LLMs as a source of our task planning?
Yeah, maybe I can start on this one. So I think as we are using the language models, it's a double-edged sword. So we are getting the benefit of it can do task planning zero shot, but we are also getting the vulnerabilities of language models, such as the biases or being hallucination and something else. And as we are deploying this in the real world, we actually have more responsibilities. For example, if you tell a robot, take out the bowl from the dishwasher, feed my cat and put it back in the dishwasher, will it put your cat in the dishwasher? If when those actions got rolled out in the real world, the any bias or safety issues of the language model get amplified. So I think we need to have a lot of safety steps, safety layers, not just on the hardware level, but also on the software level, from very high level to very low level. Everything need to have a safety layer, and also we can treat the safety as a grounding or affordance problem. So far we have been thinking about affordance as whether you can do it here, whether you can do it in the certain environment, but there could also be safety as an affordance, it is safe to do a certain thing here. if we have those in place, like we'll have safer robot and we'll have a better time deploying like large language models in the real world. But it's ongoing discussion that I think the community need to chime in as a whole.
Kristen or Sarah, any comment?
I'd say I think it's another very large model that has been trained. We will fine tune it for these kind of things, and any kind of learned model has this issue, and this will have it too. And whatever we do to deal with that, we'll have to do to deal with this. So, but yeah, it's a thing worth thinking about. I think this is an important question.
Okay, I think we have got a couple questions in the room.
Hello. Okay, so from what I understand, I think there is some amount of simulator usage for I think all of the panelists, and some amount of simulator development as well for at least some of the panelists. So for your favorite simulator, suppose you could like direct the efforts of the group that is developing that simulator for a year and just like allocate them to do whatever you want. So how would you, what would you do? Would you get them all to sort of familiarize themselves with Blender so they could make better art? Would you like get them to design faster GPU hardware so the thing runs faster? Would you get them to like scan more stuff and bring it into the simulator, higher fidelity sound? How would you allocate that budget of sort of development effort for on your favorite simulator?
I think I'd ask for more interactive objects, so ability to have, articulations and if not even deformations and things to this is a big ask, but yeah, that's what I think we would benefit a whole lot from going more in that direction.
Yeah, the same here. I'm actually quite interested in manipulating deformable objects, like things like plants and leaves and fluids and contact rich tasks. And I think either we don't have simulation for some of these things or they're very slow, and it'll be nice to have something over there. Yeah.
Cool. Yeah, this is a great question for me because I did spend 5 years of my PhD building simulator and building simulation. So it's almost triggered my PTSD. I think, yeah, so during my PhD, I spent some time first building a neural rendering engine to do better rendering. And then I spent maybe 2 or 3 years to kind of create articulate objects from like environments. And then you have this articulation, like Kristen just said. And then I also spent some time designing tasks, like designing long horizon mobile manipulation tasks for robots. However, if like I'm given the budget and power to direct a group's direction for a simulator for a year, I think I would treat the simulation and learning as an integrated system. Like whatever simulator you build, it needs to help learning, not just a building simulator for the sake of simulation, but treat the entire thing as a whole. So maybe you want to, just to give an example, maybe you want to write your physics simulation also using JAX. So your simulation and RL can be all in JAX, end-to-end differentiable. That might be interesting. Or maybe like you want like neural rendering or like neurophysics so that the simulation can improve itself when you observe some rollouts from the real world. So that has been my dream.
Okay, I think we got everyone, right? So was there another question from the room?
Okay, hi. This might be a little bit controversial. I'll just ask. So for most of the RL-based work for manipulation, a lot of the time the demos that I look at usually have pretty nice set of objects that if you do traditional control and traditional 60 degree of 60 of pose estimation for the objects, you could do that for the objects at least I'm seeing for RL-based work. So my question is, why are we like, when are we going to move away from that, or why are we doing that still if it is possible? And secondly, it's actually would be safer to do traditional control and just pose estimation than to do RL when it goes into a space where it doesn't know what to do. So Yeah, sorry, it is a controversial question. Yeah.
I think this is a great question. I'd start by saying I think so. 6-drop pose is sufficient if you know the know the object. If you don't know the object, then it's difficult to decide pose and so forth. So I think that's one detail which is important to note. Second is I think there is work which does more interesting, more like harder tasks beyond pick and place tasks. So I think Dieter had a few examples of like rotating cubes, and I think other groups have this. And I think if you, but not everyone has it, partly also because the hardware, which is parallel jaw grippers, is quite limiting in terms of what you can do with it. Plus haptic feedback. So if you're trying to do things with, soft things and such, you may be wanting haptic feedback. So I think it's all a combination of that. But I think, 6-drop pose estimation by itself doesn't work. I mean, there's some more details there. I think that's.
I think there are two main reasons you might still want to use RL. One is robustness. Like imagine if you just cannot do a super well state estimation or system identification, you just have some like mismatch. So maybe using RL, you can do some randomization. While if you're using state and traditional plan, you might not be able to design a robust enough controller to handle all possible like out of distribution scenarios. The second thing is that using RL, sometimes you can also find emergent solutions. So sometimes you need to reorient an object in order to grasp it. I would say it's pretty difficult to plan for that using a traditional planner.
So, Kristen?
All right, so if I could ask a question, I saw some pretty impressive work today, and I'm kind of curious if, now that robots seem to be working fairly well, these embodied agents indoors doing certain tasks, have you reached the point they can do useful, helpful things for people that are practical, or are there sort of missing technologies or bits of it that we should fill in first before they can actually help somebody? Go get me a cup of coffee, or do the dishes, please, or whatever task that might be. Have we reached the point where we're actually made something useful for humanity?
I mean, I think the vision that you're painting has the big obstacle of fine-grained manipulation. Curious what everyone else, how others look at that.
And robustness. I think things work in simulation, but they may not work in the real world. So I think that's also important.
And another thing, a big obstacle is hardware. Can we get like cheap enough hardware that can have enough payload and enough like accuracy that can do well in the real world? So I feel that's one of the biggest bottleneck.
And just weighing in myself here, it's like we had a task that was performing like close to like 90 or 98% in some of our simulated benchmarks, and even in some of our physical things. And then when we tried to do it in a large scale building deployment, the success rate was less than 50%. And then it was another couple years of work to bring it back up to like 98%. And that wasn't a diverse task. That was one building scale task. And a lot of the things that involve robots trying to help people involve open set questions, which is why the language models are so important, which require a much larger diversity of skills and object recognition and so on. So I think that if we were to try to like do a deployment, my expectation is that we would eventually do very well, but that it would be a lot of research work. Were there any more questions for the audience, or should we take some more from the from online?
Thank you.
All right, then I'm going to go for another question. So say we had a time machine and we were at Embodied AI 5 next year. What would you guys want to see happen in the intervening years worth of work? And it can be, what challenges do you want to see what happen? What problems do you think are currently the hard nut problems you would like to see some work on tackling? What data set do you wish was created, or something I haven't mentioned? What
maybe start with Kristen. What would you like to see happen a year from now if you could control what the community was going to do? Big responsibility.
Yeah, I mean, a year is not a lot of time. When you said 5, I thought we were about to go forward or backwards, more like 50 years, but we're going forward a year. So, I mean, I think like my first answer is, we've in the various talks, people are laying out what they see as the big important challenges. And so this is it. I think we're looking on that time scale for sure already. I mean, a practical thing for those of us like me coming really at the computer vision side and so on, but looking to understand credibly, the physical robotics side. We have early days in my group of doing some sim to real transfer. And it's a judgment call of like how much investment to make in the next year or the next 10 years, on that side versus the important parts of the problem that can be circumscribed with the perception challenges and with video, et cetera. And so I don't know, that's not like, I think that's just on the table in my personal research agenda, because I can see success or value in either way. But it's an investment to decide on, right? For any given lab as a community, it has to happen. But there's different parts of this that any one group could be choosing to work on.
Yeah, so I think 1 year is not a lot of time. So, I mean, I have a very long wish list, but I don't think most things will be done in a year. I think one thing which I would really benefit from is, or like the immediate research in my group would benefit from is perception models that work well on egocentric video data. I think would be useful, like trackers which can track through, occlusions and high-speed motion in these things, and like even detection or like some sort of 3D estimation. I think those things would be very useful.
I think I would like to see more research of like human-centered like robotics or embodied AI. So far, the embodied AI agents have been exploring with the environment. It has been interacting with the environment, but the most complex element in the environment is actually human. So like ideally, there should be more interaction with humans. So I think using language model is a great starting point because it allows the agent to communicate with human and understand human. But there are much more to it, like helping human or like social navigation. There are a lot of interesting problems I think worth exploring there.
Okay. What do you think so I'm going to make this, we're just closing in on time. So the last question I would have is, which is sort of building on this and looking more at like that 10-year horizon. What is the biggest challenge that the community is facing? Where are we weakest that needs the most effort?
Fine-grained manipulation of hardware or software or sensing. All of these are interesting questions. Yeah, I mean, hardware or simulation or sensing. Yeah.
Well,
would say manipulation as well, like fine-grained manipulation, and also learning from just a handful of data, a handful of demonstration. That seems also challenging.
Yeah, I think we've hit this question in different forms, and I have to, again, I would say fine-grained manipulation too. And just to try and add to the mix, I think when related to Faye's just example now, like like generalization in a cross task, so the more, I mean, naturally, the more narrow we allow ourselves to be to really nail it, we're narrow, and then like just trying to zoom out and imagine like what real flexible, robust, task agnostic behavior would look like. That seems like a huge challenge, even in the problem description, like making the right problem description of that, and how do you convince or decide that you've achieved task generality. So that could be another dimension.
I think that's a really important one, because I think if you look at the dozen odd
different tasks that we have and try to like look at the commonalities among them. There's some things that are very common, and there's other things that are just like, well, this one has an off-the-wall variation, and you could easily imagine 10 more that were very, very different. And so I feel like the problems are a challenge, but I am hearing, like we hear over and over again, both in like, what simulator would we want? We would want to be able to manipulate objects. What would people want us seeing doing? Manipulating objects that are harder. And so it seems like fine-grained manipulation. And also that comes back to some of the earlier talks where the geometric constraints that propagate along a task, like trying to ship a poster to CVPR is challenging because some of them won't fit in. If you make printed too large, it won't fit in a suitcase, right? That is a complicated geometric challenge. So I think that there are manipulation does seem to be like something that's coming up a lot that maybe we should be looking more closely at. Well, I wanted to, we've come up on time, and I want to be respectful of everyone's time, both our speakers and fellow organizers and our audience. This concludes our speaker panel, and I will let Luca or Claudia on site close this out physically, since I'm remote.
Thanks, Anthony. Yes, thank you all for coming. This was the fourth Embodied AI workshop. Let's thank the speakers one more time. And it's been a pleasure. Thank you.
Thanks a lot to the organizers for putting this together.
Thank you, guys. Claudia, Luca, good job. Thank you so much for all of your hard work and coordinating and organizing this and making sure people showed up and everything. I want to thank you guys so much.
Yeah, thanks for hanging around all day and yeah, doing all the stuff in the back. It's
the
great.
website.
Yeah.
This is perfect.
And thank you to everybody that's online that came. That was great. Okay.
All right.
Cool. Talk to you.
I will talk to you guys soon. You guys enjoy the speaker dinner, and hopefully we'll see each other in the rectangles in some kind of post-awesome sometime after we all have a chance to chill out and have a nervous breakdown.
Awesome. Perfect. Cool. See ya. This has been a successful meeting. Goodbye.
Bye-bye.